Hey there, and welcome to the ultimate full-stack development course, where we'll dive into FastAPI, React, and MongoDB. In this course, you're going to gain some hands-on skills in creating dynamic web applications, tweaking APIs, and effectively managing databases. Get ready for some engaging coding exercises that will really challenge your skills. And hey, don't forget to check out the GitHub repository linked in the description for all the code. You'll want that, trust me. Stick around until the end because we'll be crowning your learning journey with a final project to showcase everything you've mastered. So, let's jump in and get started. Let's dive into the Farm Stack, a powerful combination of technologies that enables developers to build robust web applications. The Farm Stack consists of FastAPI for the backend, React for the front end, and MongoDB for the database. Now, this trio provides an efficient and scalable foundation, making it easy to create dynamic applications that can handle a variety of tasks. So, imagine you want to build a web app that can manage user data. With FastAPI, you can set up your server quickly, allowing for seamless interactions between your app and its users. On the client side, React brings your user interface to life, making it interactive and responsive, which is crucial for a great user experience. And when it comes to storing all that information, MongoDB has got you covered with its flexible document-oriented database structure. Put these technologies together and you get a clean, efficient workflow that can adapt to your needs, whether you're building a simple prototype or a full-scale application. So, if you're looking to dive into web development, the Farm Stack is definitely a combination worth exploring. Now, let's implement the following FastAPI application. We begin by importing the FastAPI library, which is essential for creating our web application. Next, we create an instance of the FastAPI class. This serves as our main app. Now, to define a route, we use the @app.get/decorator. What this does is map a GET request at the root URL, which is just /, to a function called readRoute. This function is asynchronous, meaning it can handle multiple tasks without getting blocked. When called, it returns a JSON response containing a friendly welcome message. This structure is key, allowing FastAPI to perform efficiently. Now, to run the application, we'll use Uvicorn, an ASGI server. You execute a command pointing to our main.py file. Don't forget the -reload option. This allows any code changes to automatically trigger a server reload, smoothing out your development process. Once you launch the app and open your browser to http://127.0.0.1:8000, voila! You should see your welcome message, which tells you that your FastAPI application is up and running. Now, let's integrate MongoDB into our FastAPI application to manage user data effectively. First, we'll import the necessary modules, starting with FastAPI, which is our web framework. This is followed by Async.io Motor Client from the Motor library for that oh-so-important asynchronous Mongo interaction. And we'll use Pydantic's base model to define the data structure for our users. Next, it's time to establish a connection to our MongoDB instance. We'll specify our database named UserDB. To define the user data, we create a user class with name and email fields. This takes advantage of Pydantic's validation features, ensuring that our data remains intact. Now, let's write the endpoint to add a user. The createUser function will listen for post requests at the users/path. When called, it extracts the user data from the request, inserts that into the user's collection, and responds with the stored information, including the newly generated user ID. Pretty neat, huh? In addition, we define a getUsers function that handles GET requests to fetch all users from the database. It retrieves the user documents while ensuring that the IDs are converted to strings for proper JSON formatting in the response. With this setup, we have a solid foundation for user management in our application. The figure titled Key Advantages of Farm Stack Technologies displays a simple bar chart comparing the perceived advantages of FastAPI, React, and MongoDB on a 1 to 10 scale. On the x-axis, we have the three technologies, FastAPI, React, and MongoDB, while the y-axis quantifies their advantage scores. So, looking at the bars, we see numeric values, 7 for FastAPI, 8 for React, and 9 for MongoDB. From these values, we can draw some interesting conclusions for your tech choices. MongoDB ranks the highest at 9, which suggests its flexibility and schemaless data model are really valuable, seen as the strongest advantages in this comparison. Next up, React, scoring an 8, reflects its strong front-end capabilities and developer ergonomics. And then we've got FastAPI at 7, indicating it offers excellent backend performance and productivity, but it's just a tad lower compared to the database and front-end options. Now, notice how the scores are clustered in the high range, from 7 to 9. This suggests that all three technologies are quite valuable. MongoDB stands out with the most pronounced advantages, while FastAPI still delivers solid backend benefits. These relative scores really support the idea that the farm stack components are complementary. Just picture it. MongoDB's data flexibility pairs beautifully with React's front-end strengths, and then FastAPI rounds it all out with its efficient API layer. Together, they create a balanced and robust stack for building modern web applications. Now, let's dive into implementing some code in our React application to create a user interface that interacts seamlessly with our FastAPI backend. We begin by importing React along with our essential hooks, useEffect and useState. These hooks are crucial as they help us manage component state and handle side effects. All right? Next, we define the app function component. Here, we're setting up two pieces of state, one for holding the list of users and another for our form inputs, which include the name and email. Now, let's make the magic happen with the fetchUsers function. This function is designed to retrieve the list of users from our FastAPI API. It performs a GET request to the /users/endpoint and updates our user state with the return data. We've got to call this function within the useEffect hook, ensuring that our users are fetched right when the component loads. Perfect. Now, let's talk about the handleSubmit function, this little gem. It prevents the default form behavior and sends a POST request to the /users/endpoint, passing along the name and email as JSON. If everything goes smoothly and the request is successful, we'll clear our input fields and call fetchUsers again. This way, we refresh our users list and showcase those real-time updates. Finally, the component returns a form for inputting new users and displays the existing users in a list that dynamically updates whenever a new user is successfully submitted. That's how we create a smooth, interactive user interface with React and FastAPI. First, let's implement Axios to enhance our API interactions in the React application. First, we need to import Axios, which is a promise-based HTTP client that makes it super easy to send requests to our FastAPI backend. Next, we'll define the fetchUsers function. Here, we're using Axios to send a GET request to the /users/endpoint. By using await, we can seamlessly handle the asynchronous response and set the user's state with the data we get back, if the request is successful, that is. Now, if anything goes wrong during this process, we catch the error and log it to the console, which is crucial for debugging and keeping our workflow smooth. Now, let's shift our focus to the handle submit function, which is in charge of adding new users. This function kicks in when the form is submitted. It makes a post request, again using Axios, sending along the name and email data. If all goes well, we clear the input fields and refetch the user list to dynamically reflect those changes. This approach not only keeps our code cleaner, but also greatly enhances our error handling and overall user experience. Let's wrap it all up. We've built a complete farm stack application with FastAPI as the backend, MongoDB for data storage, and React as the front end. This combination is not just efficient, but also scalable, making it a favorite among developers. As you dive deeper into building applications with the farm stack, consider exploring more advanced concepts like JWT authentication for securing your API, or maybe even incorporating state management libraries like Redux for larger applications. When building applications, remember that practice is key. Try adding new features like user authentication, or explore utilizing more complex queries in MongoDB. The goal here is to not just understand how these technologies work together, but to get your hands dirty and start building real-world applications. Thank you for joining me in this journey through the farm stack. I hope you found this tutorial informative and that it sparked your interest in creating dynamic web applications. Happy coding! Understanding MongoDB for data storage is crucial for developing efficient, scalable applications. Whether you're building a robust backend or a simple application, knowing when and why to use MongoDB can help you leverage its strengths in dealing with data. So far, we learned about the farm stack, which includes FastAPI for the backend, MongoDB for data storage, and React for the front end, providing a robust framework for web applications. We set up a basic FastAPI application that offers endpoints for user management and integrated MongoDB using the motor library for asynchronous data handling. We also created a React frontend for interacting with the FastAPI backend, allowing the addition and retrieval of users. Finally, we refactored our API calls to use Axios for cleaner code and better error handling, while emphasizing the importance of hands-on practice in application development. Now, we will dive into why you should choose MongoDB for data storage, highlighting its key features, benefits, and practical examples. Let's kick off by discussing the primary reasons for using MongoDB. First and foremost, it's a NoSQL database, meaning it doesn't use a traditional structured schema like relational databases. This flexibility allows you to store unstructured or semi-structured data without being confined to a predetermined format. In the world of modern applications, where data formats can evolve rapidly, MongoDB gives you the freedom to adapt your data structure as needed. Imagine you're developing a social media application. You might have users who post text updates, images, and videos, each of which has varying metadata. Instead of trying to force these different types of data into a single schema, MongoDB allows you to store each user's data in a dynamic document format, making it easier to accommodate varying requirements. The figure titled Key Features of MongoDB for Data Storage presents a horizontal bar chart showing 5 features and their importance on a 1 to 10 scale. Flexibility, rated at 9, scalability at 8, querying capability, also at 9, community support at 7, and document model at 8. Now, each of these features is shown with a distinct horizontal bar, and you can see the numeric importance value clearly displayed at the end of each bar. On the x-axis, we have labeled Importance, 1 to 10 scale. It's pretty interesting to note that flexibility and querying capability are scoring the highest at 9, which means they are viewed as the strongest and most critical aspects of MongoDB. Scalability and the document model follow closely behind at 8, indicating solid value for managing large datasets and representing data as documents. Community support, while still positive, is slightly lower at 7. It's the least emphasized among the five. Now, from these values, we can draw some practical conclusions. When you choose MongoDB, you can definitely expect exceptional flexibility in schema design and strong, expressive querying capabilities as its primary strengths. The document model and its horizontal scalability are, well, also robust features that make MongoDB a great fit for distributed and evolving applications. Although the community support is decent, it's wise for teams to also rely on official tools and documentation to bridge any gaps that community resources may not cover as thoroughly. Now, from these earlier examples, like dynamic user documents, geospatial queries, and sharding, this chart really drives home that MongoDB's core capabilities align with the design choices we've highlighted. Now, favor those document-centric models, make the most of those rich query operators, and use sharding patterns for scalable growth, while, keeping in mind to incorporate all available tooling to complement where community resources may be comparatively less emphasized. Now, let's take a look at how we can define a new user in our MongoDB database using the motor library, which allows for asynchronous interactions. First, we establish a connection to the MongoDB server by creating an async.io motor client instance, and we'll specify the URL of our database. In this example, we're going to connect to a database named SocialMediaDB. Next, we define an asynchronous function called createUser, which takes three parameters: name, email, and posts. Inside this function, we prepare a dictionary named userdata that holds the user's name and email and, you guessed it, an empty list for posts. This flexible structure allows us to adapt and expand the data we associate with a user, pretty cool, right? Reflecting real-world scenarios without needing to alter our database schema. After forming our user data, we utilize the insert1 method of our database to insert this document into the users collection. The result of this operation is captured, so we can return the newly created user's ID. This process really showcases MongoDB's document-oriented approach, enabling those dynamic user structures that evolve alongside our application's needs. Now, let's dive into implementing a basic sharding strategy in MongoDB to enhance scalability. Sharding is a fantastic way to distribute data across multiple servers, and trust me, it shines during high-traffic scenarios. So, in our example, we're going to issue a command to the MongoDB admin interface, specifically targeting the user's collection. We'll utilize a hashed key based on the _ID field. Now, why do we choose to hash the _ID? Well, it ensures a balanced distribution of user documents across various shards. Pretty clever, right? This approach really boosts performance under heavy loads by preventing any one shard from becoming a bottleneck. When sharding kicks in, MongoDB takes care of routing queries to the right shards, which means seamless data access for us. The command itself isn't just a series of text. It represents a conceptual framework, illustrating how straightforward it is to partition your data effectively. So, remember, this code snippet is more than just a command. It's a vital strategy for managing large datasets, giving us the robustness and responsiveness we need in applications like e-commerce platforms or social media networks, especially when performance during peak usage is absolutely crucial. Now, let's explore how we can implement a function to retrieve users based on the number of posts they have. We'll define an asynchronous function named getUsersWithPost, which takes a single parameter, posts count. Inside this function, we will use the MongoDB find method to filter user documents that have a specific number of posts, making use of the powerful this operator. This operator is quite handy because it allows us to intuitively evaluate the size of an array, in this case, the posts array for each user. Once the query runs, we convert the cursor to a list using the toList method, resulting in a straightforward collection of users that match our criteria. Now, one of the real advantages of using asynchronous operations with await is that it keeps the application responsive, even when we're dealing with large data sets. Finally, the function returns this list of users, which can be utilized in various parts of the application logic, whether that's displaying results on the front end or processing them for additional functionalities. This example beautifully illustrates the simplicity and effectiveness of MongoDB's querying capabilities, reinforcing its benefits over traditional SQL approaches. Now, let's see how we can implement a user schema using Mongoose, a powerful object document mapper from MongoDB in Node.js. In the code, we begin by importing the Mongoose library, which is essential for setting up our data models. Next, we define a user schema. This schema encapsulates the structure of a user document and includes fields for name, email, and an array of posts. Think of this schema as a blueprint for our data, ensuring that every user created conforms to this defined structure. Once the schema is established, we create a user model from it, allowing us to interact with the corresponding Mongo database effortlessly. Now, the code then proceeds to define a function called createUser, which accepts parameters for name, email, and posts. Inside this asynchronous function, we instantiate a new user object based on the details provided, and we employ the save method to store it in the database. This approach abstracts much of the underlying complexity of interacting with the database, enabling developers to focus on building application logic without getting bogged down by the intricacies of database management. Now, let's implement a location-based query using MongoDB's powerful geospatial capabilities. This code defines an asynchronous function that retrieves users based on their proximity to a specified geographic point. It takes 3 parameters, longitude, latitude, and maximum distance, making it flexible for different search needs. Within the function, we construct a query that utilizes the .near operator, specifically designed for geospatial searches. By setting up a location field in our user documents as a geospatial index, we allow MongoDB to efficiently find nearby users. The query forms a point geometry with the provided coordinates, ensuring that our functionality is both accurate and effective. Now, the .max distance parameter allows us to limit our search to users within a certain distance from the point. This feature is especially useful for any applications that rely on location-based services. Finally, we execute the query asynchronously by calling toList, which returns all matching users. This implementation highlights how MongoDB's geospatial querying capabilities can significantly enhance location-aware applications, improving user experience and offering competitive functionality. Now, let's dive into implementing a multi-document transaction using MongoDB in Python. This code snippet will show you how to create a new user and a corresponding post all within a single atomic transaction. It's super important that either both of these operations succeed or neither does, as this is crucial for maintaining data integrity. So, we begin by establishing a database session with start session. This allows us to execute multiple operations within the same context. Next up, we'll use the start transaction method, which signifies that everything we do afterwards is part of a single transaction. In this block, the first thing we do is insert the user data into the users collection. And here's a neat part. We retrieve the resulting user document's ID, which we'll use when adding the new post to the posts collection. This links the post to the user effectively. Now, if anything goes awry during this process, the transaction will roll back, keeping our database in a consistent state. This feature is especially useful in applications where multiple related changes need to be treated as a single unit of work. It's a great demonstration of MongoDB's capability to manage data relationships while still being flexible. In conclusion, MongoDB's flexibility, scalability, powerful querying capabilities, and supportive ecosystem truly make it an excellent choice for a variety of application types, whether you're building a simple web app, a massive enterprise solution, or anything in between. As we venture further into the development realm, I encourage you to really dive in and practice integrating MongoDB into your projects. Explore its advanced features and see what creative solutions you can come up with. This lesson has equipped you with a solid understanding of why MongoDB is such a robust option for data storage in modern applications. So, roll up your sleeves and start experimenting with MongoDB in your applications. Your journey into full-stack development with FastAPI, React, and MongoDB awaits you. Happy coding! FastAPI is a modern, high-performance web framework for building APIs with Python 3.7 and above based on standard Python type hints. So, what really makes FastAPI stand out in this ever-evolving landscape of web frameworks? Well, let's dig into the benefits and features that make FastAPI such an attractive option for developing those high-performance web APIs. First off, it's all about speed. FastAPI is built to be incredibly fast, like really fast. Thanks to its asynchronous capabilities, it allows us to handle many requests simultaneously, which can lead to a significant performance boost. But it's not just about speed. It's also about how easy it is to use. FastAPI leverages Python type hints, which means we can write cleaner, more robust code. This type hinting not only provides better auto-completion in your IDE, but also generates automatic interactive documentation for our APIs. Pretty neat, right? No need to write separate documentation. FastAPI does that for us. Think about how much time that saves. Now, another fabulous feature is FastAPI's support for data validation. It uses Pydantic under the hood, which ensures that the data types passed into your API endpoints are exactly as expected. Having this built-in validation means fewer bugs and more reliable applications. Oh, and did I mention it's also highly customizable? We can easily integrate it with databases, authentication schemes, and more, making it super versatile. So whether you're building a simple web application or a complex microservice architecture, FastAPI gives you the tools to do it efficiently and effectively. All this makes it a standout choice for developers looking to create high-performance web APIs. So let's get ready to explore FastAPI in action and see firsthand how it can transform the way we build web APIs. So far, we've learned that MongoDB offers a flexible NoSQL database solution that's just perfect for modern applications, allowing us to store unstructured and semi-structured data. We've also explored the farm stack, zooming in on how FastAPI, MongoDB, and React work together, especially when it comes to user management and those dynamic data structures that make our lives easier. Now, key features of MongoDB include its amazing scalability through horizontal sharding and those powerful querying capabilities that really simplify how we access data. As we move forward, we'll dive deeper into using FastAPI to craft efficient web APIs, unpacking its unique features and practical applications. It's going to be a lot of fun, so stay tuned. FastAPI's design focuses on performance, ease of use, and, of course, the developer experience. It's built on top of Starlet for the web components and Pydantic for handling data efficiently. Now, the first thing to note about FastAPI is its speed. Thanks to its asynchronous capabilities, FastAPI can handle thousands of requests per second, making it one of the fastest web frameworks out there. This is especially important for applications that face high traffic demands. So let's look at how we can harness this performance boost. A great way to do this is by creating a simple endpoint that echoes back whatever message you send it. You see, this not only demonstrates how responsive FastAPI is, but it also shows off just how easy it is to get started. So, if you're curious about boosting your web application's performance, FastAPI is definitely the way to go. The figure titled Key Advantages of FastAPI for High-Performance Web APIs presents a grouped bar chart that showcases 5 key advantages across the x-axis: speed, ease of use, data validation, asynchronous support, and community support. On the y-axis, we have an importance scale ranging from 1 to 10. Each bar is annotated with its corresponding numeric value. So, speed hits a solid 9, ease of use stands at 8, data validation also earns a 9, while asynchronous support nails the top score at 10, and community support follows closely at 8. The most striking observation here is that asynchronous support reaches that maximum importance value, a perfect 10, indicating this feature is viewed as the single most critical capability for high-performance APIs. Now, speed and data validation aren't far behind, both sitting at 9, underscoring that both raw throughput and reliable input-output handling are nearly as essential. On the other hand, ease of use and community support, with scores of 8, reveal a strong, yet slightly lower focus on developer ergonomics and ecosystem backing. From these figures and their relative heights, we can conclude that FastAPI's strengths are heavily weighted toward asynchronous operation and robust data validation, while developer productivity and community resources remain key supporting factors. Overall, the bars cluster at the upper end of the scale, suggesting that multiple complementary attributes are considered critical when building high-performance web APIs. Now, let's take a look at how we can implement a simple endpoint using FastAPI that echoes back a message provided in the URL. In this code, we start by importing FastAPI and creating an instance of the application. The @app.get/echo/message decorator defines a GET request endpoint called echo, where message is a path parameter. This path parameter lets us capture a string message directly from the URL. When a request is made to this endpoint, the echo function is invoked asynchronously, which is crucial for performance as it allows handling multiple requests at the same time. Inside the function, we return a JSON response that contains the same message received in the URL. This really shows off FastAPI's powerful ability to create responsive web applications with minimal code. So, when the application is running and you make a GET request to, say, echo/hello, the server sends back a JSON response, message equals hello. This demonstrates the effective communication between the client and server and really showcases the benefits of FastAPI's non-blocking I/O capabilities. In this code, we've defined a simple endpoint that receives a message through the URL parameters. Now, notice the use of the async keyword. This allows our FastAPI application to handle requests asynchronously. So, when you run this application and make a GET request to /echo/hello, you'll receive a JSON response that echoes back the message. It's pretty neat, right? Now, one of the best features of FastAPI is its non-blocking I/O, which means the server can handle multiple requests at the same time while it waits for responses. This capability significantly improves throughput and overall performance, making your application much more efficient. So, remember, using async functions is a powerful way to enhance your web applications. Let's take a moment to discuss how straightforward it is to define data models with FastAPI using PyFastP. PyFastP really makes it easy by leveraging Python's type hints to declare data models. This not only cleans up your code, but, here's the best part, it provides automatic data validation. For instance, if you want to create a user model, you can do that effortlessly. Just, picture it. You define your model, and PyFastP validates the data for you before it even hits your database. So, let's dive into how you typically set this up. You start by importing Pydantic, defining your user class, and then you just specify the fields you need, like name and email. It's that simple. And, well, as your application grows and you add more complexity, having data validation baked right in saves you a ton of headaches down the line. Trust me, you'll appreciate this when it comes to debugging. So let's keep this in mind as we continue exploring FastAPI. It's not just about defining routes, it's about building a solid foundation with your data models. Now let's see how we can define a data model for user management using Pydantic. In our example, we're going to create a user model that specifies the structure of user data expected in API requests. This model includes 3 attributes: username and email, both of which are required fields, and full name, which is optional and defaults to none if not provided. This approach allows FastAPI to automatically validate incoming requests against the defined model, ensuring that only properly structured data is processed. If a request is made with missing or wrongly formatted data, FastAPI will return a clear error message. This not only enhances the user experience, but also reduces the amount of manual validation code you need to write. By leveraging Python's type hints, we achieve a cleaner code base and take advantage of automatic data validation. This not only streamlines the development process, but makes the API more robust and reliable, taking us a step closer to effective user management in our application. Next, we'll implement an endpoint that utilizes this user model to create new users effectively. In this example, we're going to define a user model with 3 attributes. Now, the username and email are required fields, while the full name is optional. What's cool about FastAPI is that it automatically validates incoming requests to ensure they conform to our model structure. So, if a user sends a request with missing or invalid data, FastAPI provides a clear error message, which is super helpful and means you don't have to write a ton of boilerplate code yourself. Now, let's dive into how to implement a post endpoint that creates users using this model. Just imagine, with a few lines of code, you'll have a working endpoint that not only validates, but also handles user data gracefully. All right, let's get started. Now, let's talk about implementing a post endpoint to create users using our previously defined user model. In this code sample, we're defining a new endpoint at the path /users with the @app.post decorator, which, by the way, specifies that this endpoint will handle post requests. The createUser function takes one parameter called user, and this is of type user. What that means is FastAPI will automatically validate the incoming JSON data against the structure of the user model. This ensures that both the username and email fields are present and valid, while it allows full name to be optional. Now, when a post request is made with a JSON body containing the user data, FastAPI processes that and hands off the validated data to our createUser function. The response from this function is a JSON object that includes the user data returned in exactly the same structure it was received. This enhances both clarity and maintainability. This smooth integration of data validation and structured responses minimizes the amount of manual handling and error checking that developers have to worry about. So it really helps you focus on building robust features while keeping expectations clear for how data is managed within your application. When you send a post request with a JSON body that holds the user's data, FastAPI kicks in and validates it against the user model. If everything checks out, it will return that user data in a structured format. Now, this is fantastic because it minimizes the amount of manual validation code that you need to write. This, in turn, enhances maintainability and readability of your code, making it easier to work with over time. It's a win-win situation. One of the coolest features of FastAPI is its automatic generation of interactive API documentation. By default, FastAPI creates this super user-friendly interface that allows you to test your API endpoints using Swagger UI and Redoc. What does this mean for you? Well, it means you can visualize and interact with your API right in your browser. And honestly, that significantly improves your development experience. Just imagine being able to see how everything works without jumping through a ton of hoops. It's pretty neat. So, every time you set up your API with FastAPI, you're not just building an endpoint, you're also getting that slick interface to play around with your API. Right? How awesome is that? Right? How awesome is that? All right. So let's dive into how you can access this feature. After you've got your FastAPI application up and running, head to your web browser. Now type in http://localhost 8000/docs to access the Swagger UI. Or if you prefer, you can go to http://localhost 8000/redoc for the Redoc interface. Once you do that, you'll be greeted with a fully functional interface. It's pretty impressive, right? Here you can view all your available endpoints, submit test requests, and see the responses in real time. It's like having your own playground where you can experiment and see exactly how your API behaves. In fact, FastAPI utilizes Open API standards, which means you can effortlessly integrate your API with a variety of tools and services that support Open API specifications. This really fosters an ecosystem of integration. It allows developers to easily make APIs accessible for use by front-end applications or other services. Isn't that just fantastic? So, whether you're building a small app or something more complex, you'll find that integration with FastAPI helps streamline your development process. It's all about making your work more efficient and effective. So remember, embracing these standards can really open doors for your projects in ways you might not have imagined. As we proceed, let's consider error handling in FastAPI, which is designed to be intuitive and straightforward. You can define custom exception handlers to enhance the user experience, returning appropriate error messages when something goes wrong. This flexibility not only informs users of what happened, but also guides them on how to proceed. For example, when a user hits a snag, instead of just seeing a generic error message, they could receive something specific, like, "Oops, that resource could not be found." This small detail can really improve their interaction. Now, implementing these custom handlers is pretty simple. You just create a function that takes in the request and exception, then returns a response that fits your needs. So whether it's logging the error, sending an email notification, or just showing a friendly message, you have the tools to manage it all effectively. Keep in mind, a good user experience is all about clarity and ease. Embracing error handling in your FastAPI is a fantastic way to build trust with your users. Now, let's explore how we can implement error handling in our FastAPI application using custom exceptions. In this snippet, we're going to define a GET endpoint that retrieves an item based on its ID. The path parameter, item ID, is expected to be an integer. Now, here's the catch. If the provided item ID isn't 42, the application raises an HTTP exception. This triggers a 404 status code along with a clear message stating "Item not found." This method really showcases FastAPI's built-in error management capabilities, making it easy to give informative feedback to clients while keeping your code clean and organized. By defining custom HTTP responses, you significantly enhance the user experience when an error pops up, ensuring that clients truly understand what went wrong. This intuitive error handling mechanism is part of what makes FastAPI such an attractive choice for developers looking to build high-performance APIs with robust and user-friendly interfaces. When someone tries to access an item that doesn't exist, FastAPI raises an HTTP exception. This action sends back a 404 status code alongside a descriptive message. Now, why is this important? Well, it means you can manage errors effectively while providing clear feedback to clients consuming your API. The sensible design of FastAPI keeps your error management clean and straightforward, allowing you to maintain a healthy and responsive API experience. This approach isn't just functional, it's a key part of building robust applications. So remember, having clear error messages helps everyone understand what's going on, making your API so much easier to work with. Let's not forget about authentication and security, which are paramount in any web application. FastAPI comes with built-in support for handling security features, making it easy to include OAuth 2 flows, API key-based authentication, or even JWT tokens. So you have a lot of options here. It helps ensure that only the right people can access your data, which is super important. Forgetting about security could lead to all sorts of issues, right? So let's embrace these features that FastAPI provides and make sure our applications are secure. Suppose you want to implement a simple API key authentication mechanism with FastAPI. Now, the implementation could look something like this. First, you would import the necessary modules, specifically FastAPI and a few other components for handling security. Then you'd set up your FastAPI app. After that, add a dependency that requires an API key. This could be done using a function that checks for the API key in the request header. If the key matches what's expected, great, you can proceed. If not, you return a 401 unauthorized status. It's pretty straightforward, right? And that's essentially it. You've got a simple yet effective API key authentication system in place. You can then expand upon that as needed for your project. So you see, setting this up doesn't have to be complicated at all. Now, let's implement a simple API key authentication mechanism using FastAPI. In this implementation, we'll define a custom security dependency by first importing the necessary modules like depends, HTTP exception, and API key header. The API key header class will help us read the API key from the request headers. Specifically, we're looking for it under the name XAPI key. Next up, we're going to create an asynchronous function called getAPI that takes that extracted API key as input. Inside this function, we'll check if the provided API key matches what we're expecting. Let's say it's expected API key. Now, if that verification fails, we'll raise an HTTP exception, which gives us a 403 forbidden response along with a clear and informative error message, making sure that unauthorized users cannot access our secure data. After that, we'll define the API endpoint, which will require a valid API key in the request. By using the depends function, we ensure that the getAPI function is called to validate the API key before we grant access to that protected data. If everything checks out, the API will respond with a JSON object containing that protected data. This seamless integration of security into our FastAPI application really helps in protecting sensitive information while keeping our code clean and organized. Here, we've defined a custom security dependency using FastAPI's security utilities. Now, when a request is made to secure data, it checks for the presence of a valid API key in the header. If the API key isn't correct, the user receives a 403 forbidden error, which is just a way of saying, "Oops, you can't access this." This elegant integration of security makes it so much easier to build secure applications, allowing developers to focus on creating great features, not worrying about vulnerabilities. So let's appreciate how these built-in tools streamline our development process and keep our data safe. Let's dive a little deeper into asynchronous features, which are super important for achieving efficient performance, especially when we're working with Python. So FastAPI really leans on Python's async and await syntax, allowing developers to write asynchronous code in a way that feels natural. This is particularly advantageous when we're dealing with tasks that might be blocking, such as running database operations or consuming external APIs. It's all about keeping our applications responsive and efficient. So let's keep exploring how we can harness these tools in our projects. Imagine you're tasked with fetching data from two different external web services, and you need to aggregate that into your API response. Now, here's where asynchronous programming comes in handy. It's a game changer. By leveraging this concept, you can initiate both requests at the same time, allowing your application to work more efficiently. So instead of waiting for one response before starting the other, you're essentially multitasking. This means you can handle more requests without blocking your main thread. Pretty neat, right? As we dive deeper, you'll see just how powerful this can be for optimizing performance in your applications. Now, let's take a look at how to asynchronously fetch data from multiple external services and aggregate that data into a single API response. We begin by defining two asynchronous functions, fetch data from service A and fetch data from service B. These functions utilize the HTTPX library to perform non-blocking HTTP GET requests to their respective service endpoints. By using async with httpx.async client, we ensure that our requests are handled efficiently, allowing other tasks to run concurrently while we wait for the responses. Now, next up, we create an API endpoint called getAggregatedData. This is where the magic happens. We execute both fetching functions simultaneously by employing asyncio.gather. This nifty function allows us to launch both tasks at once, significantly reducing waiting time and boosting the overall responsiveness of our API. Once we receive both responses, we'll return them in a structured format that encapsulates the results from both services. This approach exemplifies FastAPI's asynchronous capabilities, enabling developers to build high-performance applications that can handle multiple requests quickly and efficiently, making it perfect for modern web development scenarios. In this example, we're going to dive into HTTPX, which is an asynchronous HTTP client, and it's pretty cool because it allows us to fetch data from two different services. And we can do this concurrently. Now, what's really neat here is that we're using the asynchrono.gather function. This function enables us to run both fetching operations at the same time, which means we're significantly shortening the total response time for clients of your API. It works by leveraging the event loop efficiently, ensuring that FastAPI can handle a multitude of requests without any delay. So when you set this up correctly, you'll notice a smoother experience, both for you as a developer and for your users. Imagine handling multiple requests seamlessly. Pretty nifty, right? With this method, you're really maximizing the capability of your application, making it robust and responsive. So let's get our hands dirty and start implementing some code with HTTPX and Asynchrono. Let's also dive into dependency injection, which is a super powerful feature of FastAPI that really enables you to create modular and testable code. So what are dependencies? Well, they can be anything from your database connections to configuration settings, and the beauty of it is that they can be automatically injected into your path operations or even other dependencies. This makes your code cleaner and more maintainable. Imagine not having to hard code connections every time you need them. That's a game changer, right? So, as we explore this feature, keep in mind that dependency injection helps you manage your application in a more structured way. It simplifies testing too, allowing you to mock dependencies without much hassle. Isn't that cool? All right, let's get into how to implement this in your FastAPI projects. For instance, if you want to connect to a MongoDB database, you can set up a dependency that provides the database connection, making it accessible to any endpoint that needs it. This means whether you're fetching data or storing it, every part of your application can easily tap into that connection without reinventing the wheel every time. Just think about it. You're simplifying your code, keeping it clean, and ensuring that everything has access to that crucial database resource. So when configuring your application, this approach not only boosts efficiency, but also enhances maintainability. So remember, every endpoint can benefit from that shared connection, fostering a more interconnected and robust application architecture. Next, we'll write some code to connect our FastAPI application with a MongoDB database. First, we need to import the Mongo client from the PyMongo library, along with the depends function from FastAPI. After that, we'll create an instance of Mongo client. This will establish a connection to our MongoDB server, which is running locally on the default port. Pretty straightforward, right? Now, to define the database we'll use, we access it through our client instance and assign it to the variable db. Next, to make this database accessible to our endpoints, we'll create a function called getDB. This function will simply return our DB object. Now, let's look at the read users endpoint. With FastAPI's handy dependency injection, this endpoint will utilize our getDB function to interact with the database. So, when a GET request is sent to /users, it will fetch all user documents from the users collection and return them as a list. This structure not only promotes code reusability, but also keeps our application modular, allowing for easy adjustments and scalability for future updates. In this case, the getDB function acts as a dependency that exposes the database connection to the read users endpoint. Now, the beauty of this setup lies in its simplicity and reusability. You only need to define the database connection once, and you can use it across multiple endpoints while keeping your code clean and organized. It's like having a central hub for your database access, making everything feel streamlined, right? So, whenever your read users function needs to interact with the database, it just taps into this single connection. And that means you can manage your connections more easily, avoid redundancy, and, let's be honest, keep your code looking sharp. So, whether you're reading data or making changes, having that neat, reusable connection in place is a game changer. This way, you're setting yourself up for success with cleaner, more maintainable code. And isn't that what we all strive for? As we look ahead, it's essential to consider the community and ecosystem surrounding FastAPI. You see, the rapid adoption of FastAPI has really sparked a vibrant community that's contributing tons of resources, projects, and tools. I mean, from middleware libraries to authentication frameworks, the variety is just expanding. This growing ecosystem is all about making your development process easier and more efficient. So, if you're diving into FastAPI, keep an eye on these resources. They can be incredibly helpful as you build your applications.
Moreover, the framework's creators are actively engaging with the community on GitHub, taking the time to address issues, evolve the software, and really listen to user feedback. So, as a developer, you have the opportunity to contribute too. You can report bugs, suggest cool new features, or even lend a hand by writing documentation. This sense of community is vital. It ensures that FastAPI will keep growing and adapting to meet the ever-evolving needs of developers, which is pretty fantastic, right?
In conclusion, FastAPI really shines as a high-performance, user-friendly web framework specifically designed for building APIs. With its focus on speed, type safety, automatic documentation, and robust asynchronous capabilities, it's perfectly suited for the demands of modern web development. As you embark on creating your applications, remember to leverage FastAPI's powerful features to craft efficient APIs that are not only easy to maintain, but also scalable. It's like having the best toolkit in your developer's toolbox.
Now that we've covered the essential aspects of FastAPI, I really encourage you to put this knowledge into action. So why not start building your own APIs with FastAPI? Dive into its extensive documentation. There's so much to explore. Experiment with its features and see what you can create. The journey into high-performance API development is exciting, and FastAPI is a fantastic companion for that adventure. So happy coding, and remember, the possibilities are endless. You've got this. FastAPI is a modern and efficient web framework for building APIs with Python. It's designed for developers who want to create web applications quickly and functionally, all without sacrificing performance. Today, we'll dive into some of the compelling features of FastAPI that really make it a top choice for API development. So far, we've learned that FastAPI is a high-performance framework that puts a strong emphasis on speed, ease of use, and asynchronous capabilities. We've also explored its key features, like automatic data validation using Pydantic, which really simplifies data handling. Oh, and don't forget about those interactive API documentation tools. It's like having a built-in manual. Now we've touched on the significance of dependency injection, which helps in managing components efficiently, and the crucial security mechanisms like API key authentication that ensure your APIs are safe and secure. As we move forward, let's continue to leverage FastAPI's capabilities for efficient API development and tap into the community resources that will enhance our learning experience even further. The displayed figure, titled Key Features of FastAPI, is a vertical bar chart that quantifies 5 principal attributes of the framework: speed, automatic validation, asynchronous capabilities, dependency injection, and documentation. The chart clearly shows the numeric values above each column, making it easy to grasp at a glance that documentation tops the chart with a score of 95, followed closely by speed at 90. Asynchronous capabilities rank at 85, while automatic validation is at 80. Now, you might notice that dependency injection, though still solid, comes in last at 75. So what does all this tell us? Well, it emphasizes that both documentation and runtime performance are standout features of FastAPI. This framework shines in providing excellent asynchronous support and robust automatic validation as well. While dependency injection is certainly commendable, it just doesn't quite reach the same level of emphasis compared to the others. All in all, this chart illustrates that FastAPI consistently maintains a high standard across essential API concerns, with a particular highlight on documentation and speed, important takeaways for developers who prioritize discoverability and performance in API design. Now let's take a look at how we can implement a simple user creation endpoint using FastAPI and Pydantic. We start by importing the necessary components, specifically FastAPI for creating our web application and base model from Pydantic, which helps us define our data model. So first things first, we create an instance of FastAPI. This instance serves as our application. Next up, we define a user class that inherits from base model. This class is crucial because it specifies the structure of the user data we're expecting. It includes an integer field for ID, a string field for name, and another string field for email. This model plays a key role, ensuring that any incoming data for user creation strictly adheres to this specified format. Now moving on, we set up an endpoint for creating users by defining a function called createUser. This function takes a parameter of type user, which allows FastAPI to automatically validate the request's body against our user model. If the incoming data is valid, the function returns a dictionary containing the user's details. However, if validation fails, FastAPI steps in to handle the error and respond accordingly, indicating what went wrong. This process beautifully highlights how FastAPI simplifies data validation and ensures data integrity in API development. Now let's dive into implementing FastAPI's interactive API documentation feature using the provided code. First up, we need to import FastAPI and Pydantic's base model, which are crucial for data validation. With our FastAPI instance ready to go, let's define a user class that extends from base model. Here, we'll list the attributes our user objects will have: an integer ID, a string name, and another string for email. Moving on, we'll set up a post endpoint at users and create an asynchronous function called createUser, which takes a user object as input. This setup allows FastAPI to automatically validate incoming requests, making sure they have all the necessary fields and that the data types match our model. If everything checks out, this function will return a JSON response containing the user's ID, name, and email. It's a neat and efficient way to build robust APIs by automating validation and enhancing user interaction. Plus, it gives developers the ability to test requests right through the auto-generated documentation available at docs. So with this straightforward approach, we can see how FastAPI simplifies user input handling while generating useful documentation that's great for both development and testing.
Now, let's see how we can implement asynchronous data fetching in FastAPI using Python's async and await keywords. In the example we're working with, we'd start by importing the necessary modules, then create an instance of our FastAPI application. So, let's dive in. We define an asynchronous function called fetchUserData, which basically simulates fetching user data from a database. To illustrate the concept of I/O-bound operations, we utilize await asynchronous.sleep2. This creates a non-blocking delay, mimicking the time it typically takes for a database call to complete. Next, we define an asynchronous endpoint, readUser, which accepts a user ID as a path parameter. Within this endpoint, we call our fetchUserData function, allowing FastAPI to manage other incoming requests without having to wait idly while the user data gets fetched. Now, once our data is ready, it's returned immediately, showcasing FastAPI's efficiency in handling several requests at once. By embracing asynchronous programming, our application remains responsive, which is, a crucial aspect for developing high-performance web applications.
Now let's see how we can implement dependency injection in our FastAPI application to efficiently handle current user information. We start by importing the necessary components from FastAPI, and then we instantiate our application using FastAPI. Next, we define a function named getCurrentUser, which serves as a dependency that returns the current user's data. For demonstration purposes, this function simply returns a placeholder dictionary containing a user ID and name. This modularity is really beneficial, as it allows us to keep our user fetching logic separate from our endpoints, which ultimately improves code reusability. Now, we'll create a route for the user's me endpoint by defining an asynchronous function called readCurrentUser. Here, we leverage FastAPI's depends feature to declare the getCurrentUser function as a dependency. When this endpoint is accessed, FastAPI automatically invokes getCurrentUser and passes its return value to the currentUser parameter in the readCurrentUser function. This streamlined approach not only enhances the maintainability of our code, but also simplifies testing and modification of user-related logic independently, which, I must say, is a significant advantage of using dependency injection. Now let's implement API key authentication, which is a crucial security feature in FastAPI. In our code, we start by initializing a FastAPI application, and here's the important part: we're going to define a secret API key that will be used for authentication. The API key auth function is created to validate the API key provided by the user against our predefined secret. Now, if the key doesn't match, the function raises an HTTP exception with a 401 status code, which simply means that the request is unauthorized. Next, we set up an endpoint called secureData/. This endpoint uses FastAPI's depends to incorporate the API key auth function as a dependency, ensuring that any request to this endpoint must include a valid API key. If the correct API key is provided, users will receive a JSON response containing a message indicating that they've accessed protected data. It's a straightforward approach for securing your API, and believe me, it's essential for applications that handle sensitive information, as it prevents unauthorized access and significantly enhances the overall security of your API. This foundational security practice is vital for maintaining user trust and application integrity. Now let's implement the integration of FastAPI with a SQLite database using SQL Alchemy. First up, we need to install the required dependencies for SQL Alchemy and SQLite. This step is essential as it enables us to connect to and interact with our SQLite database. Next, we'll define the database connection URL. Then, we create an engine that interacts with the database. The session local instance is really useful here, as it allows us to manage our database sessions, which makes handling transactions with the database a breeze. Now, let's declare a base class for our database models using declarative base. This sets us up nicely for the next part. In our implementation, we're going to define a user class that represents the user's table in our database. This class specifies its structure, including fields for ID, name, and email, complete with their respective data types and attributes, such as setting them to be indexed or unique. Once the model is set up, creating the table in the database is straightforward. We simply call base metadata, create all bind equals engine. Now, with our FastAPI application instance created, let's define an asynchronous endpoint that allows us to add new users. The createUser function will accept user details, initialize a new user object, and then commit that to the database. This efficient approach to database interaction showcases FastAPI's seamless integration with SQL Alchemy, giving you the tools to build robust web applications. As we wrap up our discussion today, it's vital to highlight the incredible community and resources available for FastAPI developers. FastAPI boasts a vibrant community. Seriously, it's like a goldmine of information. With extensive documentation, tutorials, and forums, you'll find plenty of places to seek help or get inspired. Now, let's talk about the official FastAPI documentation. It's a fantastic resource. It covers everything from installation all the way to advanced usage. Here's a quick example of how to navigate it. Just visit https://fastapi.com and you'll see sections neatly categorized into tutorial, deployment, and advanced. Each section is meticulously structured, offering code snippets, examples, and explainers. And guess what? The community actively contributes to this documentation, enriching the learning experience and making it super easy for newcomers to dive into the FastAPI world. By leveraging FastAPI's numerous features, you can build robust, high-performance APIs that cater not only to your needs, but also to those of your users. Its ease of use, combined with powerful capabilities, makes it an excellent choice for any developer venturing into API development with Python. And remember, it's crucial to continuously explore community resources and experiment with your own projects to really solidify your understanding. So let's summarize what we've covered. We delved into the key features of FastAPI, including automatic data validation, interactive documentation, asynchronous capabilities, dependency injection, security mechanisms, SQL Alchemy integration, and those invaluable community resources. By harnessing these features, you'll be well on your way to becoming proficient in building scalable and efficient APIs. So keep coding, and until next time, happy coding. MongoDB is a free, fast, and scalable database that allows us to work with data in a flexible, JSON-like format. Its simple syntax makes it accessible, and it is particularly well suited for applications requiring high performance and high availability. So far, we've learned that FastAPI is an exceptional framework for building APIs with Python, capitalizing on features like automatic data validation and interactive documentation. Now, we will take a leap into the world of databases and specifically focus on MongoDB. In this session, we'll explore its core features, how to set it up, integrate it with FastAPI, and execute various operations such as creating, reading, updating, and deleting data, all while keeping our code tidy and efficient. MongoDB is a NoSQL database, which means it does not store data in the traditional tabular format used by relational databases. Instead, it utilizes a document-oriented format, storing data in BSON, which is essentially a binary representation of JSON. This design allows for rapid data retrieval and flexibility in data modeling. Let's set up a simple MongoDB instance and see how we can interact with it. Next, we will write the command to start the MongoDB server, which is essential for running our database. We use the command mongo in the terminal, which stands for MongoDB daemon, to initiate the server and allow our application to interact with the database. This command starts the MongoDB service, enabling the storage and retrieval of data. Once the MongoDB server is up and running, we can interact with it using the MongoDB shell. By opening a new terminal window and entering the Mongo command, we can access an interactive shell to execute database commands directly. This is particularly useful for testing queries and viewing the data we manage within our collections. Always ensure that MongoDB is running before attempting to connect your FastAPI application, as the lack of a running service will lead to connection errors. Understanding this setup is crucial as we move forward to connect FastAPI with MongoDB and perform various data operations effectively. Now let's see how we can create a simple FastAPI application that connects to MongoDB. We begin by importing the necessary libraries, including FastAPI for building our REST-TFL API, Mongo client from PyMongo for MongoDB interactions, and base model from Pydantic for data validation. Here, we define a user class that outlines the structure of our user data, requiring a name and email as string fields. Next, we initialize our FastAPI app instance, which will be the core of our application. We then create a Mongo client instance to connect to our local MongoDB server, specifying the connection string. Using the getDatabase method, we specify the database we will use, in this case, MyDatabase, and create a collection named users that will store user data. This setup allows us to effectively store and retrieve user information in our MongoDB collection as we proceed to implement our API endpoints for CRUD operations. The bar chart titled Key Features of MongoDB maps 5 features on the x-axis: CRUD operations, flexibility, scalability, performance, and community support, against numeric performance ratings on the y-axis. From the annotated values, flexibility is highest at 95, indicating that schema adaptability and document-based modeling are MongoDB's strongest points. CRUD operations and performance are tied at 90, showing that core data manipulation and runtime characteristics are both highly rated. Scalability sits at 85, reflecting robust horizontal scaling capabilities that are slightly lower than raw performance and flexibility. And community support is lowest at 80, suggesting relatively less ecosystem or community-driven resource strength compared to the other measured aspects. The pattern is a modest decline from flexibility through community support rather than abrupt differences, which highlights MongoDB as a balanced platform with pronounced advantages in flexible data modeling and operational performance. Practically, this means MongoDB is especially well suited when you need schema flexibility and high-speed operations, while you may want a plan for additional tooling or community resources when relying on broader ecosystem support. Now that we have our FastAPI app connected to MongoDB, let's implement an endpoint for creating user records. We will define a post endpoint at users that expects a user object included in the request body. When a client sends new user data, the createUser function is triggered asynchronously, allowing for efficient handling of requests. Inside this function, the user object is transformed into a dictionary using user.dict, which makes it easier to work with the data. Next, we will insert this dictionary directly into our users collection using the InsertOne method, which adds a new document to the collection. Once the insertion is successful, we can send a response back to the client confirming that the user was created, including a success message along with the user data. To improve our application, we should also consider adding error handling. Wrapping the database insertion logic in a try-except block can help us catch any potential exceptions and return more informative error messages, ensuring a smoother user experience. Now let's see how we can implement a GET endpoint that retrieves user data from our MongoDB collection based on an email address. This endpoint is defined using the FastAPI decorator at app-get and specifies a dynamic path that includes an email parameter. The function readUser is asynchronous, which helps in handling requests efficiently without blocking the server. Inside the function, we utilize the findOne method from the user's collection to look for a document where the email field matches the provided parameter. If a user document is found, we simply return it, allowing the client to see the user's information. However, if no match is found, we return a JSON response that includes an error message, notifying the client that the user was not located. This way, our endpoint not only facilitates the retrieval of user details, but also employs clear error handling, improving the user experience by informing them when a particular email does not correspond to any existing record. This illustrates the flexibility of MongoDB in terms of data retrieval based on various fields, enhancing the overall capability of our application. Next, we will write the following code to create a PUT endpoint for updating user information. This endpoint is essential for scenarios where users need to modify their details, such as changing their email or name. The endpoint is defined with the path parameter for the user's email, which acts as a unique identifier. Within the function, we utilize MongoDB's findOneAndUpdate method, which allows us to search for a document that matches the provided email and modify it in a single operation. We structure the update using the set operator, passing in the new user data converted into a dictionary format. This integration ensures that only the specified fields are altered, making the operation efficient. After the attempted update, we check if an updated user document was returned. If the user exists and the update is successful, we respond with a success message along with the updated user data. Conversely, if no document matches the given email, we send an error message indicating that the user was not found. This structured feedback is crucial for client-side handling, creating a smooth user experience when managing user data. Now let's implement the delete endpoint that allows us to remove a user from our collection. In the code, we define an asynchronous function called deleteUser, which takes an email parameter as part of the URL path. This endpoint listens for delete requests at the /users/email path. Inside the function, we utilize the deleteOne method from the MongoDB collection to attempt to remove a user document that matches the specified email. If the deletion is successful, indicated by a deleted count greater than 0, we respond with a success message confirming that the user was deleted successfully. On the other hand, if no user is found with the provided email, we return a structured error message stating user not found. This approach allows us to manage user deletions effectively while providing clear feedback, which is essential for the client to understand the outcome of their request. By handling different outcomes, we enhance the endpoint's user experience and reliability in our CRUD operations. Now let's implement a robust error handling mechanism for our delete user endpoint. Here, we use FastAPI's built-in HTTP exception to manage potential issues that could arise during database operations. This is particularly important as it allows us to respond to clients with meaningful status codes and details when errors occur. In the deleteUser function, we first wrap our deletion logic in a try-except block to catch any exceptions. Within the try block, we call deleteOne on our MongoDB collection to attempt deleting a user document based on their email. If no document is deleted, indicating that the user was not found, we raise an HTTP exception with a 404 status code and a descriptive detail message. This approach ensures that if an unexpected error arises, we respond with a 500 status code in the error message, allowing us to diagnose issues easily while keeping the client informed. By encapsulating our error responses in a structured format, we enhance the client-side handling of errors, fostering a clearer and more reliable user experience. Now let's see how we can implement indexing to enhance the performance of our MongoDB queries. By creating an index on the email field in our users collection, we can significantly speed up data retrieval, especially when dealing with large datasets. This is crucial for applications that require quick access to user data, as it reduces the time it takes for the database to search through potentially thousands of documents. To create the index, we use the createIndex method provided by the MongoDB library. The syntax is straightforward. We pass in the field name, in this case, email. Once the index is created, MongoDB will maintain it automatically, ensuring that queries filtering or sorting by the email field execute faster. This practice not only improves performance, but also enhances the overall user experience by minimizing response times when searching for users. As you continue developing your application, remember that indexing is a vital strategy to optimize performance, making your interactions with the database much more efficient. So far, we've covered the core features of MongoDB, including how to set it up, perform CRUD operations using FastAPI, and improve our application's robustness through error handling and indexing. As you continue your journey with MongoDB, remember to explore its rich set of features and capabilities that can help you build powerful, scalable applications. Whether it's implementing geospatial queries, using the aggregation framework, or organizing your data with the appropriate data model, MongoDB offers a wide array of tools to meet your needs. In the next sessions, we'll take what we've learned today and integrate it with React for a full-stack application, bridging the gap between your front-end and back-end seamlessly. Get ready to dive into the exciting world of full-stack development. Understanding REST APIs is essential for modern web development, especially when building full-stack applications. Today, we will explore what REST APIs are, how they work, and how to interact with them effectively. By the end of this session, you'll not only understand the concept of REST APIs, but also how to utilize them with practical code examples. So far, we learned that MongoDB is a flexible NoSQL database that supports rapid data retrieval and scalability, making it particularly suitable for applications requiring high performance. We explored how to set up MongoDB and integrate it with FastAPI to perform CRUD operations, including creating, reading, updating, and deleting user data. Additionally, we discussed error handling and best practices, such as implementing indexing for improved performance and security measures for production applications. As we move forward, we will integrate what we've learned with React to create a complete full-stack application. REST, or Representational State Transfer, is an architectural style that outlines how web services should be designed and interact with clients. In a nutshell, a REST API allows different software applications to communicate over the internet, relying on standard HTTP methods like GET, POST, PUT, and DELETE. These methods provide a familiar way to perform CRUD operations, engaging with resources represented by URLs. The figure titled HTTP Methods Usage in REST APIs presents a pie chart that breaks down usage frequency across the four primary HTTP methods: GET 40%, POST 30%, PUT 20%, and DELETE 10%. The clear pattern is a red dominant distribution where GET accounts for the largest share, followed by POST for creation, PUT for updates, and DELETE as the least frequent operation. From these proportions, we can draw practical conclusions. Most traffic to REST endpoints tends to be read operations, so optimizing read paths, caching responses, scaling read replicas, and using CDNs where appropriate will yield the biggest performance gains. The sizable POST slice indicates significant create activity, so attention must be paid to validation, idempotency safeguards when needed, and efficient write handling. The smaller but non-negligible PUT portion highlights the need to support update semantics and to ensure proper handling of idempotent operations, while the relatively small delete slice suggests delete operations are rarer but still critical. These should be handled with careful authorization, auditing, and possibly soft deletes to avoid accidental data loss. Overall, the chart emphasizes designing APIs with read-heavy performance optimizations, robust create-update safeguards, and strict controls around destructive actions. Now let's take a look at implementing a GET request to retrieve user data from our API. First, we start by importing the requests library, which allows us to send HTTP requests easily. We then specify the URL of the API endpoint we want to access. In this case, it's the endpoint for fetching users. A GET request is sent to this URL, and the server responds with a status code and the user data. We must check if the response status code equals 200, which indicates a successful request. If successful, we convert the response into JSON format, allowing us to easily work with the user information. Finally, we print the users to the console to see the data retrieved from the API. This straightforward approach demonstrates how simple it is to fetch data using the GET method in a REST API, paving the way for integrating this functionality within your FastAPI application for dynamic user retrieval. Now let's see how we can implement the POST method in our application. In the following code, we begin by importing the requests library, which is essential for making HTTP requests in Python. Next, we create a dictionary named newUser, which holds the information for the new user we want to add, specifically their name and email. Following that, we make a POST request to the specified URL of our API endpoint, which in this case is used to add new users. We send the new user data as JSON in the body of the request. Once the request is made, we need to handle the response from the server. By checking the status code of the response, we can determine the result of our request. A status code of 201 indicates that the user was created successfully, allowing us to print a confirmation message. Conversely, if the status code is anything other than 201, we print a failure message, helping us identify issues in the user creation process. This illustrates the simplicity and power of using REST APIs to manage data within our applications effectively. Now let's examine the code that performs a PUT request to update an existing user resource. We begin by importing the requests library, which enables us to make HTTP requests in Python. Next, we define a dictionary named updatedUser containing updated information, in this case, the user's name and new email address. Now let's see how we can implement the PUT request using the requestSplit method. This method is invoked with the URL endpoint for the user, which includes the user ID, in this case, https://API example.com/user/1, and we pass our updated user data as a JSON object by specifying the JSON parameter. This effectively updates the user's information on the server. Following the PUT request, we check the response status code to determine the outcome of our request. A status code of 200 indicates that the update was successful, allowing us to print a confirmation message. If any issues arise during the update, we handle it gracefully by printing a failure message. This is a crucial aspect of working with REST-TFL APIs, where proper response checking ensures a robust interaction with the server. Now let's implement the delete method, which is crucial for removing user resources from our server. In the code, we begin by importing the requests library, a popular tool for making HTTP requests in Python. The core operation here is a delete request directed at the endpoint of the user we want to delete, identified by the ID 1. This URL structure follows the REST-TFL convention, where each user can be accessed using their unique identifier. Upon sending the delete request, we examine the server's response through its status code. A status code of 204 means that the request was successful, and the user has been deleted without any additional content to return. This conveys to the client that the operation was completed effectively. Alternatively, if the deletion fails, we handle it gracefully by checking for any other status codes and informing the user accordingly. This method exemplifies robust API interaction, ensuring users can manage their accounts seamlessly while following REST principles. Understanding these methods is fundamental, yet it's also essential to be aware of the structure of a REST-TFL API. Typically, a REST API is designed around resources, in our case, users. Each resource can be accessed through its corresponding URL, which leads to a logical mapping of methods and resource identifiers, URIs. For example, let's look at a hypothetical API structure. GetUsers retrieves all users. PostUsers creates a new user. Get/user/OD retrieves a specific user by ID. PUT/user/OD updates a specific user by ID. Delete/user/OD deletes a specific user by ID. This organization clearly defines how to interact with our resources and what to expect in return. You can think of this as a blueprint for your application's architecture. In addition to understanding the endpoints, it's important to acknowledge the significance of status codes in API responses. Status codes communicate the result of your requests. Here's a quick overview of some common status codes you might encounter. 200 OK, the request was successful, and the server returned the requested data. 201 created, the request was successful, and a new resource was created. 204 no content, the request was successful, but there is no content to return, often used for delete requests. 400 bad request, the server could not understand the request due to invalid syntax. 404 not found, the requested resource could not be found on the server. 500 internal server error, the server encountered a situation it doesn't know how to handle. Understanding these status codes is like having a guidebook for troubleshooting. It allows developers to handle errors gracefully and inform the users appropriately. Now let's implement a simple token-based authentication system that allows users to access protected resources in our API. First, we need to set up headers for our HTTP request, specifically adding the authorization field with a bearer token. This token, which serves as a key denoting the user's identity and permissions, must be included in every request to ensure that the user is authenticated. Next, we will make a GET request to the API endpoint that retrieves user data. By using the requestGet method, we pass in the URL of the resource we want to access, along with our previously defined headers. This method sends the request to the server, which will check if the provided token is valid and if the user has the necessary permissions to access the requested data. After we receive the response, we can evaluate the status code returned by the server. A status code of 200 indicates that the request was successful and the user is authorized to view the data. Conversely, if the status code indicates unauthorized access, we must handle this gracefully to inform the user that their token may be invalid or expired. This approach not only secures our API, but also ensures that sensitive information is protected. Let's take a moment to talk about versioning your API. As your project evolves, the API may also need modifications and improvements. By versioning your API, you can ensure that older applications continue to work even as newer updates are introduced. A common practice is to include the version number in the API URL. For example, https://API example.com/v1/users. https://API example.com/v2/users. This way, if any breaking changes are introduced in version 2, the clients using version 1 will remain unaffected. Thoughtful versioning enhances the longevity and stability of your application, allowing developers to maintain backward compatibility. To summarize what we've covered, we've delved into the essentials of REST APIs, how to utilize HTTP methods for CRUD operations, explore the structure, and understand the importance of status codes, authentication, and versioning. By grasping these crucial concepts, you are well on your way to mastering the art of API development, a vital skill in today's web development landscape. As we move forward, we will take what we've learned today about REST APIs and integrate it with React to seamlessly connect our front-end user interfaces with back-end services. This integration will enable us to create highly interactive and robust applications that can cater to users effectively. Thank you for joining me in this exploration of REST APIs. I hope you feel equipped with the knowledge you need to start building and integrating your APIs into your full-stack applications. Stay excited, keep coding, and let's dive deeper into the world of full-stack development. FastAPI is a modern web framework designed for building APIs quickly and efficiently. It leverages Python's asynchronous capabilities and utilizes type hints, making it an appealing choice for developers looking to create high-performance applications. So far, we covered the fundamentals of REST APIs, understanding how they operate and the standard methods used for communication. We also explored API structure, status codes, and authentication mechanisms. Now, we'll dive deep into FastAPI, uncovering its key features and how they can enhance the development of robust APIs. Now let's implement a basic FastAPI application to illustrate its speed and efficiency when handling requests. Here, we begin by importing the necessary FastAPI module and the time module, which we will use to simulate different response times. We create an instance of the FastAPI class that serves as the main application. Next, we define two endpoints. The first one is the fast endpoint, which responds quickly with a JSON message indicating that it is a fast endpoint. This showcases FastAPI's capability to handle quick responses effectively. In contrast, the second endpoint, slow, simulates a slower response by using time, sleep 2, causing a 2-second delay before sending back a message stating that it is a slow endpoint. This example is particularly useful for demonstrating how FastAPI manages multiple requests concurrently, even when one of the endpoints introduces a delay. By testing these endpoints, you'll observe that while one endpoint takes longer to respond, FastAPI's asynchronous design allows the application to remain responsive and effectively manage incoming requests. This underlines FastAPI's strength as a high-performance web framework. The displayed bar chart titled Key Features of FastAPI maps a set of core features on the x-axis: speed, dynamic validation, dependency injection, automatic documentation, CORS support, background tasks, security features, against an effectiveness 0-100 y-axis with values clearly annotated above each bar. From the numeric labels and bar heights, we can read a clear ranking. Automatic documentation is highest at 95, followed by speed at 90, dynamic validation at 85, dependency injection and security features both at 80, background tasks at 75, and CORS support lowest at 70. The chart shows a pronounced emphasis on documentation and performance, top two values, a closely grouped mid-tier 80-85, indicating consistently strong capabilities in validation, dependency handling, and security, and comparatively lower but still meaningful scores for background processing and CORS. The uniform y-axis scale, 0-100, and the grid lines make these relative differences explicit. Documentation and speed stand out as primary selling points. The middle cluster reflects reliable core services, and the lower values highlight areas that may require more configuration or attention depending on project needs. Now let's see how we can implement dynamic request validation using a Pydantic model in FastAPI. In this example, we first import the base model class from the Pydantic library, which allows us to define data models with validation rules. We then create a user model that specifies the required fields, username, email, and age, each annotated with their expected data types. Following this, we define a post endpoint at users that receives data in the form of the user model. FastAPI automatically validates the incoming request body against the structure defined in the user model. If a user sends a request with valid data, FastAPI deserializes it into a user object and passes it to the createUser function. This function, in turn, returns a JSON response containing the user's details. However, if the data does not match the expected format or any of the requirements are not met, such as missing fields or incorrect data types, FastAPI responds with a clear error message, informing the user what went wrong. This automatic validation not only streamlines the API development process, but also improves the overall user experience by providing immediate feedback on their requests. Now let's see how we can implement a simple authentication mechanism using FastAPI's dependency injection feature. The verifyUser function is designed to check the validity of a provided token. If the token does not match the expected value of valid token, it raises an HTTP exception, specifically returning a 401 unauthorized status. This centralized function allows us to handle user authentication logic in a single place. Next, we will write the secureData endpoint, which incorporates the depends method to include the verifyUser function as a dependency. This means that every time the secureData endpoint is accessed, the token validation happens automatically, effectively decoupling the authentication logic from the endpoint itself. The advantage of this approach is that it enhances code readability and maintainability, especially in larger applications where multiple endpoints may require the same authentication logic. Finally, if the token is valid, the endpoint proceeds to return a JSON response containing secured data. This clean implementation showcases how dependency injection fosters code reuse and minimizes redundancy in FastAPI applications. Now let's implement a background task in our FastAPI application to handle an email notification. In this example, we define a function called sendEmail, which simulates the process of sending an email by printing a message to the console. This is a simplification, but serves to illustrate the concept of background tasks. Next, we create a post endpoint at sendNotification. This endpoint takes an email as input and also leverages FastAPI's background tasks feature. When a user sends a request to this endpoint, FastAPI immediately queues the sendEmail function as a background task without blocking the response. This means the API can respond to the user right away, telling them that their notification has been scheduled, while the actual email sending operation runs in the background. This approach significantly enhances the user experience by ensuring the application remains responsive, even when performing time-consuming tasks like sending emails. By using background tasks, we can efficiently manage operations that don't need to be performed immediately while maintaining quick feedback for users. Now let's implement CORS support in our FastAPI application to handle cross-origin requests effectively. We begin by importing CORS middleware from FastAPI middleware CORS, which is essential for managing CORS in our app. Next, we add the middleware to our FastAPI instance using the addMiddleware method. Here, we specify allow_origins equals *, allowing requests from any origin. While this is convenient during development, it is crucial to limit the origins in production environments to enhance security. We also enable credentials by setting allow_credentials equals true, which allows cookies and authorization headers to be sent. Additionally, we configure allow methods equals asterisk and allow headers equals asterisk to permit any HTTP method and header, respectively. Finally, we define a simple root endpoint at the path /, which returns a basic message. This setup not only simplifies Core's configuration, but also enhances our API's accessibility, making it easier for web applications hosted on different domains to interact with our FastAPI backend seamlessly. Now let's implement JWT authentication in our FastAPI application to secure our endpoints. We start by importing the necessary modules, including OAuth to password bearer and OAuth to password request form from FastAPI's security package. The OAuth to password bearer instance is created with a token URL, which will be used to retrieve the token when a user logs in. Next, we define a token endpoint that allows users to log in. This endpoint accepts a username and password via the OAuth to password request form. Within the login function, we validate these credentials. In this example, we check if the username and password match predefined values, user and password. If the credentials are valid, we generate a JWT token encoded with the username as the subject. This token is returned in the response as an access token. Now let's see how we can protect another endpoint, users.me, which allows users to access their data. This endpoint is secured using the depends method with the OAuth2 scheme, ensuring that only users with a valid token can access it. The token is extracted from the request and returned in the response, demonstrating a simple yet effective way to safeguard sensitive data in our application. Throughout our discussion of FastAPI, we've covered a range of features that distinguish it as a leading choice for API development. We explored its high performance, dynamic request validation, and efficient dependency injection. Additionally, we admired its background task capabilities, Core's handling, and built-in security features. In summary, FastAPI is not just a framework. It's a comprehensive solution that simplifies API development while maximizing performance and security. Its use of modern Python features ensures that developers can work efficiently and effectively, focusing on delivering stellar applications. As you continue your full-stack journey with FastAPI, React, and MongoDB, embrace these features to build APIs that stand out in functionality and performance. MongoDB is a free, fast, and scalable database that utilizes a JSON format, making it incredibly user-friendly and efficient for developers. In this video, we will explore the myriad advantages of using MongoDB, diving deep into its features and functionalities while showcasing practical code examples along the way. So far, we have learned about FastAPI, a powerful framework for developing APIs with Python, and now we will discuss how MongoDB complements and enhances full-stack applications built with FastAPI. Now let's take a look at how we can connect to a MongoDB database and insert user profiles with varying attributes. We start by importing the Mongo client from the PyMongo library, which allows us to interact with our MongoDB instance. To establish the connection, we create a client that points to our MongoDB server running locally on port 27017. We then specify the database we want to use, in this case, user database, and define a collection named users, where we will store our user information. Next, we'll create two user profile dictionaries that contain different sets of attributes. The first user has a username, email, and age, while the second user includes an additional attribute for a profile picture. This illustrates the flexibility of MongoDB's schemaless design, enabling us to store records with different fields effortlessly. Finally, we utilize the insert_one method to add both user profiles to our collection. This efficient insertion process showcases MongoDB's ability to handle dynamic data structures, highlighting how easily we can adapt our data storage as our application evolves. The figure titled Advantages of Using MongoDB displays a horizontal bar chart with 7 labeled advantages and their effectiveness scores on a 0-100 scale. From top to bottom, the plotted values are flexibility in data modeling 90, seamless integration 88, horizontal scalability 85, geospatial indexing 82, rich querying capabilities 80, community support 79, and built-in replication 75. The bars and their numeric labels make it clear that flexibility in data modeling is the highest scoring advantage, closely followed by seamless integration. These two stand out by being near the 90 mark. Horizontal scalability and geospatial indexing occupy the mid to high range, around 80 to 85, indicating strong capabilities there as well. Rich querying capabilities and community support are slightly lower but still above 75, showing consistent strengths across core developer needs. Built-in replication is the lowest of the set at 75, which, while lower relative to the others, remains in the upper percentiles overall. The x-axis grid and the 0-100 range emphasize that all listed advantages score well, clustering in the 75-90 band. The pattern supports the lesson's claims that MongoDB offers multiple robust benefits, with flexibility and integration being the most prominent when prioritizing features for application design and architecture decisions. Next, we will write the code to set up sharding in a MongoDB database specifically tailored for our e-commerce application. The first step involves establishing a connection to our MongoDB instance using the MongoClient class. This allows us to interact with the database we want to work with. In this example, we are connecting to e-commerce database. Now let's enable sharding for the database by using the enable sharding command. This is a crucial step as it prepares the database to distribute its data across multiple servers, which is vital for handling increased traffic without sacrificing performance. Once sharding is enabled, we move on to the shard collection command, which specifies that we are sharding the product's collection by the producted. This choice is strategic, as sharding by producted ensures efficient data distribution, allowing for rapid access times, especially during peak usage times typical for e-commerce applications. By implementing sharding in this manner, we are setting our application up for scalability and improved efficiency. Now let's take a look at how we can query our user collection in MongoDB to efficiently find specific data. In the following code snippet, we initiate a query that retrieves all users who are older than 25 years. This is accomplished by using the find method where we specify the condition, age, GT, 25. The use of MongoDB's query operators like GT, greater than, allows us to filter users based on their age dynamically. Once we have the filtered results, we further enhance our output by sorting these users in alphabetical order according to their usernames, achieved by chaining the sort method with the argument username. This flexible querying capability showcases MongoDB's powerful approach, enabling developers to construct comprehensive queries that extract meaningful insights from their datasets. Finally, we loop through the results and print each user, providing a clear representation of the users who meet our specified criteria. This demonstrates not only how to query data, but also how to ensure that the returned information is organized in a user-friendly manner, reflecting the versatility of MongoDB's querying language. Next, we will see how we can implement a replica set in MongoDB, which is essential for ensuring high availability and fault tolerance in your application. To start, you'll need to launch 3 MongoDB instances, each configured with the same replica set name, myReplicaSet. Each instance is assigned a different port, 27017, 27018, and 27019, and a unique database path to store data. This setup allows all 3 instances to work together as a single system, ensuring that if one instance goes down, the others can continue to operate seamlessly without losing data. Once you have started the instances, the next step is to initialize the replica set. This is done by connecting to one of the running instances and executing the command rs initiate. This command will configure the MongoDB server to start working as a replica set, managing the synchronization of data among the instances. This method enhances data redundancy and ensures your application remains reliable, making it well equipped to handle unforeseen failures or downtimes. Now let's see how we can implement a FastAPI endpoint to handle user registration while efficiently storing data in MongoDB. In this example, we start by importing the necessary libraries: FastAPI for building our API, Pydantic's base model for data validation, and MongoDB's MongoClient for database interactions. We establish a connection to our MongoDB instance and specify the database and collection where user data will be stored. Next, we define a user model using Pydantic. This model outlines the structure of the data we expect when registering a user, including the username, email, and age attributes. By utilizing Pydantic, we ensure that incoming data is validated automatically, catching any discrepancies early in the process. Following this setup, we create a post endpoint at users, which will handle requests for new user registration. Inside this endpoint, we convert the incoming user data into a dictionary format before inserting it into the MongoDB collection. Finally, we return a success message along with the user data, allowing the client to confirm that the registration was successful. This straightforward and efficient approach highlights the synergy between FastAPI and MongoDB, streamlining the process of creating full-stack applications. Now let's see how we can implement geospatial indexing in MongoDB to effectively handle geographic data, such as locating coffee shops. First, we create a collection specifically for coffee shops, which will store their relevant information. Next, we insert a document representing a coffee shop, where we specify its name and include its geolocation in the form of coordinates. This geolocation is crucial as it enables us to perform various geographic queries based on proximity. Once we have our coffee shop data stored, we can utilize MongoDB's powerful geospatial querying features. In this case, we want to find all coffee shops within a 1 km radius of a specified location. We use the near operator combined with the geometry specification to set the coordinates of the reference point and define the maximum distance to search within. This allows us to retrieve nearby coffee shops efficiently, illustrating how geospatial features in MongoDB empower developers to build location-based applications seamlessly, whether for real estate, travel, or social networking. Lastly, let's not overlook the thriving community and extensive documentation surrounding MongoDB. With a rich ecosystem of resources, including tutorials, community forums, and official documentation, developers can easily find help and support as they navigate their projects. This aspect not only accelerates the learning process, but also offers a comforting safety net when facing challenges. In our project scenarios, we can rely on MongoDB's user guides, API references, and use cases that clarify how to leverage different features effectively. If you ever get stuck, a quick search often leads you to community solutions or previously asked questions, ensuring you're never alone in your development journey. In conclusion, MongoDB is not merely a database. It's a comprehensive solution tailored for the demands of modern application development. Its flexibility, scalability, rich querying capabilities, built-in replication, seamless integrations with frameworks like FastAPI, and robust support for geospatial queries prove that it empowers developers to create sophisticated applications with ease. As we move forward in our full-stack journey with Python, FastAPI, React, and MongoDB, embracing these MongoDB benefits will undoubtedly pave the way for building high-performance, reliable, and future-ready applications. Thank you for tuning in, and I can't wait to see you in the next lesson. FastAPI and React combine to create a powerful stack for building modern web applications. In this lesson, we will dive into how FastAPI integrates seamlessly with React, focusing on optional dependencies served by Unicorn, a high-performance ASGI server. So far, we've learned about MongoDB's advantages, including flexible data modeling, horizontal scalability, and its ability to integrate with frameworks like FastAPI. Now, we will cover the nuances of how FastAPI can serve as the backend while React takes care of the frontend, making for a dynamic full-stack development experience. The displayed figure, titled Integration of FastAPI with React, is a radar chart plotting 6 integration-related categories on a 0-100 scale. FastAPI 95, Unicorn 90, Pydantic 85, MongoDB 80, React 90, and User Experience 88. The polygon formed is broadly balanced, but shows a noticeable inward dip on the MongoDB axis relative to the others, indicating that database integration and data persistence present the most room for improvement compared with the rest of the stack. FastAPI reaches the highest score, 95, underscoring its central role and maturity as the backend framework. Unicorn and React both score 90, highlighting strong performance and parity between the server runtime and frontend. Pydantic at 85 and User Experience at 88 are high but slightly behind the top tier, suggesting validation schema design and UX refinements are important next steps. From this chart, we conclude that the stack is overall well-aligned, performance and front-end concerns are well covered, while targeted effort on MongoDB integration, indexing, schema design, connection management, and on tightening data validation with Pydantic will yield the best improvements to make the full-stack integration more robust and consistent. Now let's create our FastAPI application by writing the core code in a file named main.py. We start by importing the necessary modules, FastAPI, which manages our API routing, and Pydantic's base model for data validation. Next, we define a class called item that extends base model to represent the structure of our items, specifying attributes such as ID, name, and price. This defines how the incoming data should be structured and allows FastAPI to automatically validate requests against this schema. Following this, we initialize our FastAPI application with app equals FastAPI and set up sample data in the form of a list of dictionaries, each containing an item's details. Now we will implement a GET endpoint by creating the readItems function. This function is decorated with @app_get/items/, indicating that it responds to GET requests at the path items. When invoked, it returns our sample list, formatted as JSON. Finally, to observe our FastAPI application in action, we will run it using Uvicorn by typing uvicorn main app reload into the terminal. The reload flag allows for automatic refreshing of the server upon code changes, facilitating a smoother development process. Once running, we can access our API at http://127.0.0.18000/items/, where we will see our items listed in JSON format. Now let's transition to building our React frontend that will interact with the FastAPI backend we previously set up. First, we need to create a new React application using create_react_app, which simplifies the setup process. Once we have our React app established, we will focus on creating a component named itemList.js. This component serves a critical role in fetching and displaying the items from our FastAPI API. In the itemList component, we will utilize the useState hook to manage our item's state variable, which will hold the data fetched from the backend. Next, we will implement the useEffect hook to perform a fetch request to our FastAPI endpoint as soon as the component mounts. This approach ensures that data is retrieved in a timely manner, populating our UI as soon as it becomes available. Upon receiving the data, we will update our state with the fetched items, allowing us to dynamically render them in an unordered list. Now let's take a look at how we can integrate this component into our main app.js file. By importing the itemList component and including it in the component tree, we ensure that it renders when the application is accessed. After completing these steps, running the React application will enable users to view the list of items seamlessly pulled from the FastAPI backend. Now let's implement a new endpoint in our FastAPI application that allows clients to filter items by price. We start by importing query from the FastAPI package, which provides a way to define query parameters with additional features such as descriptions. In the readItems function, we define a query parameter called price, which defaults to none. This allows the parameter to be optional, giving clients the flexibility to request all items or only those that meet their price criteria. When the endpoint is accessed with a price query, we conditionally filter the items list, returning only those items with a price less than or equal to the specified value. This enhances the API's usability by allowing for dynamic data retrieval based on user input. If no price is provided, the function simply returns all items. Such adaptability in filtering options exemplifies how optional dependencies can significantly improve the API's functionality and user experience. Next, we will enhance the React frontend by integrating a form within the itemList.js component, allowing users to input a maximum price for filtering items. This interactive feature will demonstrate how the combination of optional dependencies in FastAPI and dynamic updates in React can create a more engaging user interface. Now let's implement error handling in our fetch operation. We will enhance the fetchItems function to ensure that our application behaves gracefully even when fetch requests fail. This function is defined as an asynchronous arrow function that attempts to fetch item data from our FastAPI backend. To ensure robust error management, we wrap our fetch call in a try-catch block. Within the try segment, we await the response from the fetch request. We also check if the response is OK by evaluating response OK. If the response indicates a failure, we throw an error with a descriptive message. This action prompts the control to jump to the catch block, where we can log the error details to the console, informing us of the failure and helping in troubleshooting. In the catch block, we can also consider adding state management for displaying error messages to the user, enhancing the overall user experience by keeping them informed about any issues. Implementing error handling significantly contributes to the robustness of our application and reassures users that errors will be managed effectively. Now let's implement the following endpoints for creating, updating, and deleting items within our FastAPI application. First, we define a post endpoint at items, which allows clients to send new item data in JSON format. This endpoint appends the new item to our existing list and returns the created item, ensuring that it conforms to our predefined schema. Next, we will write a PUT endpoint at items_itemId, which handles updates for existing items. It takes an item ID as a path parameter and searches for the corresponding item in our list. If found, it updates the item details with the new data provided and returns the updated item. If the item isn't located, it returns an error message. Lastly, we create a delete endpoint at items_itemId to enable the removal of items from our list. Upon receiving the item ID, it filters the list to exclude the specified item and confirms the deletion with a success message. Together, these endpoints form a cohesive CRUD interface, adhering to REST-default principles, allowing seamless interaction between your React frontend and FastAPI backend. So here we stand, understanding how FastAPI integrates with React to create a powerful full-stack application. We've walked through the basic setup, added optional dependencies, explored error handling, and discussed best practices for scaling the API. In this dynamic era of web development, knowing how to seamlessly link a modern frontend with a robust backend is a powerful skill that will serve you well. As we wrap up, remember that the combination of FastAPI, React, and MongoDB opens up pathways to building intricate applications while maintaining performance and flexibility. It's all about how you orchestrate these technologies to create a smooth user experience. Make sure to experiment further with your FastAPI endpoints and React components. The more you practice, the better your understanding will get, leading you to build even more complex and engaging applications. Thank you for tuning in, and I look forward to seeing your projects come to life. MongoDB's aggregation framework serves as a powerful system for processing and transforming data, allowing developers to generate insights and perform calculations within their applications. This framework uniquely aligns with modern web applications where data is often structured in complex ways, such as embedding documents within documents. In this session, we will explore the features and functionalities of the MongoDB aggregation framework, enhancing our understanding of how to manipulate and analyze data effectively. So far, we learned that FastAPI and React together form an effective stack for modern web applications, focusing on their seamless integration, especially regarding API requests and user interfaces. We discussed how to set up a FastAPI backend that serves data to a React frontend and explored optional dependencies for creating dynamic API endpoints. Additionally, we covered error handling best practices and how to design a scalable API following REST-default conventions, enabling full CRUD functionality for our application. This combination of technologies equips developers to create robust, high-performance web applications. Now, we will delve into the MongoDB aggregation framework, examining its purpose, structure, and practical applications in building dynamic web solutions. Next, we will implement the following pipeline to count the total number of comments per blog post. We start by unwinding the comments array, which deconstructs each blog post's comments into individual documents. This transformation is crucial because it allows us to analyze each comment separately, facilitating accurate aggregation. After unwinding, we employ the group stage to aggregate the unwound comments based on the id of each blog post. Here, we use the sum operator to tally the total count of comments for each post. The result of this aggregation gives us a clear insight into how many comments each blog post has received, which can be valuable for understanding engagement levels and author popularity. Now let's see how we can modify the pipeline to calculate the average number of likes per comment across all blog posts. We again begin by unwinding the comments array, allowing us to focus on individual comments. This time, the group stage computes the average likes using the AVG operator, effectively giving us a single value that represents the mean engagement across all comments. This efficiency in calculating averages demonstrates the power of MongoDB's aggregation framework in providing meaningful insights into user interactions. Now let's implement code to count all comments present in our blog posts collection by utilizing the MongoDB aggregation framework. We begin by importing the Mongo client from the PyMongo library to connect to our MongoDB instance. Upon establishing the connection, we select our database and the blog posts collection we'll be working with. Next, we define our aggregation pipeline, which consists of two stages. The first stage is the unwind operator applied to the comments array. This step transforms each array element into its own document, allowing us to work with individual comments separately. Following this, we employ the group stage where we aggregate the unwound documents. Here, we group by the id of each blog post and calculate the total comment count using the sum operator. Every time we find a comment, we increment our count by 1. Lastly, we execute the pipeline using the aggregate method and convert the results to a list, which is then printed out. This approach provides a clear overview of the total number of comments associated with each blog post, showcasing the power of MongoDB's aggregation capabilities. Next, we will implement a pipeline to calculate the average number of likes across all comments in our blog posts. To achieve this, we start with the unwind stage, which deconstructs the comments array, creating a separate document for each comment. This step is crucial as it allows us to perform operations on individual comments rather than on the entire array. Following the unwind operation, we use the group stage to aggregate the unwound documents. Here, we specify id, none, to group all documents together, allowing us to calculate the average likes without dividing by any specific criteria. The AVG operator efficiently computes the average number of likes from the likes field within each comment. When we run this pipeline, we gather the necessary metrics to understand reader engagement across all comments. The final result collected in the result variable provides insights into how many likes, on average, comments received across our blog posts. This aggregation technique not only simplifies the analysis, but also extracts meaningful information that can inform content strategies or improvements. Now let's see how we can calculate the average number of likes specifically for comments made by John using the MongoDB aggregation framework. We begin by unwinding the comments array, which transforms each comment into a separate document, allowing us to work with individual comment attributes more efficiently. After unwinding, we introduce a match stage that filters these documents, ensuring that we only consider comments authored by John. This is a crucial step as it allows us to narrow down our data set to focus solely on the relevant comments, facilitating a more accurate average calculation. Following the match, we employ the group stage where we set id to none, indicating that we want a single consolidated result rather than grouping by specific document identifiers. Here, we calculate the average likes by using the AVG operator on the likes of John's comments. The output of this aggregation will yield a document that reflects the average number of likes for all comments made by John, providing valuable insights into user engagement related to his contributions. Now let's implement the following aggregation pipeline to display the most liked comment per blog post. First, we'll use the unwind operator to deconstruct the comments array, enabling us to work with each comment as a separate document. This is essential for accurate grouping in the next stage. Next, we will group the documents based on the blog post's id. Here, we introduce the max operator to identify the highest number of likes for the comments within each blog post. Additionally, we'll use the push operator to gather all the comments associated with that post into a single array called comment details. This dual approach allows us to track the most liked comment while also retaining access to all comment data for further analysis. Finally, we will apply the project stage, where we specify the output fields we need. We retain the most liked comment that we calculated earlier, while details will extract the comment information from our comment details array by utilizing the array element operator. This structured output not only highlights the most liked comment, but also captures the relevant details, providing a clear summary of engagement for each blog post. Now let's implement the following aggregation pipeline utilizing the facet operator. This allows us to perform multiple aggregations simultaneously on the same dataset, making it an efficient choice for obtaining diverse insights in a single query. In this pipeline, we first define a facet that creates two distinct aggregation streams, one for counting the total comments and another for calculating the average likes across those comments. To achieve this, we start with unwind, which transforms the comments array. This action breaks each blog post's comments into individual documents, allowing us to perform grouped calculations on them. For the total number of comments, we use group to aggregate the unwound documents, counting each instance. The second aggregation stream also unwinds the comments and subsequently utilizes group to compute the average likes by applying the AVG operator. Ultimately, this methodology effectively consolidates results into a single document, demonstrating the power of the facet operator to streamline complex aggregations while minimizing the number of database calls, thus enhancing application performance and responsiveness. The displayed horizontal bar chart titled Key Insights from MongoDB Aggregation Framework summarizes 3 core aggregation outputs: total comments 35, average likes 7, and most liked comment 15. Along the vertical axis, the 3 concepts are listed, while the horizontal axis quantifies counts and averages. Each bar has a numeric label at its end showing the exact value. Interpreting these values together, the total comments value 35 represents the overall comment volume captured by account aggregation. The average likes value 7 indicates mean engagement per comment across the dataset, and the most liked comment value 15 reflects the maximum likes found on a single comment. The pattern shows a moderate average engagement level, with a single comment reaching more than double the average, 15 versus 7, which suggests a skew in engagement where some comments outperform the typical comment. From an aggregation perspective, this visual confirms that using group with sum, AVG, and max yields complementary insights: overall volume, central tendency, and extreme values, enabling you to detect both the common behavior average and standout items max within the same dataset. In summary, the MongoDB aggregation framework offers extensive capabilities for processing and analyzing data stored in the database. We've covered how to use basic operators like unwind, group, and match to handle embedded documents effectively and obtain insightful results. Additionally, we witnessed the potential of using more complex operators, such as facet, to streamline multiple aggregation queries simultaneously. By understanding and implementing these concepts, you're well equipped to harness the power of MongoDB in your applications, particularly for data-driven solutions. This agile framework not only enhances query performance, but also supports the dynamic nature of modern web applications as they interact with complex data structures. Utilizing these tools effectively can yield significant insights and practically improve user experiences. Next, we will be looking into how these aggregation features can best be integrated with our FastAPI backend to ensure that our frontend remains fast and responsive, feeding it real-time insights straight from the database. Keep experimenting with your queries, and soon you'll find yourself mastering the art of data aggregation. FastAPI provides remarkable asynchronous support that enables developers to build highly efficient web applications. By using an asynchronous server gateway interface, or ASGI, alongside an ASGI-compatible server like Uvicorn or Hypercorn, FastAPI delivers a truly non-blocking workflow. You don't even have to import the Asyncio module. It's all handled seamlessly under the hood, allowing developers to maximize performance with minimal overhead. So far, we learned about the powerful capabilities of FastAPI and how it can be used to serve and manage data efficiently. We've incorporated FastAPI's various features to improve API design and performance, and now we will focus on how its asynchronous functionality can help us build scalable applications that can handle numerous concurrent connections without sacrificing performance. The figure titled FastAPI Performance Metrics displays 3 primary metrics across 2 coordinated visual encodings, bars and align with markers. On the left primary y-axis labeled count, 2 bars represent numeric counts, concurrent requests at 1000 and response time ms at 200 with the exact values annotated above each bar. A secondary right y-axis labeled response time ms supports a 2-point line plot that connects the point for response time ms 200 to the point for I/O operations 5000 with markers indicating the plotted values. Reading these elements together, the chart shows a high capacity for concurrent requests 1000, a moderate measured response latency 200 ms, and an extremely large number for I/O operations 5000 that sits far above the response time point on the secondary axis. The visual pattern, a relatively tall concurrent requests bar, a modest response time bar, and a steep rise on the line to the very large I/O value, highlights that while request concurrency is high and latency remains moderate, I/O activity is orders of magnitude greater and likely to dominate system load. From this, we can conclude that optimizing or offloading I/O, for example with asynchronous I/O, batching, caching, or background tasks, would be a primary focus to improve overall performance, since the I/O operations appear to be the largest contributor to resource usage in the displayed metrics. Now let's see how we can implement an asynchronous endpoint using FastAPI. In this code, we create a FastAPI application instance, which serves as the main entry point for our web application. Next, we define an asynchronous endpoint at the path async data using the @app_get decorator, allowing HTTP GET requests. Within this endpoint, we define an asynchronous function called fetchData, which simulates a long I/O bound operation by awaiting a 3-second delay using Asyncio sleep 3. This use of await makes the function non-blocking, enabling the FastAPI server to handle other incoming requests during this wait time. As a result, the application remains responsive, showcasing the power of asynchronous programming. Once the delay is complete, the function returns a JSON response with a message indicating that the data has been fetched successfully. This example illustrates how FastAPI can efficiently handle multiple requests concurrently, proving especially beneficial for applications that may need to manage many simultaneous users without sacrificing performance. Now let's implement the following code that creates a FastAPI endpoint for fetching a random joke. In this example, we define the joke endpoint, where we utilize the HTTPX library to make an asynchronous HTTP GET request to the joke API. By employing HTTPX sync client, we enable our application to handle the request without blocking other operations. This approach highlights FastAPI's asynchronous capabilities, as it allows the server to remain responsive to additional incoming requests while waiting for a response from the external API. When the joke endpoint is accessed, we open an asynchronous context for the HTTP client and send the request to retrieve a joke. Once the response is received, we parse the JSON data to extract the joke's setup and punchline parts. Finally, the endpoint returns this information in a JSON format. By structuring the code this way, we not only ensure that our application can serve multiple requests efficiently, but also leverage external APIs seamlessly, enhancing the overall functionality of our FastAPI application. Now let's implement an asynchronous endpoint in our FastAPI application that fetches a random joke from an external API. We start by importing the necessary modules, including FastAPI and HTTP exception for handling HTTP errors, as well as the HTTPX library for making asynchronous HTTP requests. In our code, we define a FastAPI instance and create an endpoint at joke. Inside the endpoint function, we utilize a try-except block to gracefully handle potential errors during the HTTP request. This is crucial because it ensures our application remains robust. We establish an asynchronous HTTP client session using HTTPX async client. This allows us to send a GET request to the joke API asynchronously, meaning while waiting for the API response, our application can continue to handle other incoming requests, thus maintaining performance. We also use response raise for status to trigger an error for any non-successful HTTP responses. If an error occurs, we raise an HTTP exception, providing a relevant status code and message to the client. Finally, when the request is successful, we extract the joke data from the response JSON and return it in a structured format. This approach not only offers an enjoyable user experience by providing jokes, but also demonstrates effective error handling and asynchronous programming principles in FastAPI. Now let's see how we can implement asynchronous logging in FastAPI using dependency injection. We begin by importing the necessary modules and initializing the FastAPI application. We've set up basic logging configuration to capture log messages at the info level. Next, we define an asynchronous logging function called logger, which takes a message string as a parameter and logs it using the logging_info method. Now let's write an endpoint for our application data that utilizes this logging function. By using FastAPI's depends, we can specify that the logger function should be executed as a dependency before the main logic of the endpoint runs. In this case, whenever the data endpoint is accessed, it triggers the logger to log fetching data asynchronously. This demonstrates how we can reuse the logging functionality to improve code clarity and maintenance. While the logger is executing, the endpoint simulates a delay with await Asyncio sleep 2 to mimic fetching data, showcasing how FastAPI can handle concurrent operations without blocking the execution flow. Finally, it returns a simple JSON response with sampled data. This pattern not only facilitates effective logging, but also enhances the overall architecture of your FastAPI application by promoting clean and maintainable code. Now let's implement the following code using FastAPI's background tasks feature to handle time-consuming operations without blocking the request-response cycle. In this example, we create a FastAPI application that listens for post requests on the process endpoint. When a request is received, we immediately add a background task using the background tasks parameter, allowing the server to continue processing without waiting for the task to complete. The function perform background task simulates a long-running task by including a sleep period. Here, we mimic a heavy process by calling time sleep 5, which pauses execution for 5 seconds to demonstrate how background operations are executed. Meanwhile, the main request handler sends an immediate response back to the client with a message confirming receipt of the data, while the background task runs concurrently without disrupting the user experience. This approach is particularly beneficial for operations such as sending notifications or generating reports, where immediate output is not required. By offloading these tasks to the background, we enhance the performance and responsiveness of our application, making it more suitable for high concurrency scenarios. Now let's implement the following code to establish an asynchronous database connection using FastAPI and the databases library. We begin by installing the necessary packages to interface with PostgreSQL asynchronously. Next, we define a FastAPI application and set the database URL, which contains the credentials and location for connecting to the database. Upon starting the application, we utilize an event listener for the startup event that establishes the database connection and another for the shutdown event that gracefully disconnects from the database. This ensures that our application manages connections efficiently and doesn't leave any open connections hanging. We then create an endpoint items itemid that demonstrates how to retrieve a specific item from the database. This endpoint utilizes a parameterized query to prevent SQL injection attacks and enhances security. By using the fetchOne method, we can asynchronously execute the query and await the results, allowing FastAPI to maintain responsiveness by handling other requests while this operation is in progress. This approach showcases the elegance and efficiency of working with an asynchronous framework, greatly improving the performance of applications interacting with a database. Now let's write a test for our joke endpoint to ensure its functionality works as expected when accessed. We will utilize the HTTPX async client within a PyDist test function, allowing us to send asynchronous requests to our FastAPI application. The @PyDist mark asyncio decorator indicates that the test will run asynchronously. In the test function, we create an instance of the async client, passing our FastAPI app as an argument. This client will allow us to simulate HTTP requests to the application without needing to spin up a server. By using a context manager, we ensure that the client is properly closed after the test completes. Next, we send a GET request to the joke endpoint and await the response. The test assertions confirm that we receive a successful status code of 200, indicating the endpoint is accessible. Additionally, we check if the JSON response contains the expected fields, setup, and punchline. These assertions validate that the endpoint behaves correctly, ensuring our asynchronous functionality within the FastAPI app is robust and reliable. This approach exemplifies how easy it is to test asynchronous endpoints with FastAPI. In conclusion, FastAPI's asynchronous support creates a unique environment for developing high-performance web applications that can handle many tasks simultaneously. Through the use of async-await, the HTTPX library for asynchronous HTTP requests, dependency injection for reusable code, background tasks for offloading heavy operations, and efficient database interactions, we've explored how to build applications that remain responsive under load. By mastering these asynchronous capabilities, you're well equipped to build modern applications that can scale gracefully, making your way into the full-stack development world more efficient and enjoyable. Keep experimenting with these concepts to harness the full power of FastAPI, and soon you'll be writing lightning-fast applications that wow your users. Let's dive into deployment options for FastAPI. In today's session, we'll explore various environments where FastAPI can flourish, enabling us to host our web applications securely and efficiently. So far, we learned about FastAPI's asynchronous capabilities, which allow developers to build highly efficient web applications that can handle numerous concurrent connections without blocking. We explored how to implement asynchronous endpoints, utilize third-party libraries like HTTPX for non-blocking HTTP requests, and manage errors effectively. Additionally, we discussed the importance of dependency injection, background tasks, and efficient database interactions to enhance performance. Through these features, FastAPI enables the development of scalable applications that maintain responsiveness under load. Now we will talk about deployment options where these applications can thrive. Now let's take a look at a basic command to run a FastAPI application using Unicorn. The command consists of several parts that dictate how our server will behave. The Unicorn main app portion specifies that Unicorn should locate the application instance named app within the main py file, providing the entry point for our FastAPI app. Next, we see the host 0000 option, which allows the server to be accessible from any IP address. This is particularly important for cloud environments where multiple requests from different sources might be coming in. The port 8000 argument specifies the port number on which the application will listen for incoming traffic. Lastly, the reload flag is a fantastic feature for development. It enables automatic code reloading whenever changes are made, so developers do not need to manually restart the server each time they modify the code. This results in a smoother development workflow, allowing for quicker iterations and testing of changes. Overall, this command is essential for getting your FastAPI application up and running efficiently while facilitating a user-friendly development experience. Now let's take a look at a basic Nginx configuration that serves to reverse proxy requests to our Unicorn server. This configuration begins by specifying that Nginx should listen for incoming traffic on port 80, which is the standard port for HTTP. The server name directive should be replaced with your domain name, directing Nginx to handle requests for that specific URL. Within the location/block, we use the proxy pass directive to forward all requests that hit this endpoint to the Unicorn server running on port 8000. This enables Nginx to act as a middleman, receiving requests from users and passing them to the FastAPI application seamlessly. To preserve essential request information, we include several proxy set header directives. These headers ensure that vital details such as the original host, real client IP address, and forwarded protocol are sent along to the FastAPI application. This is crucial for maintaining accurate request logging and for any functionality depending on the client's IP. By implementing this configuration, we establish a robust setup that enhances application performance, security, and scalability. Let's start by creating the requirements (txt) file, which is crucial for outlining the dependencies of your FastAPI application. This file serves to inform Heroku about the necessary packages that should be installed during the deployment of your application. For this implementation, we will include FastAPI, Unicorn Standard for the ASGI server, and HTTPX for handling asynchronous HTTP requests. It is important to list each package on its own line to ensure that Heroku can install everything required for your application to function properly. Following that, we will craft a procfile, which provides Heroku with instructions on how to initiate your FastAPI application. In this document, we define the command to launch Unicorn with your FastAPI app, including the settings for the host and port. By using port -5000, we allow Heroku to automatically assign a port, making your application accessible over the web. Finally, we will examine the Git commands necessary to prepare and deploy our application. We begin by initializing a Git repository to handle our project files. Then we create a new application on Heroku using the Heroku create command. Afterward, we stage our modifications, commit them with an appropriate message, and push the code to Heroku. This progression ensures that your FastAPI application is effectively set up and deployed within Heroku's cloud infrastructure. Now let's implement a Dockerfile to containerize our FastAPI application. We start by specifying the base image from Tiangolo, which includes both Unicorn and Unicorn, offering a solid foundation for running our FastAPI app in a production environment. The first instruction copies the entire application directory into the container's app directory, ensuring that all our application files are included. Next, we need to install any dependencies our application requires. We achieve this by first copying the requirements (txt) file into the app directory of the container. This file lists all the necessary packages our application needs to run properly. The run command then executes a pip installation using this file, ensuring that we have all dependencies installed without unnecessary cache files, which keeps our image size smaller and cleaner. Once our Docker file is ready, we can build our Docker image using a specific tag, making it easy to identify. After that, we can run the container, mapping port 8000 on our local machine to port 80 of the container. This setup allows us to access the application through http://localhost 8000, demonstrating the effectiveness of containerization for deploying FastAPI seamlessly across different environments. The figure shown is a vertical bar chart titled Deployment Options for FastAPI that compares performance ratings on a 0-100 scale across 5 deployment methods: Docker 80, Unicorn and Nginx 75, Heroku 90, Serverless Oz 70, and Load Balancing 85. Each bar is labeled with its numeric value, and the y-axis is scaled to 0-100 with horizontal grid lines to aid comparison. Key patterns are immediately visible. Heroku has the highest reported performance, 90, followed by Load Balancing 85 and Docker 80. Unicorn and Nginx sit slightly lower at 75, while Serverless AWS shows the lowest rating at 70. From these values, you can conclude that in this depiction, managed platforms and traffic distribution strategies rank highest for raw performance. Containerization offers solid and consistent results. A standalone ASGI server with a reverse proxy gives good but slightly lower ratings, and serverless shows the lowest performance figure, suggesting potential trade-offs like invocation overhead or concurrency limits. Use this comparison to inform deployment choices. Prioritize solutions that align with your performance needs, e.g., load balancing or managed hosts for higher throughput. Choose Docker for portability with good performance, and reserve serverless for use cases where cost or on-demand scaling outweighs peak performance. Now let's implement the following code to set up our FastAPI application for deployment to AWS Lambda using Mangum. First, we begin by installing the Mangum library, which serves as a connector between our FastAPI app and the AWS Lambda environment. This is essential for allowing our application to run in a serverless architecture. Next, we define our FastAPI application instance using the FastAPI class. This is where we can define our routes and corresponding request handling logic. In this case, we're creating a simple endpoint at the root, represented by the path. The asynchronous function readRoute responds to GET requests by returning a JSON object with a friendly greeting. This demonstrates how easy it is to define endpoints in FastAPI. Finally, we wrap our FastAPI app with the Mangum handler. This enables our app to process incoming Oz Lambda events properly, allowing it to function seamlessly in a serverless setting. With this setup, you're ready to deploy your FastAPI application to AWS Lambda, making it accessible over the web through an API gateway. Now let's implement a caching mechanism to optimize our FastAPI endpoint. In this example, we first import the Redis library and create a connection to the Redis server running on our local machine. This connection allows us to utilize Redis as our caching solution. Next, we define an asynchronous GET endpoint at the path cached data. When a request is received at this endpoint, we formulate a cache key, which acts as an identifier for the data we want to cache. The application then checks if there's already a cached result associated with this key. If a cached result exists, we immediately return it in the response after decoding it from bytes to a string format. However, if the key is not found in the cache, we must perform the computation to generate the data using the computeData function, which represents a heavy computation or data fetching process. Once the result is computed, we store it in the cache for future requests and then return the newly generated data. This approach significantly reduces the load on the database and enhances the overall performance of our FastAPI application by minimizing response times for repeated requests. Now let's implement the following Nginx configuration to secure our FastAPI application. The first server block listens on port 80, which is the standard HTTP port. Its main purpose is to redirect all incoming HTTP traffic to HTTPS, ensuring that users connect securely. The return 301 directive sends a permanent redirect response, directing users to the same URI but with an HTTPS scheme. The second server block listens on port 443, which is the standard HTTPS port and enables SSL. Inside this block, we specify the SSL certificate and SSL certificate key, directives to point to the paths of your SSL certificate and private key files, respectively. These are essential for establishing a secure connection. Further, we define the location block for the route path, which allows us to route incoming requests to the Unicorn server running our FastAPI application on port 8000. This setup helps maintain a secure environment for your application while delegating the responsibility of SSL termination to Nginx, allowing for improved security and performance. By implementing this configuration, your FastAPI application is well equipped to handle secure traffic, guarding against threats like man-in-the-middle attacks. In conclusion, whether you're deploying FastAPI on a traditional server, a cloud platform, or going serverless, the deployment landscape offers a wide range of options to suit your needs. From using Uvicorn and Nginx for traditional hosting to leveraging Docker for containerized applications, each method has its own advantages. Don't forget about scaling your application with caching strategies and load balancing to enhance performance as your user base grows. Pay close attention to security, using SSL to protect your data in transit. With these insights under your belt, you're well equipped to deploy FastAPI applications with confidence, ensuring they are robust, efficient, and secure in production environments. Happy deploying. FastAPI is a modern and high-performance web framework designed specifically for building APIs with Python. Its unique features streamline the process of API development, making it an excellent choice for developers looking to create robust applications efficiently. So far, we covered FastAPI's deployment options, including running applications on Uvicorn and using Nginx for SSL termination and load balancing. We also explored cloud deployment through platforms like Heroku and Docker containerization, which ensures consistency across environments. Additionally, we discussed serverless architecture and scaling strategies, focusing on load balancing and caching to enhance performance. Now we will dive into the main features of FastAPI that make it stand out in the world of web development. The figure titled Key Features and Performance of FastAPI is a horizontal bar chart that maps 7 core FastAPI features to a performance rating scale from 1 to 10. The x-axis is labeled Performance Rating 110, and the chart range runs from 0 to 10. Each horizontal bar is labeled with the feature name on the vertical axis and displays its numeric score inside the bar for clarity. Key observations from the chart: speed and automatic documentation both receive the top score of 9, indicating these are the framework's strongest aspects. Data validation, security, and background tasks each score 8, showing consistently high capability in ensuring correctness, protecting endpoints, and handling asynchronous background work. Dependency injection and ORM integration are rated 7, slightly lower than the others but still solid. The pattern reveals that FastAPI's principal competitive advantages are raw request handling speed and built-in, high-quality automatic documentation, while dependency management and ORM tooling are strong but comparatively less emphasized, suggesting that developers may need to pair FastAPI with specific libraries or patterns for advanced DI/ORM needs. Overall, the chart corroborates the lessons points by visually emphasizing FastAPI's balanced strengths across performance, validation, documentation, security, and background processing, with modest opportunities for improvement around dependency and ORM integrations. Now let's take a look at a simple FastAPI application that demonstrates how to handle multiple endpoints. We begin by importing the necessary libraries, FastAPI and Uvicorn. Next, we create an instance of the FastAPI class, which will serve as our application. We define 2 endpoints using the @appget decorator. The first endpoint responds to requests made to the root URL and returns a simple JSON message saying, "Hello, world." This helps us ensure that our server is running as expected. In the second endpoint, we use a dynamic path parameter to retrieve an item based on a given itemid. By defining this endpoint as an asynchronous function with the async-await syntax, we inform FastAPI to handle multiple requests concurrently without blocking the server. This feature is crucial for improving performance, especially when dealing with simultaneous users. Finally, we include the condition to run our application using Uvicorn, specifying the host and port. This setup allows us to easily run the app and test these endpoints directly in the browser, showcasing FastAPI's ability to create quick and efficient web applications. Now let's take a look at how we can implement a Pydantic model for an item in FastAPI. A Pydantic model is a powerful feature that allows us to define the structure of the data our API expects and returns. In this case, we define an item class inheriting from base model, where we specify fields such as ID, name, description, price, and tax. The description and tax fields are optional, indicated by assigning them a default value of none, while the ID, name, and price fields are mandatory. This structured approach ensures that incoming request data matches the specified schema, enhancing data integrity. Next, we will integrate this model into our FastAPI application by creating a new endpoint. The createItem function is decorated with @app_post/item/, indicating that it will handle post requests to the item's root. This function accepts an item parameter of type item, which FastAPI automatically validates against our defined model. If the data does not match the required structure, FastAPI will respond with an error message detailing the validation issues, which significantly simplifies error handling and improves application robustness. The interactive API documentation generated by FastAPI is another thrilling aspect of the framework. When you create a FastAPI application, it automatically generates a user-friendly interactive documentation using Swagger UI and RayDoc. All you have to do is run your application and access it via docs or /redoc. For instance, if we run the previous FastAPI application and navigate to http://127.0.0.18000/docs, we'll find a beautiful UI where we can explore our API's endpoints, test them out, and see the request and response models right there in the browser. This automatic documentation is invaluable for both developers and users of the API, enabling easier collaboration and integration. Now let's implement dependency injection in our FastAPI application, which promotes code reuse and maintainability. We start by defining a simple function, queryParam, that takes an optional query string parameter, q. This function is designed to handle incoming query parameters seamlessly. Next, we create an endpoint using the @app_get_decorator@items. Notice how we annotate the parameter query with the depends function. This tells FastAPI that it should invoke the queryParam function to resolve the value of query when the endpoint is called. This modular approach means that if we want to change how we handle query parameters later, we only need to modify the queryParam function without touching the endpoint logic itself. By leveraging dependency injection in this way, we not only enhance the clarity of our code, but also encourage best practices in managing application dependencies. The result is a more organized code base where concerns are separated, making it easier to read, test, and maintain as the application grows. Now let's implement the following security feature using FastAPI that exemplifies how to secure an endpoint with OAuth 2 authentication. We begin by importing necessary modules, including security for managing security schemes and HTTP exception for handling errors. Next, we define an instance of OAuth to password bearer, specifying the token URL where clients will request tokens. This sets the groundwork for using bearer token authentication. Now, we will create an endpoint that allows us to retrieve information about the current user. The /users/me root will utilize the security function to enforce that a valid token is required to access this endpoint. If the provided token does not match our placeholder fake token, we raise an HTTP exception, which returns a 401 status code indicating unauthorized access along with an appropriate error message. If the token is validated, the endpoint will return a simple JSON response signaling access to the current user. This structure not only demonstrates token-based authentication, but also highlights how FastAPI simplifies the process of securing API routes while allowing developers to focus on implementing robust security logic. Now let's implement a background task in FastAPI to handle long-running operations without blocking the main application flow. We start by importing background tasks from FastAPI, which will allow us to schedule tasks to run after returning a response. Next, we define a function called writeLog, which accepts a message as an argument. This function is responsible for appending the message to a log file named log.txt, ensuring a persistent record of actions taken by the application. Now we'll create an endpoint /sendMessage/message that accepts a message as a path parameter. Inside this endpoint, we leverage the background tasks feature by adding the writeLog function to the background tasks queue using background tasks add task, passing the message along. This means that when a client sends a message to this endpoint, FastAPI will quickly respond with a confirmation message while the logging action happens in the background. This asynchronous processing is particularly beneficial for tasks like logging or sending notifications, as it enhances user experience by keeping the application responsive, allowing users to continue interacting with it without waiting for these operations to complete. Now let's implement the following code to demonstrate how FastAPI integrates with SQL databases using SQL Alchemy. This example starts by establishing a connection to a SQLite database through a specified database URL. We create an engine that allows FastAPI to interact with the database and a session maker that facilitates creating new database sessions. Next, we define a model class named user, which represents the structure of our database table. It includes an id field, which serves as the primary key, and a name field for storing user names. With the base metadata createAll method, we instruct SQL Alchemy to generate the database table based on the defined model. To manage database sessions efficiently, we define a function called getDB, which yields a database session when invoked. This approach ensures that the session is properly closed after use, preventing resource leaks. Finally, we implement the createUser endpoint, which leverages FastAPI's dependency injection feature to obtain the database session. This endpoint processes incoming user data, adds a new record to the database, commits the transaction, and returns the created user object. This entire flow illustrates how effectively FastAPI works with SQL Alchemy for database interactions. The community support around FastAPI is remarkable, with an abundance of documentation, resources, and tutorials available. This supportive environment helps both new and experienced developers in solving challenges efficiently while integrating various technologies within their projects. Furthermore, as FastAPI's popularity grows, the ecosystem around it is expanding rapidly, resulting in plugins and extensions that enhance its core capabilities. In conclusion, FastAPI has rapidly become a preferred choice for many developers due to its impressive performance, ease of use, and robust features. Whether it's automatic data validation, real-time API documentation, or seamless async support, FastAPI offers a modern solution that simplifies API development while allowing for scalability and maintainability. In this lesson, we've covered the main features of FastAPI, including its speed, data validation, automatic documentation, dependency injection, security, background tasks, and ORM integration capabilities. With these tools and features at your disposal, you're well equipped to tackle full-stack development using FastAPI, React, and MongoDB with confidence and efficiency. Thank you for watching, and don't forget to explore FastAPI's rich documentation for more advanced features to further enhance your projects. In this lesson, we're diving into one of the standout features of FastAPI, its powerful dependency injection system. This mechanism not only makes your code cleaner, but also enhances reusability and the overall architecture of your applications. So far, we learned that FastAPI is a high-performance web framework for building APIs with Python, known for its speed and automatic documentation features. We have discussed deployment options, including cloud and serverless architectures, and explored core functionalities such as data validation, dependency injection, and security implementations. Additionally, we examined the framework's ability to handle asynchronous requests and manage background tasks efficiently. Overall, FastAPI simplifies API development while ensuring scalability and maintainability. Now, we will cover advanced usage of FastAPI, focusing on how to effectively utilize dependency injection for cleaner code and better application structure. Dependency injection in FastAPI is one of those features that sets the framework apart. By promoting the separation of concerns, dependency injection allows developers to write modular code that is easier to test, maintain, and extend. At its core, dependency injection involves passing dependencies to a function rather than having the function create them internally. This can include anything from database connections to configurations or even API clients. Let's jump into some code examples to illustrate how this works in practice. Now let's implement a simple API for managing users using FastAPI, incorporating dependency injection to keep our code clean and maintainable. We start by defining a fake database class that simulates a user database. It initializes with a dictionary of user data. This class includes a method to retrieve user details based on the user ID. Next, we instantiate the fake database and create a getDB function that simply returns our database instance. Using the depends decorator, we inject this database dependency into the read_user endpoint. This design allows our endpoint to retrieve user information without being directly coupled to the database logic, thus promoting separation of concerns. If we later decide to switch to a real database, the endpoint functional logic would remain unchanged. The read_user function, which handles incoming requests, validates the user ID and calls the database to fetch the user data. If a user is not found, it returns an appropriate error message. This structure enhances testability and maintainability, demonstrating the power of dependency injection in building scalable applications. Next, we will implement a user service class that serves as an intermediary between our FastAPI routes and the database, encapsulating business logic for better organization. This class initializes with a fake database instance, allowing it to retrieve user information through a dedicated method called getUser, which abstracts away direct database interactions. Now let's see how we can utilize this service in our endpoint. We define an asynchronous read_user function that takes a userid as a path parameter and uses dependency injection to access an instance of user service. By calling service getUser user ID, we attempt to retrieve the user data associated with the provided ID. If the user is not found, we return an error message. Otherwise, we return the user's information. This architecture not only improves code organization by separating concerns, but also paves the way for future enhancements, such as adding methods for user creation or deletion, without cluttering our root logic. By encapsulating user-related functionality, we maintain a clean and maintainable codebase that aligns well with FastAPI's principles of simplicity and scalability. Now let's implement a simple configuration system for our FastAPI application using a Python class. We begin by defining a settings class that inherits from Pydantic's base model. This allows us to create a structured and validated settings schema for our application. Here, we define a single attribute, API key, which is initialized with a default value of default secret key. This approach helps ensure that all configurations are clearly defined and validated, making it easier to manage and maintain settings. Next, we instantiate the settings class, creating an object named settings. To provide access to these settings throughout the application, we define a function called getSettings. This function simply returns the settings object whenever it is called. Now we can integrate this configuration setup into our FastAPI application. In our endpoint defined at /config, we utilize dependency injection by specifying that the config parameter should be populated using the getSettings function. When this endpoint is accessed, FastAPI will automatically provide the settings instance, allowing us to return the API key as part of the response. This method of encapsulating configurations enhances maintainability and centralizes the management of application settings. The figure titled Key Concepts of FastAPI and Their Importance presents a bar chart that maps 7 core FastAPI concepts to numeric importance ratings on a 1-10 scale. Reading the chart, dependency injection and automatic documentation are shown at the top with ratings of 9 each, indicating they are the most critical features according to the data. A middle tier of capabilities, data validation, security, and background tasks, each carry ratings of 8, forming a clear cluster that signals these are strong, well-supported features that are essential but slightly less dominant than the top 2. Asynchronous requests and ORM support are rated lower at 7, forming the lower bound of this set. This pattern suggests that while FastAPI provides these features, they are perceived as moderately important relative to documentation and dependency injection. The data labels on each bar make these comparisons explicit and allow us to conclude that the framework's primary strengths, per the displayed values, lie in its dependency injection model and automatic documentation, while validation, security, and background processing are also robust capabilities that closely follow. Taken together, the chart reinforces the lesson's emphasis. Dependency injection is a standout advantage in FastAPI, and alongside excellent automatic documentation, forms a foundation that complements other important features like validation and security. Now let's see how we can implement a more advanced endpoint in our FastAPI application that incorporates multiple dependencies. In the following code, we define the read_user config endpoint, which requires both a user and configuration settings. This is achieved by specifying two dependencies in the function signature: user, which retrieves user information, and config, which provides access to the application's configuration. When a request is made to this endpoint, FastAPI first resolves the dependencies before executing the handler function. The depends function is utilized here for both dependencies, ensuring that the desired data is prepared in advance. This design promotes a clean separation of concerns, as the endpoint now focuses solely on returning a response, leaving the data retrieval and configuration management to the respective dependency functions. The return statement constructs a JSON response that includes the fetched user data alongside an API key from the configuration settings. This showcases the power of FastAPI's dependency injection system, enabling seamless integration of different components while maintaining clean and easy-to-read root logic. Now let's implement basic token authentication in our FastAPI application using the built-in OAuth to password bearer. We start by defining OAuth2 scheme, which will manage the extraction of the token from requests, specifying the token URL as token. The next step is to create the getCurrentUser function, which relies on the token extracted by OAuth2 scheme. This function checks whether the provided token is valid. If it's not, an HTTP exception with a 401 status code is raised, indicating invalid credentials. This design abstracts the authentication logic, allowing multiple routes to reuse the same verification process effortlessly. Next, we define the readCurrentUser endpoint to allow users to fetch their information. By employing the depends function, we inject our getCurrentUser dependency directly into the endpoint, ensuring that only authenticated users can access their data. If the user is authenticated successfully, their information will be returned as a response. This streamlined approach not only enhances code organization, but also safeguards our roots, demonstrating the power and efficiency of FastAPI's dependency injection system in managing security features. Now let's implement the session management feature using FastAPI, which allows us to maintain user sessions through cookies. In our code, we define an asynchronous function called getSession, which retrieves the session ID from the incoming request's cookie. If the session ID matches our predetermined value, we return a user object indicating a valid session. Otherwise, an error message is returned signifying an invalid session. This function acts as a dependency that can be reused across different endpoints, enhancing code organization. Next, we create an endpoint at session that employs this session management function. By using the depends class, we indicate that readSessionInfo, the endpoint handler, relies on getSession for its logic. When a user accesses this endpoint, the application automatically checks the session cookie, ensuring only authenticated users can access their session information. This approach highlights how FastAPI's dependency injection system efficiently encapsulates session management, promoting a cleaner and more secure user experience. Let's summarize this advanced look at FastAPI's dependency injection system. We've explored essential aspects of dependency injection, starting from mocking a database and creating a service layer, to managing configurations and handling multiple dependencies. We've also seen how to effectively leverage FastAPI's features for security and session management, allowing us to maintain clean, organized code structures across our applications. With these powerful features in play, FastAPI not only simplifies our code, but also enhances its scalability and maintainability. As you continue to work on your applications, keep these concepts in mind and explore how they can streamline your development process. Dependency injection is not just a tool, but rather a philosophy that fosters clean code practices and makes collaboration within teams more efficient. In conclusion, mastering dependency injection in FastAPI is like equipping yourself with a Swiss Army knife. It has all the tools necessary for building robust APIs effortlessly. As you venture further with FastAPI, think about how you can incorporate these concepts into your projects. By doing so, you will create a more efficient workflow and a maintainable code base that stands the test of time. Happy coding, and don't forget to have fun while building your next FastAPI application. FastAPI is an incredible tool for building APIs, and when combined with modern front-end frameworks like React, it can significantly enhance your application development process. In today's lesson, we will delve into how to integrate FastAPI with front-end frameworks, focusing primarily on using React with MongoDB as our database to explore a schemaless approach. So far, we learned that FastAPI's dependency injection system enhances code organization, reusability, and testability by promoting separation of concerns. We explored its integration with features like mock databases, service layers, configuration management, and security practices such as token authentication. Additionally, we discussed how to effectively manage multiple dependencies within endpoints for cleaner code. Overall, dependency injection serves as a fundamental aspect that simplifies API development while ensuring maintainability and scalability. Now we will cover the integration process of FastAPI with front-end frameworks like React, highlighting how to establish seamless communication between your FastAPI backend and a React frontend, while utilizing MongoDB for a dynamic and flexible data management experience. The figure titled Key Concepts in Integrating FastAPI with Front-End Frameworks presents a horizontal bar chart that ranks 7 integration concepts by importance on a 1-10 scale. The tallest bar corresponds to dependency injection at 10, indicating it is rated as the single most important concept in this integration workflow. Immediately below, FastAPI, React, and state management are all rated highly at 9, showing that both the backend framework, the front-end framework, and the way state is handled on the client are nearly equally critical. MongoDB and user interface are scored at 8, signaling strong but slightly lower emphasis on database choice and UI considerations, while APIs sits at 7, the lowest of the set but still a meaningful factor. From these values, we can draw practical conclusions directly applicable to this lesson. Prioritize establishing clear dependency injection patterns in your FastAPI services because they enable modular, testable interactions, reflected by the top score. Equally invest effort in making sure your FastAPI endpoints and React components are well structured and that state management is reliable, all scoring 9, since mismatches here will most directly impact integration quality. While MongoDB and the user interface are slightly less prioritized, their 8s indicate they remain important. Design your data models and UI flows to be flexible and aligned with the schemaless approach. The APIs themselves, though scored lowest at 7, still require robust design because they are the contract between systems. Treat API design as foundational, but recognize that internal patterns like dependency injection and client-side state will most influence integration success. The numeric labels on each bar reinforce these priorities and make it clear where to allocate development and testing effort when building a FastAPI plus React plus MongoDB stack. We will begin by setting up the essential elements for our FastAPI application, focused on creating and managing user data. The process starts with importing the necessary modules: FastAPI, which aids in building our application, Mongo Client from the PyMongo library for connecting to our MongoDB database, and Base Model from Pydantic, which allows us to define the schema for our user data. We then instantiate FastAPI to serve as our main application framework. The next step involves establishing a connection to our MongoDB database by utilizing Mongo Client, specifying the database and collection we intend to use, namely MyDatabase and users. To ensure that user data adheres to a specific structure and undergoes validation, we define a Pydantic model called user, which includes attributes for the user's name and email, both specified as strings. Following that, we set up a post endpoint at users using the decorator at app_post to handle requests aimed at creating new users. Within the createUser function, we accept an instance of the user model, transform it into a dictionary format, and insert this data into our MongoDB collection. Lastly, we return the newly created user object as confirmation of its successful creation. This organized approach facilitates smooth interaction with the database while maintaining data integrity. In this section, we will implement the code necessary to set up our React frontend to communicate with the FastAPI backend. We start by importing React along with the useState hook and Axios, which we will use for making HTTP requests. The main component, app, is responsible for managing the state related to user input, specifically tracking the name and email fields. We then create the handleSubmit function, which gets called when the form is submitted. This function prevents the default behavior associated with form submissions, constructs a user object, and sends a post request to the FastAPI backend at the designated endpoint. Upon a successful request, it logs the response and alerts the user about the successful creation of the entry. If any errors occur, they are caught and logged, allowing us to diagnose any issues. Furthermore, we design a form that enables users to input their name and email. Each input field is managed by its own state, and both fields include validation to ensure that the user provides the necessary information. The form is submitted when the user clicks the Submit button, and it also incorporates a visual feedback mechanism to indicate any failures. This setup successfully links our React frontend with the FastAPI backend, facilitating user interaction and data management. Now that our FastAPI server is operational, we need to verify its functionality by running a specific command. We will utilize uvicorn main app reload, which initiates the FastAPI server defined in the main py file. By default, this command starts the server on port 8000, enabling us to effectively manage incoming API requests. Moving on to our React application, we will create a new app by executing npx create react app myapp. This command establishes the project structure and installs the essential dependencies required for a React environment. Once we navigate into the newly created project directory, we will install Axios with npm install Axios. Axios is a powerful library that simplifies the process of making HTTP requests, facilitating smooth communication between our front-end and FastAPI backend. With both applications operational, it's crucial to understand their interaction. FastAPI handles the requests and responses, while React takes care of the user interface. This clear division of responsibilities establishes a strong foundation for a full-stack application. Now let's implement the GET endpoint for fetching users in our FastAPI backend. This endpoint, defined as getUsers, allows us to retrieve all user records stored in the MongoDB collection without exposing the internal MongoDB object TID. We achieve this by using the collectionFind method to query the database, specifying an empty dictionary to fetch all documents. By providing a projection of id 0, we ensure that the object TID is excluded from the returned results. Next, we need to integrate this fetching capability into our React frontend. Here, we will create a fetchUsers function that performs an asynchronous GET request to our FastAPI backend using Axios. This function retrieves the list of users and updates the local state by calling setUsers, which ensures our application reflects the most current user data. Additionally, we will utilize React's useEffect hook to call fetchUsers automatically when the component mounts, ensuring that our user state is populated with data from the backend right away. This approach fosters a seamless integration between our FastAPI backend and React frontend, enriching the user experience with dynamic data retrieval. Finally, we'll render the fetched users as an unordered list, displaying each user's name and email address, providing a clear and organized view of the user data. Now let's see how we can implement error handling and loading states in our React application. We'll start by introducing a loading state which is initialized to true. This state will indicate when data fetching is in progress. The fetchUsers function is updated to set the loading state to true before making a request to the FastAPI backend. Following the Axios GET request to retrieve users, we utilize a try-catch block to handle any potential errors that may arise during the fetch operation. If an error occurs, it's logged to the console, but we ensure the loading state is set to false regardless of whether the request succeeds or fails, thanks to the finally block. In addition to the front-end enhancements, we will also improve our FastAPI backend to provide appropriate error responses. We modify the existing createUser endpoint by wrapping the database insertion logic inside a try-except block. If an error arises during user creation, we raise an HTTP exception with a specific status code and a detailed message explaining the error. This structured error handling allows the front-end to present meaningful feedback to users, enriching the overall user experience while interacting with the application. To wrap up, when integrating FastAPI with front-end frameworks such as React, you leverage the power of FastAPI's rapid API development capabilities alongside React's dynamic user interface features. By using MongoDB's flexible schemaless approach, you enhance the overall interaction with data, enabling a truly modern stack that efficiently manages data without rigid constraints. Today's lesson, we've built a full-stack application that connects a FastAPI backend with a React frontend. We successfully created, retrieved, and displayed users while handling errors and incorporating a fluid user experience. This not only equips you with the practical skills needed for full-stack development, but opens the door to countless possibilities for building robust applications. Keep experimenting, have fun with your projects, and remember, your only limit is your imagination. Happy coding! In this video, we're diving into the seamless integration of MongoDB with FastAPI. This combination is a game changer for building rapid, scalable web applications without the shackles of rigid schemas. We'll explore how FastAPI allows us to not only create a robust REST-TFL interface, but also how it complements MongoDB's schemaless approach to data management. Now let's see how we can implement our FastAPI application. We begin by creating a new Python file named main.py, where we'll set up the FastAPI application and establish a connection to MongoDB. We import FastAPI along with a Sync.io motor client from the motor package, which enables us to perform asynchronous operations with MongoDB. After instantiating the FastAPI app, we create a MongoDB client connected to our designated database. This asynchronous client ensures efficient request handling, which is critical for improving the application's performance. Next, we'll implement a post endpoint to allow the creation of new users. Here, we define a Pydantic model called user with fields for name and email. In our createUser function, we convert the incoming user data into a dictionary and insert it into the user's collection in MongoDB. The endpoint responds with the new user's ID and their data. Following this, we need a GET endpoint to retrieve user details by their ID. In the readUser function, we query the database, return user data if found, or raise an HTTP exception if not, which helps us manage errors effectively. This structure is foundational for our FastAPI application, enabling us to set up a robust API interfacing seamlessly with MongoDB. Next, we will write the following code to set up our FastAPI application and connect it to MongoDB. First, we import FastAPI as well as a Sync.io motor client from the motor package, which provides an asynchronous interface for MongoDB operations. By creating an instance of FastAPI, we initialize our application. The Sync.io motor client is then used to establish a connection to our MongoDB instance, allowing us to specify the database we will use. This setup enables FastAPI to handle requests asynchronously, ensuring efficient performance. Now let's see how we can implement an API endpoint to add user data to our MongoDB collection. We begin by defining a Pydantic model called user, which serves as a schema to validate user information consisting of a name and an email. Here, we create the createUser function decorated with the post method. This function converts the validated user data into a dictionary and performs an asynchronous insert operation into the user's collection. The response includes both the newly created user's ID and their data, facilitating easy tracking of user information while maintaining data integrity and validation. The chart titled Frequency of CRUD Operations in FastAPI with MongoDB displays 4 vertically oriented bars labeled create, read, update, and delete on the x-axis with corresponding frequency values of 50, 80, 60, and 40 on the y-axis. Each bar is annotated with its numeric value above the top edge, making exact comparisons immediate. Read 80 is the highest, update 60 is the second, create 50 is third, and delete 40 is the lowest. The clear pattern is a read-dominant workload. Read operations occur twice as often as deletes, 80 versus 40, and are noticeably more frequent than creates and updates. From this distribution, we can draw practical conclusions for designing the API and database layer. Prioritize optimizations that accelerate reads, indexing commonly queried fields, adding caching layers, or using read replicas. Plan for moderate write-update handling, ensuring efficient set operations and considering optimistic concurrency control, and treat deletes as infrequent actions, which may allow soft delete strategies to simplify auditability. The presence of grid lines along the y-axis and the numeric labels emphasizes proportional differences and supports capacity planning. For example, provisioning more resources for endpoints that serve GET requests and validating that asynchronous drivers and connection pooling are tuned to handle read-heavy traffic. Next, we will write a GET endpoint that allows us to retrieve user data based on a user ID. This is an essential functionality, as it enables us to confirm that a user has been successfully created and to access their details as needed. We define an asynchronous function named readUser, which takes a user ID as a path parameter. Inside this function, we interact with the MongoDB collection dedicated to users, where we attempt to find a user document that matches the provided ID. If a user is found, the function responds with a dictionary that includes the user's ID, name, and email, effectively returning their information in a structured format. On the other hand, if the user is not present in the database, we raise an HTTP exception with a status code of 404, signaling that the user does not exist. This approach not only provides clarity in our API responses, but also enhances error handling, allowing front-end applications to manage user absence gracefully. With this mechanism in place, we've ensured our application can effectively read user details while maintaining robust error management. Now let's implement error handling in our readUser function to ensure our application can gracefully manage unexpected situations. We'll begin by importing HTTP exception from FastAPI, which allows us to return structured error responses to the client. In our readUser function, we analyze the user ID provided as a path parameter and attempt to retrieve the corresponding user from the database. If the user is found, we proceed to return their details, including the ID, name, and email. However, when a user is not found, instead of returning a plain error message, we raise an HTTP exception. This triggers a standardized HTTP response with a status code of 404, indicating user not found. By employing this method, we enhance the clarity of error reporting, enabling the front-end to respond appropriately to such scenarios. Next, let's see how we can create an update endpoint using a patch request, which will allow us to modify existing user data based on the user's ID and the updated details provided through a user model. This method leverages the update1 function from MongoDB to apply changes specified in the request, ensuring that our application can effectively manage user data modifications. Now let's implement the update endpoint for our FastAPI application. This is achieved through an asynchronous patch method that allows us to modify the user data stored in the MongoDB database. The updateUser function takes in the user ID and a user object that contains the updated information. Within this function, we establish a connection to the user's collection and make use of the update1 method, incorporating the set operator to update the user's details based on the provided user ID. We also include a check to confirm whether the update was successful by examining the modified count. If a user is successfully updated, a confirmation message is returned. Otherwise, we raise an HTTP exception to inform that the user was not found. Next, we will write the delete endpoint to facilitate user removal. The deleteUser function follows a similar structure to the previous ones, but focuses on deleting a user from the database. Upon receiving the user ID, it attempts to delete the corresponding document in the user's collection using the delete1 method. If the deletion is successful, we return a message confirming the deletion. However, if the user ID does not correspond to any existing user, again, we raise an HTTP exception to indicate that the user was not found. Now that we've covered the create, read, update, and delete CRUD operations in our FastAPI application using MongoDB, let's summarize what we've accomplished. We've set up our FastAPI project, connected it to MongoDB, created a user model, and built a comprehensive REST-TFL API that allows us to perform all necessary operations on user data. As we wrap up this section, it's essential to remember how powerful FastAPI is when combined with MongoDB. This not only simplifies data management, but also enhances the performance and scalability of our applications. Quick data retrieval and a schemaless approach allow us to adapt to changing requirements on the fly. With that said, next, consider how we can handle front-end integration effectively. We will explore how to connect our FastAPI backend with a React front-end, allowing for a dynamic and interactive user experience. Stay tuned, as that's where the magic truly happens. Now get ready to put your newly learned full-stack development skills into action and take your project to the next level. See you in the next video. As developers, finding effective ways to manage data can often make or break our projects. In this lesson, we will explore the numerous advantages of using Pydantic with FastAPI for data validation and simplicity. So far, we learned that we can effectively integrate MongoDB with FastAPI to create a robust REST-TFL API for managing user data. We've established a FastAPI application, connected it to MongoDB, and implemented CRUD operations including creating, reading, updating, and deleting users. Additionally, we've incorporated error handling to ensure meaningful feedback during database interactions. Next, we will focus on integrating this backend with a React frontend for enhanced user experience. Now let's see how we can define a Pydantic model by creating a user class. This class inherits from base model, which is the foundational class provided by Pydantic for creating data models. In the user class, we specify that it has two attributes, name and email, both of which are defined as strings. By utilizing Python's type annotations, we ensure that when a new instance of user is created, Pydantic will automatically validate any input data against these type definitions. If the input does not match the expected structure, Pydantic will raise a validation error, alerting us to discrepancies before processing the data further. This feature is essential as it reduces the need for manual validation and streamlines our workflow when developing applications. Consequently, we can focus on implementing the business logic of our application, knowing that the data being processed adheres strictly to the criteria we defined in our model. This approach exemplifies how Pydantic simplifies data handling while enhancing code maintainability and clarity. The horizontal bar chart titled Advantages of Using Pydantic with FastAPI displays 5 categories with associated percentages: data validation 90%, ease of use 85%, error handling 80%, performance 75%, and nested structures 70%. The bars are ordered to show a clear descending trend from highest to lowest perceived advantage. The most prominent takeaway is that data validation is viewed as the strongest benefit, at 90%, indicating that developers primarily rely on Pydantic for its robust validation capabilities. Ease of use and error handling follow closely at 85% and 80% respectively, highlighting that Pydantic not only enforces correct types but also simplifies developer workflows and produces actionable error information. Performance 75% and nested structures 70% are slightly lower but still substantial, suggesting that while speed and support for complex, nested models are valuable, they are secondary to validation and usability in developers' assessments. The consistent roughly 5% step-down between categories implies a balanced set of strengths where Pydantic delivers multiple meaningful benefits, with validation at the forefront and strong support across usability, error clarity, and handling of nested data structures. Now let's see how we can implement the Create User endpoint in our FastAPI application. In this code, we begin by importing the necessary modules, including FastAPI, HTTP exception for error handling, and a Sync.io motor client from the motor library to interact with MongoDB asynchronously. We then create an instance of FastAPI and establish a connection to the MongoDB database. Next, we define a user model, which inherits from Pydantic's base model. This model outlines the structure we expect from incoming user data, specifying that each user will have a name and email, both as strings. Following this, we define our user's endpoint using the @app_post decorator, allowing it to accept post requests. In the createUser function, we take the user parameter as an instance of our user model. The incoming data is automatically validated against this model, streamlining our validation process. We then convert the user instance to a dictionary and insert it into the user's collection in MongoDB. If the insertion is successful, we return the newly created user's ID along with their data, making it clear and easy for clients to understand what has been stored. Now let's see how we can implement a more complex data model using Pydantic within our FastAPI application. In this example, we define an address model that captures essential components of an address, such as street, city, state, and zip code. Each of these attributes is explicitly typed, ensuring that only valid data can be represented. Next, we incorporate the address model into our user model, allowing users to have multiple addresses. This is achieved by using a list of address instances as an attribute in the user model. When a new user with a list of addresses is created through the API, Pydantic automatically validates the structure of each address against the defined model. This seamless validation process means developers can confidently manage hierarchical data without manual checks. The Create User endpoint facilitates user creation while leveraging MongoDB for storage, ensuring that the user data, including nested addresses, is properly inserted into the database. This approach exemplifies the power of Pydantic in handling complex data structures, making it easier to maintain robust and flexible data models in your applications. Now let's implement the following user model using Pydantic, which will not only validate but also transform input data. In this example, we define a user class that inherits from base model, allowing us to specify the attributes required for each user. The name and email attributes are straightforward strings, while we introduce a registered attribute of type datatime. This attribute utilizes Pydantic's field feature to assign a default value that captures the current timestamp whenever a new user instance is created, thus streamlining the user registration process. Next, we will create the Create User endpoint to handle incoming API requests. This endpoint expects a user object, which means it automatically benefits from Pydantic's validation. Once the user data is validated and transformed into the correct format through the incoming request, we convert the user model into a dictionary using the dict method. Then we insert this user data into our MongoDB database and await the result of the insertion. Finally, the endpoint returns a JSON object containing the new user's ID along with their data, providing a clear response to the client. This approach encapsulates multiple essential functionalities of Pydantic while maintaining clean and manageable code. Now let's explore how to handle error situations gracefully in our FastAPI application. We'll implement logic to check if a user trying to register already exists in the database. To achieve this, we first define our Create User function under the user's endpoint and make sure that it accepts a user instance as input. Within this function, we obtain a reference to the user collection in our database and convert the incoming user object into a dictionary format. The crucial part is simulating a lookup by querying the database to see if a user with the provided email already exists. If a matching user is found, we raise an HTTP exception, specifying a 400 status code and a detailed error message indicating that the email is already taken. This approach provides users with clear feedback on why their registration failed instead of just a generic error message. Finally, if no conflicts are found, we proceed to insert the new user data into the collection and return a response containing the newly created user's ID along with their data. This structured error handling enhances the user experience and allows for more intuitive interactions with the API. Lastly, let's not overlook performance. Pydantic is known for its speed, thanks to a lean design and reliance on type hints. Validation is often a bottleneck in data-heavy applications, but with Pydantic, performance remains high. When working with FastAPI, which is built for asynchronous handling, the combination of quick validation and lightweight processing becomes a competitive advantage. To summarize, using Pydantic with FastAPI brings multiple advantages. It improves data validation by automating checks and maintaining data integrity. It simplifies the complexity of managing nested structures. It transforms and coerces data seamlessly. It provides informative error messages, and it remains high-performing. As we prepare to dive into how we can connect our FastAPI backend with a React frontend, it's critical to appreciate how Pydantic allows us to build APIs that not only manage but validate and transform data in a user-friendly manner. Understanding these features will enable us to create responsive applications that enhance user engagement and satisfaction. In our next lesson, we will explore how to fetch and post data to our FastAPI API using a React frontend and see how Pydantic's capabilities facilitate smooth data interactions between the two. Get ready, as the world of full-stack development opens up new dimensions for us. See you in the next video. Asynchronous programming is a powerful paradigm that can make your applications more responsive and efficient. Today, we're diving into how FastAPI leverages asynchronous programming through the use of an Asynchronous Server Gateway Interface, or ASGI. FastAPI allows you to create performant web applications without needing to worry about the intricacies of the Asyncio module directly. So far, we learned that effective data management is crucial for developers, and Pydantic with FastAPI simplifies this process through automated data validation and error handling. We've successfully integrated MongoDB with FastAPI, implemented CRUD operations, and enforced data integrity using Pydantic models. Additionally, we've seen how Pydantic aids in handling complex data structures and enhances user experience through clear error messages and data transformations. Next, we'll explore the fundamental aspects of asynchronous programming with FastAPI. The foundation of FastAPI's asynchronous capabilities lies in the ASGI specification. ASGI is designed to handle asynchronous code, allowing you to write non-blocking applications that can handle multiple tasks simultaneously. Unlike the traditional WSGI, which is synchronous, ASGI servers like Uvicorn or Hypercorn can manage many concurrent connections. This makes it ideal for web applications that require real-time features, such as chat applications or live data updates. With FastAPI, you can achieve a truly asynchronous workflow by just declaring your endpoints with async functions, resulting in increased performance and responsiveness. Now let's implement the basic setup for our FastAPI application and an asynchronous endpoint. We begin by importing the necessary modules, including FastAPI and Asyncio. Next, we initialize a FastAPI instance, which serves as the main application object that handles our requests. Now let's take a look at how we can define an asynchronous endpoint that simulates a long-running task. We declare a root at long task using the @appget decorator, indicating that this will respond to GET requests. The function long_task is defined as an async function, which allows us to use the await keyword inside it. Here we call await Asyncio, sleep 5, to introduce a mock delay of 5 seconds, simulating a long-running operation, such as a database query or an external API call. Once the delay completes, the function returns a JSON response with a message indicating that the task has been completed. By using this approach, we harness the non-blocking nature of asynchronous programming, allowing our application to handle multiple requests efficiently while waiting for the simulated delay to conclude. Now let's see how we can run our FastAPI application using Uvicorn, a lightning-fast ASGI server. To start the server, we will use a command that specifies our application file and enables automatic reloading for development purposes. This allows our changes to be applied without restarting the server manually. As we execute this command, Uvicorn will launch our FastAPI app, making it accessible for testing. Next, we'll introduce a second endpoint that performs a quick task, demonstrating the non-blocking nature of our asynchronous application. We will declare an endpoint at quick task, which simply returns a message indicating that the task has been completed swiftly. By using the async def syntax, we ensure this function is asynchronous, helping us to maintain performance even under concurrent loads. As both the long and quick tasks are available, we can make requests to the long task endpoint while also hitting the quick task endpoint simultaneously. This showcases the effectiveness of asynchronous programming in handling multiple tasks at once, improving the responsiveness of our application significantly. Now let's see how we can run our FastAPI application using Uvicorn as our ASGI server. To do this, we will use a command specifying the application's entry point and host settings. The command uvicorn main app host 0000 port 8000 reload instructs Uvicorn to serve the FastAPI application found in the main module with the variable app. The host flag set to 0000 allows the server to accept requests from any IP address, making it accessible from the network. The port option specifies that the application will run on port 8000, a common choice for development. Meanwhile, the reload flag is particularly useful during development as it enables automatic reloading of the server every time a change is detected in the source code, thereby streamlining development efforts. In a production scenario, however, we may want to enhance the server's capability to handle multiple requests simultaneously. To achieve this, let's implement the workers option to run multiple worker processes, such as in the command uvicorn main app host 0000 port 8000 reload workers 4. This setup allows our FastAPI application to handle concurrent requests more efficiently, thereby improving performance and scalability under load. Now let's take a look at how to integrate MongoDB with our FastAPI application using the motor library, which facilitates asynchronous database interactions. First, we create a FastAPI application instance and establish a connection to the MongoDB database using async.io motor client, making sure to specify our database's connection string. By using the async.io motor client, we enable our application to handle non-blocking database operations, improving overall responsiveness. Next, we define an asynchronous endpoint at user's userid, which takes a user ID as a path parameter. Inside the endpoint function, we access the user's collection from the database and utilize the await keyword to fetch a user document that matches the provided ID using the findOne method. This is crucial because it allows other operations to continue while waiting for the database response. If the user is found, we extract their name and email and return this data in JSON format. Conversely, if the user isn't found, we return an error message. This setup demonstrates how to retrieve user data effectively while maintaining the benefits of asynchronous programming in FastAPI. Now let's take a look at how we can implement error handling in our FastAPI application when retrieving user data from the database. In this code snippet, we define an asynchronous endpoint for getting user details via a specific user ID. We start by accessing the user collection from our MongoDB database and attempt to find a user matching the provided ID. Importantly, we use the await keyword with the findOne method to ensure that our application remains non-blocking while waiting for the database response. If a user is found, we return their name and email. However, if the user ID does not correspond to an existing user, we utilize FastAPI's HTTP exception to raise an appropriate error. This approach sends back a 404 status code along with a user not found message. This method aligns with best practices for API design, as it not only provides immediate feedback on the requested resources availability, but also enhances the user experience by handling error cases gracefully. Thus, we ensure that clients can adequately manage all possible responses from the API. Now let's see how we can implement concurrent requests in our FastAPI application using the HTTPX library. In the provided code, we create an asynchronous endpoint that fetches user information and their orders by making requests to two different API endpoints simultaneously. We begin by importing HTTPX, which is an asynchronous HTTP client. That app get/userinfo/user-ID decorator defines our endpoint, where userid will be a variable part of the URL that gets passed to the function. Inside the function userinfo, we utilize an async with block to create an instance of HTTPX, async client, ensuring that the client is properly closed after completing our requests. Next, we make two await calls to fetch data from the user information and orders endpoints concurrently. Using await allows other tasks to execute while waiting for the request responses. Once the responses are received, we extract the JSON content for both the user information and orders, and finally return them together in a single JSON response. This approach enhances the performance of our application by reducing the total time taken to fetch related data from different sources, thus demonstrating the power of asynchronous programming in FastAPI. As we wrap up our exploration of asynchronous programming with FastAPI, let's summarize the key takeaways. FastAPI is built on the ASGI specification, enabling it to handle asynchronous requests efficiently. Using an ASGI-compatible server like Uvicorn or Hypercorn allows FastAPI applications to manage multiple connections without blocking, which is vital for responsive web applications. We've seen how to create asynchronous endpoints, simulate long-running tasks, and integrate with databases using async drivers like Motor. Furthermore, we learned how to handle errors properly, utilize concurrent requests with Asyncio, Gather, and ensure our APIs remain fast and reliable. Asynchronous programming can often enhance the performance and scalability of your applications, allowing for an overall smoother user experience. Now you have the knowledge to leverage asynchronous capabilities in FastAPI, opening up new possibilities for developing exciting, real-time web applications. In our next lesson, we'll be focusing on connecting our FastAPI backend with a React frontend, enabling seamless interactions between the two. Get ready for an exciting journey into full-stack development. See you in the next session. FastAPI is not only known for its simplicity and speed, but also for its advanced features that allow developers to build highly performant applications. One of the most exciting aspects of FastAPI is its use of asynchronous capabilities through ASGI, or Asynchronous Server Gateway Interface. This opens up a world of non-blocking operations that maximize the efficiency of web applications. Today, we will dive deeper into these advanced features that give FastAPI its edge. So far, we learned that asynchronous programming enhances the efficiency and responsiveness of applications, particularly within FastAPI, which utilizes the ASGI specification for non-blocking operations. We've successfully created asynchronous endpoints, integrated MongoDB using the motor library, and learned how to handle errors effectively. Additionally, we explored the benefits of making concurrent requests with libraries such as HTTPX, allowing for improved application performance. In the next lesson, we will connect our FastAPI backend with a React frontend for full-stack development. Now we will explore how to take advantage of FastAPI's advanced asynchronous capabilities and use them to create more complex functionalities. At the core of FastAPI's asynchronous capability is its reliance on ASGI. ASGI is the spiritual successor to WSGI, designed with asynchronous programming in mind. Unlike the traditional WSGI applications that are synchronous, ASGI allows for handling multiple requests simultaneously, thus enabling a truly concurrent experience. To set up an ASGI-compatible server, we typically use Uvicorn. It's lightweight and easy to set up, and it will help us to experience the full potential of asynchronous capabilities. Now let's see how we can install Uvicorn, which is essential for running our FastAPI application on an ASGI-compatible server. To start, you will need to use pip, Python's package installer. This straightforward command allows us to quickly set up Uvicorn in our development environment. By installing Uvicorn, we ensure that we can take full advantage of FastAPI's asynchronous features, enabling our application to handle multiple requests concurrently without blocking operations. Once you have Uvicorn installed, you can easily run your FastAPI application. This setup is crucial because it serves as the foundation for testing and deploying our asynchronous capabilities. With Uvicorn, you'll experience the performance benefits that come with asynchronous programming, allowing your application to respond rapidly to user requests, even under heavy load. Now let's take a look at how to start our FastAPI application using Uvicorn, which acts as an ASGI server to run our app asynchronously. To launch the server, we will use a simple command, uvicorn app reload. This command specifies the module in the FastAPI instance we want to run. Here, app refers to our Python file, while the second app is the FastAPI instance created within that file. The reload flag is particularly useful during development, as it enables automatic reloading of the server whenever we make changes to our code. This means we don't have to manually restart the server every time we finish coding a feature, making our workflow much more efficient and seamless. By executing this command, we prepare our application to handle incoming requests asynchronously, leveraging FastAPI's strengths in creating high-performance applications. With the server running, you can begin to test your asynchronous endpoints and see how FastAPI manages concurrent operations effectively. The reload flag allows the server to automatically reload when you make changes, which speeds up your development process. Now your FastAPI application is ready to serve requests asynchronously. The displayed pie chart breaks down the relative emphasis across 5 core FastAPI concepts: asynchronous features 25%, dependency injection 20%, background tasks 15%, CORS management 20%, and webhooks 20%. The largest slice is asynchronous features at 25%, indicating a primary focus on non-blocking, concurrent request handling as the foundational capability. Dependency injection, CORS management, and webhooks each occupy equal 20% slices, signaling that modular architecture, clean dependency management, cross-origin request handling, and integrations for real-time or external event-driven flows are equally important supporting pillars. Background tasks at 15% is smaller but still meaningful, reflecting the role of offloaded post-response processing for tasks like emails, analytics, or file processing. From this distribution, we can conclude that while asynchronous execution is the central strength to prioritize, production-ready FastAPI applications require balanced attention to dependency patterns, secure cross-origin configurations, and webhook integrations, with background tasks complementing these capabilities to maintain responsiveness and operational workflows. Next, we will write a simple asynchronous route in FastAPI to demonstrate how non-blocking operations can enhance server responsiveness. In this example, we define a long-task endpoint using the app_get/long_task decorator, which specifies that this function will handle GET requests to the long task path. Inside this function, we use the await keyword with Asyncio, sleep 5. This simulates a long-running task by introducing a delay of 5 seconds without blocking the server. As a result, while the server awaits this sleep operation, it can still process other requests, which is a significant advantage of asynchronous programming. Once the sleep period concludes, the function returns a response as a JSON object with a message indicating that the task has completed. This approach illustrates how to create efficient, non-blocking endpoints in FastAPI, allowing developers to build applications that can handle multiple operations simultaneously without sacrificing performance. This is particularly useful in scenarios where tasks might take time, such as API calls or data processing. Now let's set up a MongoDB connection dependency inside our FastAPI application. First, we import the necessary modules, FastAPI and depends from FastAPI, and async.io motor client from motor Asyncio to facilitate asynchronous database operations. We create an instance of FastAPI and define our MongoDB connection string. Here, we connect to the MongoDB instance with async.io motor client, establishing a client object that allows us to interact with our database. Next, we implement an asynchronous function named getDB, which returns a reference to our database. This function serves as a dependency that we can easily inject into our root handlers. Now, let's see how we can implement a root to read items from the database. We define a root handler called readItem, which takes an itemid as a path parameter. Inside this handler, we use the injected database dependency to fetch an item from the MongoDB collection using its findOne method. If the document is found, it is returned. Otherwise, a message indicating that the item was not found will be sent back. This modular approach not only promotes clean code and easy testing, but also makes it clear what dependencies each root has. Next, we will implement background tasks in our FastAPI application to log messages while allowing clients to receive immediate responses. We start by importing background tasks from FastAPI, which enables us to execute tasks in the background after sending a response. In our example, we define a function, logMessage, that prints a log statement. Now let's see how we can modify our longTask endpoint to include this background functionality. Within our asynchronous root longTaskWithLog, we utilize the background tasks parameter to add a task that will log the message longTaskStarted. This addition allows the server to proceed with the main task, which simulates a delay of 5 seconds while still queuing the logging operation. What's important here is that the client receives a response with the message task completed almost immediately, even though the logging operation proceeds in parallel. This feature is particularly beneficial for responsive user-facing applications where you want to maintain quick interactions while still performing necessary operations like logging or sending emails in the background. Now let's see how we can implement CORS in our FastAPI application to handle requests from different origins securely. We first import the necessary classes from FastAPI and specifically the CORS middleware to manage cross-origin requests. By creating a FastAPI instance, we set up our application. Next, we add the CORS middleware with several configurations. We specify allow origins equals *, which allows requests from all origins. While convenient for development, be cautious in production and specify exact origins to enhance security. Additionally, we enable credentials, specify allowed methods and headers, which gives flexibility to the types of HTTP requests our application will accept. In the main root, we define a simple asynchronous function that responds with a welcome message. This setup illustrates how CORS can be effectively managed, ensuring that your application remains flexible and secure. By enabling CORS in this manner, you prepare your FastAPI app to interact smoothly with external services, enhancing its usability for various client applications. Next, we will write the following FastAPI code to set up a webhook endpoint that listens for incoming post requests. In this implementation, we first import the necessary components from FastAPI, specifically the FastAPI framework and the request object to handle incoming HTTP requests. We then create an instance of FastAPI, which will serve as our web application. Now let's implement the /webhook post endpoint. This function is defined as asynchronous using the async-def syntax, allowing it to handle requests without blocking the server. When a request is made to this endpoint, it captures the request data using awaitRequest, JSON, which asynchronously retrieves and parses the JSON payload sent to the webhook. This is crucial for real-time integrations, as it allows the application to handle events as they come in. We print the received payload to the console for logging purposes, which can be useful for debugging or monitoring webhook events. Finally, the function returns a simple JSON response indicating that the webhook was received successfully, which helps the sender know that the data was processed. This asynchronous design ensures high performance and responsiveness of the FastAPI server while handling these incoming notifications. As we wrap up, it's vital to understand that FastAPI combines the benefits of asynchronous programming with elegant designs like dependency injection and middleware, making it a fantastic choice for modern web applications. The asynchronous capabilities of FastAPI help developers to build responsive and efficient applications while utilizing features like background tasks and CORS handling. As we transition to the next lesson, we will prepare to integrate our FastAPI backend with a React frontend, further enhancing our project into a full-stack application. This integration will not only solidify what we've learned, but also bring our FastAPI skills into the modern web development ecosystem. Thank you for joining me in this exploration of advanced FastAPI features, and I cannot wait to see you in the next session as we bring our backend and frontend together. Let's dive into Pydantic data validation in FastAPI. In this lesson, we'll explore how Pydantic enhances data validation in our FastAPI applications, streamlining how we handle complex data structures and ensuring that the data flowing through our application is as clean and structured as possible. So far, we have covered how FastAPI takes advantage of asynchronous programming through ASGI to improve application efficiency. We've created asynchronous routes, integrated MongoDB with dependency injection, and employed background tasks for logging operations. Additionally, we've discussed managing CORS requests and implementing webhooks. Now we will talk about Pydantic's role in validating and structuring data seamlessly within FastAPI, making our applications robust and reliable. Now let's see how we can define a simple data model for a user using Pydantic within our FastAPI application. To do this, we start by importing base model and email SDR from the Pydantic library. The base model serves as the foundation for our data model, providing built-in validation and serialization features. We then create a user class that inherits from base model. In this user class, we declare three attributes: ID, name, and email. The id is specified as an integer, while name is defined as a string. For the email, we leverage the email STR type, which ensures that any email address assigned to this attribute adheres to the proper format. This automatic validation simplifies our coding process by catching errors early. With this simple structure in place, we lay the groundwork for validating user input as it flows through our application, ensuring our data is both clean and reliable. Next, we will integrate this model into our FastAPI routes to see how it improves data handling when creating user profiles. Next, we will integrate our user model into a FastAPI route to create an endpoint for adding user profiles. Now, let's create an asynchronous route called createUser, which accepts a user instance as input. This function will be executed when a post request is made to the user's endpoint. FastAPI takes advantage of the user model's schema to automatically validate the JSON payload we receive, ensuring that the data matches the expected structure. If the payload is valid, FastAPI will successfully create the user and respond with a confirmation message and the created user data. For instance, if we send a correctly formatted JSON object containing an ID, name, and a properly formatted email, the endpoint will process it without any issues. However, if we mistakenly provide an invalid email format, such as not an email, FastAPI will return a detailed validation error response, clearly indicating what went wrong with the input. This robust validation capability helps maintain data integrity and ensures a smooth user experience by providing immediate feedback on incorrect data submissions. Now let's take a look at how we can extend our user model to include an address by creating a separate Pydantic model. First, we define an address class which inherits from base model. This class includes fields for street, city, and zip code, all specified as strings. By structuring our data in this way, we not only create a clear and organized model, but also set the groundwork for validation, ensuring that any address passed in must adhere to these requirements. Next, we modify our user class to include an address field which is of type address. This establishes a hierarchical relationship, allowing us to nest the address model within the user model. Now, whenever a new user is created, they can also have an associated address with its own required fields. To see this in action, we'll adjust our FastAPI endpoint to accept a user request containing nested data. When a request is made with a JSON payload including the user's information along with the nested address details, FastAPI automatically validates the entire structure, confirming that both the user and address fields adhere to the defined types. This layered validation simplifies handling complex data structures and enhances the reliability of our application. To complement the nested models discussion, the accompanying figure titled Key Concepts in Pydantic Data Validation in FastAPI summarizes the relative emphasis placed on 5 core topics: Pydantic models 30%, data validation 25%, asynchronous programming 20%, CRUD operations 15%, and JWT authentication 10%. The bar heights and the numeric labels above each bar make the ranking explicit. Pydantic models are the single largest focus, followed closely by data validation, while asynchronous programming occupies a significant but smaller share. CRUD operations and JWT authentication are present but account for the lower portions of the distribution. Reading the chart with its y-axis limited to 0.35% and dashed horizontal grid lines shows that the top 2 concepts together constitute more than half of the emphasis, 55%, and the top 3 combined reach 75%, indicating that model design, validation logic, and async behavior form the core priorities in the lesson. The clear ordering of bars and the exact percentages allow you to conclude that mastering Pydantic models and validation is primary, with asynchronous patterns and standard data operations as important supporting topics, and authentication, JWT, addressed but as a lower priority concern in this specific scope. Now let's take a look at how we can define a data model for an address in our FastAPI application using Pydantic. We introduce an address class that extends base model, enabling us to leverage Pydantic's powerful data validation features. In this model, we define 3 fields, street and city, which are required and thus expect a string, and zip code, which is made optional. By utilizing Python's optional type from the typing module, we allow zip code to either contain a string or default to none if not provided. This means that when our users submit data, they can omit the zip code, and our application will handle it gracefully by assigning it a value of none. This design approach ensures flexibility, as it accommodates user input variations without causing errors or breaking the application. Next, let's explore how this model integrates with incoming JSON data. When a request is sent without the zip code, our application is able to process it seamlessly, maintaining robustness and user-friendliness in data handling. This feature of optional fields is vital for applications that must adapt to varying user contributions. Now let's implement a custom validator to ensure the integrity of the name field in our user model. In the code, we utilize that validator decorator provided by Pydantic, which allows us to define validation logic for specific fields. Here, we've specified a validator for the name field named name must not contain digits. This method will check the value of name every time a user instance is created or updated. Within this validator, we use a simple conditional that examines each character in the provided name. If any character is a digit, we raise a value error with a clear message indicating that names must not contain digits. This approach helps maintain data quality, as it prevents faulty data from entering our system. If a request is made containing an invalid name like John 123, Pydantic will automatically handle this by raising a validation error, thereby reinforcing the constraints we've established for user names. This is a crucial step in ensuring our application processes valid and clean data. Now let's implement the following modifications to our user model for enhanced data validation. We will use Pydantic's constr class to define constraints specifically on the name field. This allows us to both strip any leading or trailing whitespace from user input and enforce that the name contains at least one non-whitespace character. By enforcing these constraints, we guard against common input errors that can often lead to data integrity issues. We will also be maintaining the other fields such as id and email, where id remains an integer and email continues to utilize Pydantic's email str type to ensure that the format of the email address is validated correctly. This combination of built-in and custom validation ensures that we not only shape our user data correctly, but also simplify the process of dealing with malformed input. By incorporating these validations, our application can safely process user data, leading to a more robust and reliable backend. This is particularly crucial in a FastAPI application where data integrity is paramount. As you can see, Pydantic is a powerful ally for data validation in FastAPI applications, offering a wide variety of features out of the box. By taking full advantage of these capabilities, we can ensure that the data our applications process is always validated, well-structured, and safe for use. This level of assurance not only leads to robust back-end operations, but also makes it easier to manage and manipulate data as we build out our applications. In this lesson, we explored Pydantic's essential role in validating and managing data in FastAPI. We learned how to define models, handle complex nested structures, and implement custom validation logic. Pydantic's use of Python types allows for a high degree of flexibility and robustness in managing the data flow of our applications. As we look forward to our next lesson, we will shift our focus to integrating our FastAPI backend with a React frontend. This integration will bring our backend functions to life, allowing us to build full-stack applications that are not only powerful but also user-friendly. Thank you for joining me in this deep dive into Pydantic and FastAPI, and I can't wait to see you in our next session. Today we're diving into an incredibly important topic: deployment strategies for FastAPI applications. Deploying your application effectively is just as crucial as building it. So far, we learned about Pydantic's key role in enhancing data validation within FastAPI applications, allowing us to define clear data models and handle complex structures seamlessly. We discussed how Pydantic automates input validation, reducing errors by using type annotations to enforce data integrity. Additionally, we explored features such as nested models, optional fields, and custom validators, which help ensure that our application processes clean and safe data. In our upcoming lesson, we will focus on integrating our FastAPI backend with a React frontend for full-stack development. Let's jump right into how we can effectively deploy FastAPI applications. Deployment might sound intimidating, but with some clear strategies and tools, you'll find it's a smooth ride. There are various deployment options to consider based on your specific needs, from cloud services and containers to traditional hosting platforms. Each has its own strengths and weaknesses. To deploy our FastAPI application to Heroku, we need to create some essential files. The first one is the procfile, which is crucial for Heroku deployment. This file provides instructions on how to run the application and must include the command for launching the FastAPI app using Uvicorn. The correct format starts with the keyword web followed by the command uvicorn main app host equals 0000 port equals $port minus 5000. This setup allows the application to listen on the port that Heroku dynamically assigns. The next step involves creating a requirements.txt file where we'll list all the dependencies necessary for our application. Specifically, we need to include FastAPI and Uvicorn, which will enable Heroku to install these packages during the deployment process. Now let's move on to logging into Heroku using the Heroku CLI with the command Heroku login. This step is essential for authenticating and enabling interaction with our Heroku account. Once logged in, we can create a new Heroku application by running Heroku create your app name. After establishing the application, we'll use Git for version control, committing our changes with a message and pushing them to the master branch on Heroku. Finally, we can access our live application by executing Heroku open, making the FastAPI application available to users. To create a basic Docker file for our FastAPI application, we begin by defining the base image, which is the official Python 3.9 image. This selection allows our application to function within a controlled environment, ensuring that all necessary Python dependencies are readily available. We then establish the working directory within the container at app, which will house our application code. To facilitate the inclusion of essential dependencies for our FastAPI application, we move the requirements.txt file into this directory. This file enumerates all the necessary packages needed for the application to operate. Subsequently, we execute a command to install these dependencies using pip. This step guarantees that our application is equipped with all it needs while avoiding the retention of any unnecessary cache files, thereby helping to keep the image size small. Once the environment is properly set up, we transfer the remainder of our application code into the container. Following this, we expose port 80 to indicate that it will serve as the listening port for our FastAPI app. Finally, we define the command to launch the application using Uvicorn, configuring it to serve on the 0000 interface, which ensures that it is accessible from outside the container. This configuration allows for smooth deployment across various environments. Figure 1 is a horizontal bar chart titled Deployment Strategies for FastAPI Applications that shows the percentage distribution across 5 deployment methods. Cloud deployment, e.g. Heroku at 40%, containerization, e.g. Docker at 25%, serverless architecture, e.g. AWS Lambda at 20%, local hosting at 10%, and hybrid solutions at 5%. The horizontal orientation ranks methods from top cloud deployment to bottom hybrid solutions, making relative comparisons straightforward. Cloud deployment leads by a clear margin, 15 percentage points above containerization and 20 points above serverless. Containerization and serverless are relatively close, 25% versus 20%, indicating both are commonly adopted but with containerization more prevalent. Local hosting and hybrid solutions occupy the lower end of the spectrum, together representing only 15% of the distribution, which suggests they are niche or specialized choices. The x-axis is scaled to 50%, and each bar is annotated with its exact percentage, enabling quick identification of the absolute differences as well as the dominance of the top 3 strategies: cloud plus containers plus serverless equals 85%. From these proportions, you can conclude that managed cloud platforms and container-based deployments are the most frequently used approaches in practice, with serverless also being significant but less dominant. This implies prioritizing learning and tooling for cloud and container workflows will cover the majority of real-world deployment scenarios, while local and hybrid options remain useful for testing, constrained environments, or particular architectural needs. To install and initialize Zappa, which is crucial for deploying our FastAPI application on AWS Lambda, we first need to add Zappa to our project. This involves running a simple command to install the Zappa package via pip. This step lays the groundwork by ensuring that all the necessary components for our serverless application deployment are properly set up. Following the installation, the next step is to initialize Zappa within our FastAPI project. This is done by executing a command that creates a configuration file called Zappa settings, JSON. In this file, we can define essential settings such as the AWS region and the S3 bucket needed for our static files. By adjusting the parameters in this JSON file, we can customize the deployment process to meet the unique requirements of our application. With the configuration finalized, we can proceed to deploy our FastAPI application using another straightforward command. This command directs Zappa to package our application and establish an Oz Lambda function, while also integrating the necessary API gateway to create an endpoint for our app. Moving forward, any updates to our application can be handled easily with just a single command, allowing us to effectively manage any modifications. This efficient process highlights how Zappa streamlines the serverless deployment of FastAPI applications. Now let's see how we can implement environment variable management in our FastAPI application to ensure sensitive information remains secure. We start by importing the OS module, which provides a way to interact with the operating system, allowing us to read environment variables. Next, we create an instance of the FastAPI application by calling FastAPI. This instance will act as the main entry point for our application and handle incoming requests. To safely manage our database connection string, we use the os-getenv function to retrieve the value of the environment variable named database URL. This approach avoids hard-coding sensitive information directly into our code, improving security and maintainability. In the root endpoint defined with the @app_get/decorator, we create a function called readRoot. When a GET request is made to the root path, this function will execute and return a JSON response containing the database URL we've stored in the database URL variable. This method not only keeps sensitive credentials secure, but also allows for easy configuration changes when deploying to different environments without needing code modifications. Now let's see how we can implement logging in our FastAPI application using the popular Loguru library. First, we import the necessary modules, including FastAPI to create our app and logger from Loguru to handle logging. We then create an instance of FastAPI, which will serve as the entry point for our application. Next, we set up the logger by adding a log file named file.log, where all log messages will be stored. The rotation parameter is used to specify that the log file should automatically rotate when it exceeds 1 MB, ensuring that we don't accumulate too much data and can maintain manageable log files. Now let's implement a route to handle requests to the root endpoint. Inside the root handler function, we log an informational message each time the root endpoint is accessed. This gives us important insight into how often this endpoint is being hit, which can be vital for debugging and monitoring application performance. Finally, the function returns a simple JSON response. By integrating logging in this way, we enhance our application's observability and aid in troubleshooting issues as they arise in a production environment. In conclusion, deploying FastAPI applications can range from simple cloud hosting solutions to sophisticated container or serverless architectures depending on your project needs. Understanding environment management, effective logging, and performance monitoring are essential skills for maintaining a robust application post-deployment. So far, we've covered deployment strategies, including Heroku, Docker, and serverless options utilizing AWS Lambda. Next, we'll bring these servers and deployments into action by integrating our FastAPI backend with a React frontend, leading to full-stack development. Thank you for joining today's session, and make sure to tune in for the next lesson where we transform our backend into a full-fledged application that users can interact with in real time. FastAPI is a powerful web framework for building APIs quickly and efficiently with Python. In this section, we will dive deep into the advanced features of FastAPI, particularly focusing on its asynchronous capabilities. FastAPI leverages the Asynchronous Server Gateway Interface, or ASGI, allowing it to seamlessly handle asynchronous workflows without requiring the direct use of the Asyncio module. This approach opens up a myriad of performance benefits that we will explore, alongside practical examples. Now let's implement an asynchronous API endpoint that will handle requests for external data efficiently. We begin by importing FastAPI and the HTTPX library, which allows us to make HTTP requests asynchronously. Here, we create an instance of the FastAPI application. Next, we define the endpoint async data using the @app_get decorator, indicating that this function will respond to GET requests. Inside the function readAsync data, we utilize the async with statement to create an instance of HTTPX async client. This ensures that the HTTP client is managed properly, automatically closing it once the operations are completed, which is key for resource management. Within this asynchronous function, we make a request to an external API, specifically fetching posts from a placeholder service. The await keyword is crucial here. It allows the application to pause the execution of this function while waiting for the API response, enabling FastAPI to handle other requests during this waiting period. Finally, the JSON response is returned directly, showcasing how FastAPI efficiently manages concurrent requests and improves overall application responsiveness. Now let's implement the following code to explore how FastAPI handles background tasks effectively. Here, we define a function writeLog, which takes a message as an argument and appends it to a file named log.txt. This function is essential for logging notification events without interrupting the main application flow. Next, we create an API endpoint /sendNotification/email that allows us to send notifications to the specified email address. When this endpoint is called, we utilize FastAPI's background tasks feature to run the writeLog function as a background task, thereby adding the logging operation to the task queue. This means that the notification can be sent to the user immediately without requiring them to wait for the logging to complete. By returning a response indicating that the notification has been sent in the background, we improve user experience by ensuring that their interaction with the application remains smooth and responsive. This approach is particularly useful for handling tasks like logging or sending emails, where the processing does not need to block the user from receiving immediate feedback. The figure titled Key Advanced Features of FastAPI presents a bar chart that maps 6 specific features to an importance level on a 1-10 scale. The exact values shown on the bars are asynchronous processing equals 9, background tasks equals 8, dependencies equals 7, middleware equals 6, security, OAuth 2 JWT equals 7, and caching equals 5. From these values, we can draw several conclusions relevant to designing FastAPI applications. Asynchronous processing is identified as the most critical capability, score 9, validating the emphasis on async await patterns and ASGI-based servers described earlier. Background tasks follow closely 8, underscoring their role in offloading non-blocking work such as logging or email sending. Dependencies and security share the same importance level, both 7, indicating that structured dependency injection and robust token-based authentication are equally essential for maintainable and secure APIs. Middleware scores slightly lower, 6, implying middleware is important for cross-cutting concerns but secondary to core async behavior and security. Caching registers the lowest score, 5, signaling that caching is a valuable optimization but typically comes after establishing correct async flows, background processing, dependencies, and security. The numeric labels on each bar and the common 0-10 vertical scale make the relative gaps explicit, notably the 1-point gap between async and background tasks and the broader 4-point gap down to caching, which helps prioritize implementation and optimization steps when planning a FastAPI service. Now let's deepen our understanding of FastAPI's dependency injection by implementing a custom dependency that retrieves user information. We start by defining an asynchronous function called getCurrentUser. This function takes in a user ID and automatically receives a database session through FastAPI's depends mechanism, which allows us to inject dependencies smoothly. Inside this function, we query the database for the user based on the provided ID. If the user is not found, we raise an HTTP exception, effectively managing error responses gracefully. Next, we will see how this dependency can be utilized within an API endpoint. In our example, we create a readUser endpoint that expects a user ID in the URL. By using depends with our getCurrentUser function, FastAPI seamlessly handles the user retrieval process without cluttering our endpoint logic. This design pattern not only promotes cleaner code, but also enhances maintainability, as any changes to user retrieval logic would be centralized in the getCurrentUser function rather than spread across multiple endpoints. This approach demonstrates the power and elegance of using dependencies in FastAPI to keep our code base organized and efficient. Now let's see how we can run our FastAPI application using an ASGI server, specifically Uvicorn. The command to start the server is quite straightforward. You simply specify the file name of your FastAPI application followed by the instance name of the FastAPI class. In this case, we denote main as the file where our FastAPI app resides, and app is the instance that we created with FastAPI. By adding the host and port options, we dictate where the server will listen for incoming requests. Using 0000 allows it to accept connections from any IP address, while specifying port 8000 makes it accessible via that particular port. One significant feature during development is the reload flag. This enables automatic server reloading upon code changes, which saves developers from manually restarting the server every time they make updates. This command ultimately demonstrates the asynchronous capabilities of FastAPI, together with Uvicorn, highlighting how the framework efficiently handles concurrent requests, making it ideal for high-traffic applications. Now let's see how we can implement middleware in FastAPI to enhance our application's capabilities. Middleware serves as a mechanism to process requests globally, allowing us to intervene at various points in the request-response lifecycle. In our example, we define an asynchronous middleware function called logRequests. This function takes two parameters, the incoming request and a callable callNext, which allows us to pass control to the subsequent middleware or endpoint. Within the middleware, we first await the response generated by calling callNext with the incoming request. This means we defer any response construction until the next piece of middleware or the endpoint has been processed. After obtaining the response, we log crucial information, including the HTTP method, the request URL, and the status code of the response, which can be invaluable for tracking and debugging. This logging happens before returning the response back to the client, ensuring we capture every request's details without cluttering individual endpoints. By utilizing middleware effectively, we can implement cross-cutting functionalities like logging or authentication without complicating our root handlers, maintaining clean and efficient code. Now let's see how we can implement a root that effectively handles multiple query parameters for pagination. In our example, the endpoint items is created using a GET request, which allows users to retrieve a list of items. We define two query parameters, skip and limit, where skip is the starting index and limit specifies how many items to return. By setting default values of 0 for skip and 10 for limit, we ensure that these parameters are optional, promoting a more versatile API. Within the function readItems, we create a sample list of items, and we leverage slicing to return only the requested subset based on the skip and limit values. When a user makes a request to this endpoint, the code takes control of pagination by slicing the items list accordingly, a common requirement in many applications. This approach keeps our API organized and user-friendly, allowing clients to request manageable chunks of data easily. Overall, this demonstrates FastAPI's powerful ability to handle complex API routing requirements effectively. Now let's see how we can implement OAuth 2 authentication using FastAPI for our API. We start by importing the necessary components from FastAPI and defining the OAuth 2 password bearer scheme with a specified token URL. This establishes the groundwork for token-based authentication, enabling us to extract and utilize JWT tokens. Next, we define the getCurrentUser function as an asynchronous dependency that automatically retrieves the token from incoming requests via the depends function. Within this function, we implement a simple logic to validate the token. If the token does not meet our expected criteria, here we check against a mocked fake token. The function raises an HTTP exception and returns a 401 unauthorized error, ensuring that only authenticated users can access certain endpoints. Finally, we create the usersMe endpoint that utilizes the getCurrentUser dependency to retrieve the current user's data based on the validated token. If the token is valid, it returns user information, allowing for a secure, token-based interaction with the API. This pattern is essential for building robust, secure applications that require user authentication. Now let's implement a caching strategy to enhance performance in our FastAPI application. In this code, we define a dictionary to hold our cached data and its timestamp, allowing for quick access to potentially expensive or time-consuming operations. When a request is made to the cached data endpoint, our function first checks whether the data is present in the cache and if it is still valid, meaning the request is made within 60 seconds of the last update. If the cached data is still fresh, it returns that data immediately, thus saving the time required for fetching it from a slower source. However, if the cache is either absent or expired, the function utilizes an await keyword to call a hypothetical fetchData function. This would typically connect to a database or external API to retrieve data. Once the data is fetched, it is stored in the cache along with the current timestamp to facilitate subsequent requests. This approach not only improves response times for users, but also reduces the load on the server, showcasing how effective caching can significantly optimize application performance. Now let's see how we can implement a simple FastAPI application and connect it to our MongoDB instance. We start by importing the necessary components from FastAPI, the asynchronous MongoDB client from Motor, and base model from Pydantic for data validation. We initialize our FastAPI app and create an instance of the asynchronous MongoDB client to connect to our local database. Next, we define an item model using Pydantic, which helps in validating incoming data for our API, ensuring that each item has a name, description, and price. Now let's implement the createItem endpoint, which handles post requests to add new items to our collection. This function takes an item as input, converts it into a dictionary, and uses the insert1 method to add it to the database. Upon successful insertion, it retrieves the unique ID generated by MongoDB and includes it in the response, thereby providing useful feedback to the client about the newly created item. This structure ensures that our API is both user-friendly and efficient in handling data storage operations with MongoDB. The displayed pie chart titled Importance of FastAPI Features in MongoDB Integration shows 6 labeled slices representing feature importance values: asynchronous processing, background tasks, MongoDB integration, CRUD operations, security features, and data validation. From the slice sizes and percentage labels, MongoDB integration is the largest slice at roughly 19.6% of the total importance. indicating it is the single most critical aspect when combining FastAPI with MongoDB. Asynchronous processing and CRUD operations appear as the next largest slices, each about 17.6%, emphasizing that handling concurrent requests and implementing reliable create, read, update, delete endpoints are nearly equally central to the integration. Background tasks and security features form two equal intermediate slices at about 15.7% each, showing that offloading long-running work and protecting endpoints are significant concerns that should be planned for alongside core functionality. Data validation is the smallest slice, approximately 13.7%, which, while the least by this ranking, still represents a meaningful portion of importance, highlighting that input validation cannot be ignored. Taken together, the three largest slices, MongoDB integration, asynchronous processing, and CRUD operations, account for more than half of the chart's total importance, tilde 54.9%, suggesting priorities for initial design and optimization efforts. Ensure a solid database integration, design async handling and robust CRUD endpoints first, while also implementing background processing, security, and validation to round out a production-ready API. Now let's implement a function to retrieve all items from the database. We'll define the readItems endpoint, where we use an asynchronous function to access the items collection in our MongoDB database. The async for loop allows us to iterate over the documents efficiently, ensuring that the API remains responsive even when handling multiple requests. As each item is retrieved, we convert its id field from an object id to a string format, as this ensures that the data can be easily serialized into JSON for the API response. By appending each formatted item to a list, we can compile all items in one response that clients can consume. Next, we will write the updateItem function, which allows users to modify existing items using an HTTP PUT request directed at the /item/item-id endpoint. This function retrieves the specified item by its ID, replacing the existing document with the new data provided. Using the replaceOne method means we replace the entire document. If partial updates are needed, one could consider utilizing the updateOne method to apply specific changes instead. This flexibility and functionality is one of the advantages FastAPI offers when working with MongoDB. Now let's implement the delete functionality, which allows users to remove items they no longer need from our application. The deleteItem function is specifically designed to handle HTTP delete requests at the /item/item-id endpoint. It takes an itemid parameter from the URL, which represents the unique identifier of the item we wish to delete. Within the function, we use an asynchronous call to the MongoDB database, leveraging the deleteOne method to attempt to remove the item from the items collection based on its ID. The result of this operation is stored in the result variable, which contains information about the outcome of the deletion. To provide clear feedback to the user, we check the deleted count property of the result. If it equals 1, this indicates that the item was successfully deleted, and we return a message confirming the successful deletion. Conversely, if the count is not equal to 1, it suggests that no item was found with the specified ID, and we return an appropriate message stating that the item was not found. This structured feedback enhances the user experience by clearly indicating the result of their action. Now let's implement the following error handling and validation mechanism for our item creation endpoint. We begin by importing the HTTP exception from FastAPI, which will allow us to raise exceptions with specific status codes when certain conditions are met. In the createItem function, we first check if an item with the same name already exists in the database. This precaution helps maintain uniqueness for items, a crucial aspect for any robust API. If we find a duplicate, we raise an HTTP exception with a 400 status code and a descriptive message indicating that the item already exists. This validation enhances usability for clients of the API as they receive clear feedback regarding their requests. If no duplicates are found, we convert the incoming item data into a dictionary and proceed to insert it into the MongoDB collection. After insertion, we append the newly created item's ID to the item dictionary and return it as the response. This structured approach not only prevents errors, but also ensures that clients of the API receive consistent and informative outputs, reinforcing the overall reliability of our application. Now let's implement a simple pagination mechanism for retrieving items, which is essential as the number of items can increase significantly over time. In the readItems function, we introduce skip and limit parameters, allowing clients to specify which portion of data they wish to receive. This approach helps to avoid overwhelming users with too much information at once, enhancing the overall user experience. The function retrieves items from the MongoDB database by utilizing the find method on the items collection, while employing the skip and limit functionalities to control the number of documents fetched per request. As we loop through the cursor asynchronously, we convert each item's id to a string to ensure it is JSON serializable, since FastAPI requires JSON-compatible responses. By returning only a subset of documents, we not only improve performance but also facilitate smoother navigation through larger datasets. This implementation showcases how pagination can be seamlessly integrated into our FastAPI application, making it both efficient and user-friendly. Now let's see how we can implement categories in our data model to enhance the relationship between items. We begin by defining a new category model, which comprises a single field for the category name. This sets up a structured way to categorize our items, allowing for better organization within our application. Next, we modify the existing item model to include a category field, which is of type category. This integration demonstrates how versatile our data structures can be, taking advantage of MongoDB's flexible schema capabilities. Now let's implement the createItem endpoint to accept this new model. When users send a post request to create an item, the function will first receive the item data, including its associated category. The item data is converted into a dictionary format, allowing us to easily insert it into the MongoDB database. After the item is saved, we retrieve its unique identifier from the database response and include it in the returned result, ensuring that users can see the newly created item's ID. This illustrates the seamless handling of complex data relationships and enhances the functionality of our API as it scales. In conclusion, integrating FastAPI with MongoDB provides a powerful framework for building scalable and efficient web applications. The combination of FastAPI's speed and ease of use with MongoDB's flexibility enables you to create APIs that can handle a variety of data interactions seamlessly. We've created CRUD operations, implemented error handling, pagination, and explored more complex data modeling techniques. As you continue to develop your skills, understanding how to navigate both FastAPI and MongoDB will significantly enhance your full-stack development capabilities. In the next lesson, we will take the next big step by integrating our FastAPI backend with a React frontend, making our API accessible and usable in a full-stack development environment. This opens up many possibilities for enhancing user experiences and creating dynamic web applications, so stay tuned. When deploying FastAPI applications, understanding the various strategies available is essential for ensuring scalability, performance, and reliability. FastAPI is a powerful framework that allows for building APIs quickly and efficiently, but choosing the right deployment strategy is equally important to leverage its full capabilities. So far, we learned about the integration of FastAPI with MongoDB, highlighting the advantages of using MongoDB's flexibility and scalability alongside FastAPI's efficient handling of API requests. We explored basic CRUD operations, implemented error handling, and discussed pagination to improve performance. Additionally, we learned how to structure more complex data models by creating relationships, such as adding categories to items. In our next session, we will dive deep into deployment strategies for FastAPI applications. Now let's take a look at how to create a Docker file for our FastAPI application, which is essential for deploying it on platforms like Oz. This Docker file begins with a base image that includes Uvicorn and Unicorn, two critical components for running FastAPI applications efficiently. By using the Tiangolo/Uvicorn Unicorn FastAPI Python 3.8 image, we ensure that all necessary dependencies are pre-installed, which simplifies our setup process. Next, we copy our application code from the local directory into the Docker containers app directory. This step is crucial as it allows the Docker environment to have access to our application code, making it runnable within the container. Subsequently, we write a command to install any additional Python dependencies listed in the requirements txt file. Using the no cache dir option optimizes the Docker image size by preventing caching of installed packages, ensuring a more efficient build process. Lastly, we expose port 80. This makes our FastAPI application accessible over the standard HTTP port, allowing it to receive traffic once deployed. This Docker file essentially sets up the environment needed to run our FastAPI application smoothly in a containerized setup. Now that we have the Docker file set up for our FastAPI application, let's proceed to build the Docker image and push it to Amazon Elastic Container Registry, ECR. First, we will execute a command to build the Docker image, naming it my FastAPI app. This command compiles the application code and dependencies defined in the Docker file into a portable image that can run in any Docker environment. Next, we need to tag the image using a specific format required for ECR. This involves replacing placeholders with your Oz account information, ensuring that the image is properly identified in the ECR repository. Tagging is crucial as it allows ECR to recognize and manage different versions of your application image efficiently. Finally, the last step will be to push the tagged image to ECR. By executing the push command, we upload our Docker image to the specified registry, making it available for deployment on Oz services like Elastic Beanstalk. This process makes our FastAPI application ready for scaling and managing in the cloud, providing a foundation for a robust deployment strategy. Now let's take a look at how to create a deployment YAML file to deploy our FastAPI application on Kubernetes. In this configuration, we start by specifying that we are using the apps v1 API version and declare our resource as a deployment. The name of our deployment is set as FastAPI app, which will help us identify it within the Kubernetes cluster. Next, we configure the number of replicas to 3, meaning that 3 instances of our application will run concurrently. This is a key feature that helps distribute incoming requests, ensuring your application can handle higher traffic loads efficiently. The selector section is essential for managing which pods belong to this deployment, and it uses labels to match the specified app, FastAPI. We then define the pod template. Within this template, we set the metadata to include the same app, FastAPI label, allowing Kubernetes to manage these pods effectively. In the spec, we define the container that will run our application. Here, we specify the container's name, the Docker image from our container registry, and the port that the container will expose for HTTP traffic. This YAML file provides a clear structure for managing the deployment of our FastAPI application seamlessly on Kubernetes. Now let's implement the necessary configuration to expose our FastAPI application to external traffic using a Kubernetes service. We start by defining a service in our service YAML file. This configuration specifies that the service will act as a load balancer, managing incoming requests to our FastAPI application. In this service YAML, we designate a metadata name for the service called FastAPI service, which uniquely identifies it within the Kubernetes cluster. The spec section outlines how the service should behave, starting with a selector that matches the labels of the deployment, specifically those labeled as app FastAPI. This ensures the service can correctly route traffic to the appropriate application pods. Next, we define the ports that the service will listen on. Here, it's configured to accept traffic on TCP protocol via port 80 and to route it to the appropriate target port, which is also 80 in our application. Finally, with the type set to load balancer, Kubernetes will provision an external load balancer, assigning a public IP address for users to access the FastAPI application. This configuration allows us to ensure that our application is properly accessible to users outside of our Kubernetes cluster. After this, we can deploy the service alongside our application, enabling the full functionality in production. Now let's implement a serverless FastAPI application using AWS Lambda and the Mangum library. First, we need to install Mangum, which acts as a bridge between our FastAPI application and the AWS Lambda environment, enabling it to handle Oz events seamlessly. Next, we'll set up our FastAPI application. We begin by importing the FastAPI module in Mangum. With the instantiation of the FastAPI app, we define an endpoint using the @app_get/decorator, which specifies that a GET request to the root URL will trigger the readroot function. This function simply returns a JSON response with a friendly greeting. Finally, we wrap our FastAPI application with Mangum by assigning it to the handler variable. This step is crucial as it allows Lambda to invoke our application in response to incoming requests. Once everything is in place, you'll package your application along with its dependencies and deploy it to AWS Lambda, where it will automatically scale based on incoming traffic, ensuring efficiency and cost-effectiveness. This setup provides an effective way to run FastAPI applications in a serverless environment. Now let's implement logging capabilities in our FastAPI application to monitor its activity effectively. First, we import the logging module along with FastAPI. By configuring the logging with a basic setup at the info level, we ensure that all informational messages generated by the application will be captured, allowing us to track key events as they occur. Next, we create an instance of FastAPI, establishing our web application. One of the essential aspects of monitoring applications is logging important events, which we achieve here through a logger instance linked to the current module's namespace. This will be utilized throughout our application to record relevant actions. In the root endpoint, we define an asynchronous function that responds to incoming GET requests. Within this function, we immediately log when the endpoint is accessed, marking it as an important event in our application's flow. Finally, the function returns a simple JSON response announcing that the Hello World message was generated, demonstrating successful interaction with our API. By implementing these logging features, we effectively set the stage for ongoing application monitoring and troubleshooting in our deployed environment, making our FastAPI application more robust and reliable. Finally, let's not forget about security and performance optimization during deployment. Security best practices involve using HTTPS, validating input data thoroughly, and managing access control effectively. For example, with FastAPI, you can ensure that sensitive endpoints are protected properly using security dependencies. Regarding performance, utilizing caching mechanisms can significantly speed up your application. FastAPI can be integrated with caching services such as Redis or Memcache to cache frequent responses. To wrap it up, deploying FastAPI applications presents multiple strategies, each with its pros and cons. You can evaluate the specific needs of your application, such as scalability, traffic patterns, and ease of management to determine the most suitable deployment method. In conclusion, no matter which deployment strategy you choose, ensure to prioritize monitoring, optimize for performance, and secure your applications from potential threats. Now that we have explored the various deployment strategies for FastAPI applications, we're set to take our next step into integrating our backend with a React frontend, creating a seamless user experience in our full-stack development journey. Be ready for some exciting developments ahead. Now let's talk about deployment considerations for production environments when working with FastAPI. Deploying your applications isn't just about moving code to a server. It involves a careful selection of strategies to ensure performance, reliability, and security. Today, we'll explore vital aspects of deployment, including key practices that will benefit your deployments and help you prepare for successful production launches. Now let's see how we can set up a basic FastAPI application using the code provided. Here, we start by importing the FastAPI class from the FastAPI module, which serves as the foundation for our application. Next, we create an instance of FastAPI, naming it app. This instance will handle all our incoming requests. We then define a simple endpoint using the @app_get/decorator, which specifies that this function should be triggered when a GET request is made to the root URL /. Within this endpoint, we implement an asynchronous function called readRoot that returns a JSON response containing a greeting message, "Hello, world." This is a basic yet functional example of how FastAPI operates, highlighting its ability to work with asynchronous operations for improved performance. Finally, the application is executed through the unicorn run function, which runs the app on host 0000 and port 8000. This setup allows for asynchronous handling of multiple requests, showcasing FastAPI's efficiency and responsiveness in real-world applications. Now let's implement a Docker file to containerize our FastAPI application. In this Docker file, we begin by specifying the Python base image, which serves as the foundation for our application. We set the working directory to app, ensuring that all subsequent commands will run within this context. Next, we copy the requirements .txt file into the container. This file lists all the dependencies necessary for our application to run successfully. Following that, we execute a command to install these requirements using pip, with the no cache dir option to keep the image size minimal by avoiding caching of package installations. After installing the dependencies, we copy the entirety of our application code into the container. Finally, we define the command to run our FastAPI application using Uvicorn, specifying the host and port for it to listen on. This setup effectively allows anyone with Docker to build and run the FastAPI application consistently across different environments, simplifying deployment and ensuring that everything operates smoothly. Now, let's see the commands for building and running our Docker image. The first command builds the image, while the second runs it in detached mode, mapping port 80 of the container to port 80 of the host. Now let's take a look at how to define a Kubernetes deployment for our FastAPI application. In this YAML configuration file, we start by specifying the API version and the kind of resource we are creating, which is a deployment in this case. We give our deployment a name, FastAPI deployment, to uniquely identify it in the Kubernetes cluster. The spec section outlines the desired state of our deployment, indicating that we require 3 replicas of our FastAPI application. This replication ensures that our application can handle increased traffic and provides high availability. If one pod fails, Kubernetes will automatically replace it with a new one. Next, we set up the selector, which helps Kubernetes find which pods it should manage based on the labels. In our template, we specify metadata labels for the containers, labeled as app, FastAPI, to allow for consistent identification. Moving on to the spec of the template, we detail the container specifications. Here we define the container's name as FastAPI, specify the Docker image to be deployed, myFastAPI app latest, and indicate that the container should listen on port 80. This configuration sets the foundation for deploying multiple instances of our FastAPI application effectively, automating scaling and management through Kubernetes. Now let's implement a simple JWT authentication system to secure our FastAPI application. First, we import necessary classes and functions from FastAPI and passlib to handle authentication. We initiate our FastAPI application and create a mock user database containing user details, including a hashed password for security. Next, we define the OAuth to password bearer, which helps manage user authentication through bearer tokens and set up the password hashing context using passlib. The verify password function compares plaintext passwords with their hashed versions, ensuring that user credentials remain protected. We then write the getUser function to check if a user exists in the database, facilitating easy user retrieval. The crux of the authentication logic lies in the login endpoint, where we handle incoming login requests. This endpoint checks if the username and password are correct, raising an HTTP exception if either is invalid. If successful, it returns an access token, allowing authenticated users to access protected resources. This setup not only secures our application, but also aligns with best security practices for production environments, ensuring that sensitive information remains protected from unauthorized access. Now let's implement logging middleware in our FastAPI application to keep track of incoming requests and outgoing responses. This middleware will log each request's path and HTTP method, which is essential for understanding how users interact with your application. As requests come into the application, we create a logger using Python's built-in logging module, setting it to log at the info level to capture relevant events without overwhelming verbosity. Next, we define the middleware function that will intercept requests. Upon receiving a request, it logs the request path and method so that developers can review user interactions. Afterward, we pass the request to the next layer in the application using the callNext function, which processes the request further and returns a response. Once we have the response, we log its state as code. This comprehensive logging strategy helps identify issues, monitor performance, and analyze user engagement. By maintaining this logging middleware, we ensure that our application remains transparent and manageable, which is particularly useful when troubleshooting or optimizing performance in a production environment. Next, we will implement a simple caching mechanism within our FastAPI application to enhance performance. This approach leverages an in-memory dictionary to store frequently accessed data temporarily, reducing load times for repeated requests. In this implementation, we first define a dictionary named cache to hold our cached data, allowing us to quickly retrieve previously requested items. The main endpoint data accepts an itemid as a query parameter. When a request comes in, the code first checks if the requested itemid already exists in the cache. If it does, the cached data is returned immediately, which avoids time-consuming operations and improves response speed. If the requested item isn't found in the cache, the code simulates a slow database call using a sleep function. This represents a time-consuming process, which we want to avoid during subsequent requests. After the simulated delay, the data is generated, stored in the cache for future reference, and then returned. This method optimizes how our application handles requests, contributing to a better user experience and increased efficiency overall. In conclusion, deploying a FastAPI application entails several considerations that must align with your expectations for performance, security, and maintenance. Choosing the right server, containerization, orchestration, and implementing security measures are foundational to a successful deployment strategy. Moreover, employing logging and monitoring tools alongside optimization techniques will ensure that your FastAPI application remains robust and efficient in production. Ultimately, integrating all these elements with the sync capabilities of FastAPI forms a powerful stack capable of handling modern web application demands. As we wrap up this exploration of deployment considerations, our next lesson will focus on integrating our backend FastAPI application with a React frontend. With those skills, you'll be well on your way to mastering full-stack development with Python, FastAPI, and React. Let's dive into the advanced features of FastAPI, a modern web framework that's revolutionizing how we build APIs in Python. With FastAPI, we leverage an asynchronous server gateway interface, or ASGI, which enables us to create highly efficient, non-blocking applications. This lesson aims to unravel the hidden capabilities of FastAPI and provide you with the tools to harness its full potential. So far, we learned about the essential considerations for deploying FastAPI applications, including server selection, containerization with Docker, and orchestration with Kubernetes to ensure scalability and reliability. We've also discussed the importance of securing endpoints using authentication mechanisms, as well as the role of logging and monitoring tools in maintaining application health. Performance optimization techniques, such as caching, were emphasized to enhance user experience. Our next lesson will focus on integrating the FastAPI backend with a React frontend for full-stack development. FastAPI uses ASGI, and combined with an ASGI-compatible server like Uvicorn or Hypercorn, allows us to run asynchronous workflows without needing to import the Asyncio module directly. This is one of the standout features of FastAPI, its ability to seamlessly handle multiple requests concurrently. This concurrency is particularly useful when managing I/O-bound operations such as querying databases or calling external APIs, as it keeps our application responsive. Now let's see how we can implement an asynchronous endpoint in FastAPI to fetch data from an external source. We begin by importing the FastAPI framework and the HTTPX library, which allows us to make asynchronous HTTP requests. We then create an instance of FastAPI named app, which will serve as the main application. Next, we define an asynchronous route at external using the @appget decorator. This function, fetch external data, utilizes the async with statement to create an instance of HTTPX sync client. This context manager allows us to perform asynchronous operations while ensuring proper resource management. Inside this context, we use the await keyword to call client.get, making a request to an external API that intentionally introduces a delay. By using await, we ensure that our application does not block while waiting for a response. Instead, it remains responsive to other incoming requests. Finally, once the response is received, we return the data parsed as JSON. This example not only demonstrates FastAPI's asynchronous capabilities, but also illustrates how to maintain application efficiency, allowing for smooth handling of multiple client requests concurrently. Now let's take a look at how we can implement a database connection in FastAPI using its powerful dependency injection system. First, we define a database class that initializes a database connection. This class will manage our connection details, returning a message once the connection is established. Next, we create the getDatabase function, which serves as a dependency. This function initializes an instance of the database class and uses a generator to yield the database connection. The try block ensures that any necessary cleanup can occur in the finally section, which is where you would typically close the connection when it's no longer needed. Finally, we define the items endpoint with an asynchronous function, readItems. By using the depends function to inject the database connection, FastAPI automatically provides an instance of the database class whenever this endpoint is hit. The response returned includes the database connection message, demonstrating how FastAPI simplifies resource management and promotes cleaner modular code. This approach not only enhances maintainability, but also facilitates easier implementation of other features such as authentication and logging in future projects. Now let's see how FastAPI integrates data validation and serialization using Pydantic models. We start by importing the base model class from Pydantic, which serves as the foundation for our data model. In this example, we define a class called item that specifies the required structure for the data we expect to receive, including attributes like name, price, and an optional isOffer boolean. Next, we create an endpoint at the path items that responds to post requests. This endpoint is defined as an asynchronous function, createItem, which takes an item of type item as input. When a client sends JSON data to this endpoint, FastAPI automatically handles the parsing and validation based on the specifications provided in the item model. If the input data matches the defined structure, the function executes and returns a JSON response containing the item name, price, and offer status. This streamlined validation process not only reduces boilerplate code, but also significantly enhances the reliability of our API. FastAPI will automatically return a 422 unprocessable entity response if the data does not conform to the model, pinpointing the validation issues that need to be addressed, which simplifies debugging and improves overall data integrity. Now let's see how we can implement background tasks in FastAPI to enhance user experience during asynchronous operations. In this example, we define a function called sendWelcomeEmail that simulates sending an email to the user. This function is essential as it allows us to manage tasks that don't require immediate feedback to the user, thereby keeping the request response cycle lightweight. Next, we create an endpoint for user registration by defining the registerUser function, which takes an email address and a background tasks object as parameters. The background tasks object is a built-in dependency provided by FastAPI that enables us to run certain tasks after the response has been sent. In this case, we utilize the addTask method to queue our email sending function, allowing the server to send the welcome email without blocking the user's registration response. By utilizing this pattern, users receive an immediate success message upon registration, while the email is processed in the background. This approach exemplifies how FastAPI optimizes asynchronous operations, making APIs faster and more user-friendly, particularly in scenarios where response time is crucial. Next, we will implement a simple router to handle user-related operations within our FastAPI application. By creating a dedicated router, we can keep user-specific endpoints organized and separate from the main application logic, improving maintainability as our codebase grows. In this example, we initiate the creation of a router using the API router class from FastAPI. We define a route to handle GET requests at the user's endpoint. This asynchronous function responds to incoming requests by returning a list of user objects, each containing a username. Finally, we include this router in the main application instance with a specified prefix, /API/v1, enabling us to version our API effectively. This approach allows for better management of API changes over time, ensuring that existing clients continue to function as we evolve and enhance our service. Overall, this modular routing method helps in creating a clearer organizational structure for the application, positioning us well for further development. Now let's implement a WebSocket endpoint in FastAPI. In this piece of code, we define a WebSocket route at the path /WS. When a client connects to this endpoint, the first action is to accept the connection with await WebSocket accept. This establishes a full duplex communication channel, allowing messages to flow in both directions. Next, we enter an infinite loop where we await incoming text messages from the client using await WebSocket receive text. This method enables our application to wait for a message to arrive without blocking other connections. After receiving a message, we immediately send an acknowledgement back to the client with await WebSocket send text, echoing the received message prefixed with message text was. This design allows us to create interactive applications, such as real-time chats or notifications, where multiple clients can communicate seamlessly with the server. The asynchronous capabilities of FastAPI ensure that handling numerous WebSocket connections remains efficient, allowing for rapid updates and responsiveness without performance issues. Now let's take a look at implementing CRUD in our FastAPI application, which will help manage cross-origin requests from different front-end domains. We begin by importing CRUD's middleware from FastAPI's middleware package. This middleware is essential for specifying rules about which origins are allowed to access your API, addressing potential CRUD errors that might arise when your backend and frontend are hosted on different domains. Next, we add the middleware to our FastAPI app using the addMiddleware function. Here, we set allow origins to allow all origins by using an asterisk, but you can also specify specific domains for enhanced security. We also enable allow credentials, which permits cookies and authentication headers to be included in requests, and set allow methods and allow headers to allow any HTTP methods and headers, respectively. This setup balances flexibility and security, ensuring that our API can interact with various frontends while maintaining crucial control over which requests are permitted. By incorporating this middleware, we streamline our development process and mitigate CRUD-related hiccups. Now let's implement the event handlers for application startup and shutdown in FastAPI. By utilizing the addAppOnEvent decorator, we can define functions that execute during specific events in the lifecycle of our application. In this example, we define two asynchronous functions, startup event and shutdown event. The startup event function is triggered when the application starts, allowing us to initialize necessary resources. For instance, this could involve establishing database connections or loading configurations critical for the application's operation. The printed message, application startup, serves as a simple feedback mechanism, indicating that the startup sequence has begun. Conversely, the shutdown event function is invoked when the application is taken down. This provides an opportunity to perform cleanup actions, such as closing database connections or other resources in use. The message, application shutdown, informs us that the application is gracefully shutting down, ensuring a smooth transition and preventing data loss or corruption. These event hooks enhance the application's reliability and maintainability by neatly organizing initialization and cleanup logic in one place. To wrap up, we've explored many advanced features of FastAPI that enhance its capabilities for building modern, high-performance web applications. From asynchronous workflows to dependency injection, automatic validation, background tasks, modular routing, real-time communication via WebSockets, and extensive customization options, FastAPI proves to be a versatile and powerful framework. In the upcoming lessons, we will continue to deepen our knowledge by integrating the FastAPI application with a React frontend, allowing us to see how this powerful backend interacts seamlessly with dynamic user interfaces. FastAPI is just the tip of the iceberg on your journey towards mastering full-stack development. To get started with FastAPI, we are going to walk through the installation process and create a minimal API. FastAPI is an exciting framework that allows you to build APIs quickly and efficiently with Python. It leverages modern Python features for optimal performance, all while being incredibly user-friendly. Now, let's delve into the details. Now let's take a look at how we can check our Python version to ensure compatibility with FastAPI. First, we use a simple command in the terminal, Python version. This line will display the current version of Python installed on your system, which should be 3.6 or above for FastAPI to function properly. Next, we'll implement the installation of FastAPI and its recommended ASGI server, Uvicorn. By executing the command pip install FastAPI Uvicorn, we download and set up both packages in our environment. This step is crucial, as it prepares the framework and server needed to run our API. After installation, it's essential to verify that both packages are correctly installed. We do this by running piplist, which provides a list of all installed packages in our environment. When you see FastAPI and Uvicorn listed, it confirms that the installation was successful, allowing you to move forward with creating your FastAPI application. This setup provides a solid foundation for building robust APIs with efficient performance. The figure displays a bar chart titled FastAPI Installation Steps Duration that breaks down the time spent in minutes across 5 sequential installation tasks. check Python version 2 minutes, install FastAPI 5 minutes, install Uvicorn 3 minutes, verify installation 2 minutes, and create first endpoint 4 minutes. Reading the bars left to right shows that installing FastAPI is the single longest step at 5 minutes, followed by creating the first endpoint at 4 minutes and installing Uvicorn at 3 minutes. Checking the Python version and verifying installation each occupy 2 minutes. Summing these values gives a total of 16 minutes for the entire sequence, meaning install FastAPI accounts for about 31.25% of the total time, create first endpoint about 25%, install Uvicorn about 18.75%, and the 2 verification steps about 12.5% each. From these patterns we can conclude that package installation, FastAPI plus Uvicorn, constitutes half of the setup time, while writing and verifying the first endpoint are significant but smaller portions. The chart's data labels on top of each bar make these comparisons explicit and emphasize where most of the initial effort lies. So when planning a setup or demo, you should expect the bulk of the time to come from downloading and installing dependencies, and then allocate the remaining time to implement and verify your first route. Now let's see how we can implement our FastAPI application by writing the necessary code. First, we start by importing the FastAPI class from the FastAPI library, which allows us to utilize the framework's capabilities. Next, we create an instance of FastAPI, naming it app. This instance acts as our web application and serves as the entry point for defining our API's routes. Next, we will define our first endpoint using a Python function. In FastAPI, we can create endpoints by associating functions with HTTP methods, so we use that app get/decorator to specify that this function will respond to GET requests made to the root URL / the function readRoute will return a JSON response with a simple greeting, "Hello World." This automatic serialization of the response is a powerful feature of FastAPI, allowing us to focus more on building functionality. To run our application, we will use Uvicorn, an ASGI server recommended for FastAPI. By executing the command with the reload flag, our application will automatically restart upon code changes, facilitating a smoother development experience. Now we're ready to see our API in action. Now let's see how we can implement an additional endpoint to personalize our API's responses further. We'll create a GET endpoint called /greet/name, which utilizes path parameters to accept a user's name directly from the URL. This allows us to return a personalized greeting based on the provided name. When a user navigates to a URL formatted like http://127.0.0.18000/greet/alice, the function we define will produce a response tailored to that specific name. In our implementation, we declare the greet function taking name as a string parameter. The function then constructs a JSON response that includes a message saying, "Hello, name," where name is dynamically replaced with the user's input. This feature showcases how easy and intuitive FastAPI is for creating dynamic endpoints, making web applications more interactive and engaging for users. With this setup, your API can easily respond to requests with messages that feel personal and warm, enhancing user experience significantly. Now let's implement an endpoint that utilizes query parameters in FastAPI, allowing for personalized greeting messages. We define a GET endpoint at the path custom greet, which requires a name parameter and has an optional query parameter called message. This setup enables users to customize their greeting by providing a different message if they choose. If we access the endpoint with both parameters, such as http://127.0.0.18000/custom greet/name equals Bob and message equals hello, the application will respond with a structured JSON object that includes the personalized greeting, indicating hello Bob. This showcases how FastAPI efficiently handles input and produces outputs in a user-friendly manner. Conversely, if a user omits the message parameter, like in the request http://127.0.0.18000/custom greet/name equals Bob, the endpoint defaults to using welcome as the greeting message. Thus, it returns welcome Bob in the JSON response. This flexibility in handling query parameters demonstrates FastAPI's power and simplicity, allowing developers to create versatile and interactive APIs that cater to user preferences seamlessly. Now let's discuss how to create a data model for our API using Pydantic, which is integral to FastAPI for data validation and serialization. First, we'll import base model from Pydantic, which serves as the foundation for our models. Next, we'll set up a user model defining 3 attributes: name, email, and age, each with their corresponding data types: string for both name and email, and integer for age. This structure not only helps in organizing our data, but ensures that any incoming data adheres to these specifications. Now let's implement an endpoint that will utilize this user model. By decorating a function with @app_post/user/, we designate this function to handle post requests sent to the user's path. The function takes a user parameter of type user, allowing FastAPI to automatically validate the incoming JSON data against our model. If the data is valid, the endpoint processes the request and returns a confirmation message that includes the name of the newly created user. This showcases how FastAPI efficiently handles data validation while providing clear feedback for successful operations and potential errors. Now let's see how we can implement a personalized greeting endpoint in our FastAPI application. We will define a GET endpoint that takes a path parameter, allowing users to enter their names directly in the URL. By using the decorator @app_get/greet/name, we establish a clear route where name serves as a placeholder for user input. The function greetName_str will then accept this parameter, which is typed as a string to ensure that FastAPI knows we expect the name as input. When a request is made to this endpoint, for instance, if a user navigates to http://127.0.018,000/greet/alice, the application will respond with a JSON object containing a personalized greeting. The expression message fhello name utilizes an f-string to dynamically create a friendly message tailored to the user's input. This method not only makes the API interactive, but also illustrates how user input can be captured and used within FastAPI. By providing a summary and description in the endpoint decorator, we enhance the automatic documentation generated by FastAPI, making it easier for users and ourselves in the future to understand the purpose and functionality behind this route. Now let's take a look at adding error handling in our FastAPI application. We begin by importing the HTTP exception class from FastAPI, which facilitates the creation of custom exceptions. Next, we define a new endpoint that allows us to retrieve user information based on their user ID. This endpoint takes a path parameter userid, which will be passed into the function as an integer. Within the function, we check if the provided user ID exists in a hypothetical user database, usersDB. If the user ID is not found, we raise an HTTP exception with a status code of 404, along with a detail message stating user not found. This mechanism effectively informs the client that the requested resource does not exist. If the user ID is valid, the function pulls the user information from the database and returns it. This approach not only makes our API more robust by handling potential errors gracefully, but it also enhances the user experience by providing clear error messages for common issues like missing users. Now let's implement CORS, cross-origin resource sharing, in our FastAPI application to facilitate seamless interaction between our frontend and backend. To begin, we need to install the Starlet package, which provides the necessary middleware for handling CORS. This middleware will enable our FastAPI instance to accept requests from different origins, a critical feature for full-stack applications involving a React frontend. Next, we'll add the CORS middleware to our FastAPI application. We do this by importing the CORS middleware from Starlet middleware CORS and then calling appad middleware. Here, we specify several parameters. Allow origins equals asterisk indicates that requests from any origin are permitted. This is convenient during development, but should be tailored to your specific security needs in production environments by listing only trusted origins. Additionally, allow credentials equals true is set to allow credentials, while allow methods equals asterisk and allow headers equals asterisk permit any HTTP methods and headers in incoming requests. By configuring this middleware properly, we ensure that our FastAPI application can interact effectively with our React frontend, making it easier to test and develop a robust full-stack application. Wrapping up, we've walked through installing FastAPI, creating endpoints, handling user input, validation with Pydantic, and even talked about error handling and CORS configuration. This basic setup is just the beginning of what you can achieve with FastAPI. So far, we've covered a lot, including building a simple API and handling user data. We'll continue to explore the integration of FastAPI with React for full-stack development in upcoming lessons. The excitement only builds from here. Keep experimenting with different endpoints and features, and soon you'll be crafting APIs like a pro. In this lesson, we will explore best practices for error handling in FastAPI. Error handling is a critical aspect of developing robust APIs, ensuring that you communicate effectively with clients when things don't go as planned. Today, we'll dive deep into various error handling strategies, complete with code examples and explanations to help you understand each concept. So far, we learned about FastAPI, including its installation process and the creation of basic API endpoints. We explored functionalities like handling user input, data validation with Pydantic, and error handling to create a robust application. Additionally, we discussed the importance of cores for front-end backend communication and the automatic documentation generated by FastAPI. As we move forward, we'll integrate FastAPI with React for full-stack development. Now let's take a look at how to implement a simple user retrieval endpoint in FastAPI. In this code, we start by importing the necessary components from FastAPI and initializing our application. We create a mock database, UsersDB, represented as a dictionary containing user IDs and their corresponding information. Next, we define an API endpoint that allows clients to retrieve user information based on their user ID. Specifically, we use that app get/user/user ID decorator to specify that this endpoint responds to GET requests at the /user/user ID URL path, where userid is a path parameter indicating the ID of the user we want to retrieve. Inside the readUser function, we check if the provided userid exists in our UsersDB. If the user ID is not found, we raise an HTTP exception with a 404 status code, along with a detail message stating user not found. This approach adheres to clear error handling practices, ensuring clients receive informative feedback when they request a non-existent user. If the user ID is valid, we return the corresponding user information, giving clients the data they requested in a straightforward manner. Now let's see how we can implement user creation using a Pydantic model in FastAPI. Here we start by defining a user model that enforces data types through Pydantic's base model. This includes 3 attributes: name, which is a string; email, which utilizes email str for email validation; and age, which is an integer. By enforcing these data types, we ensure that any incoming user data adheres to the expected format, minimizing the risk of invalid submissions. Next, we create an endpoint at the user's URL to handle post requests for creating a user. The endpoint function, createUser, takes an instance of the user model as a parameter. FastAPI automatically validates the incoming JSON data against the user model attributes. If any validation fails, a 422 status code is returned, along with detailed error messages. This built-in response system helps clients promptly correct their requests. Lastly, on successful creation, the endpoint returns a message confirming the user has been successfully created, enhancing user experience by providing immediate feedback on their actions. Next, we'll implement a custom exception handler for HTTP exception in our FastAPI application. This allows us to standardize error responses across the API, ensuring that clients receive consistent information when issues arise. We start by defining an asynchronous function called HTTP exception handler, which takes 2 parameters: request, representing the incoming request object, and exc, the HTTP exception instance. Within this function, we create a JSON response that will format our error message. The response will include the status code from the original exception, alongside a structured JSON object containing 3 key pieces of information: a message detailing the error, the HTTP method used for the request, and the path of the request being made. This additional context not only aids clients in debugging their requests effectively, but also enhances the overall user experience by providing uniform error handling. Now let's see how this structure can assist in maintaining clarity while troubleshooting issues in our application. This approach facilitates clearer communication with clients, ultimately leading to a smoother interaction with the API. Next, we will implement a global exception handler for our FastAPI application. This handler will catch unanticipated errors that may occur, ensuring that our application can manage unexpected issues gracefully. We start by importing the necessary modules from FastAPI and the logging library. The AddApp exception handler exception decorator designates the following function as the global exception handler for all exceptions that aren't caught by other handlers. The general exception handler function takes two arguments: the request, which holds the request data when an error occurs, and exc, which captures the exception itself. Within this function, we log the error details for troubleshooting purposes using the logging error function. This allows us to monitor issues that may arise during application execution without crashing the entire service. To provide feedback to the clients, we return a JSON response with a status code of 500, which indicates an internal server error. The response includes a user-friendly message, advising them to try again later. This approach enhances user experience by preventing confusion while maintaining robust error logging for the developers. Now let's implement a basic logging setup to help monitor error responses in our FastAPI application. We begin by configuring a logger using Python's built-in logging module. The basic config method sets the logging level to error, meaning only error messages will be captured. We specify that logs will be written to a file named apperrorslog, allowing us to keep a record of errors that occurred during runtime. The format for the log entries includes a timestamp, severity level, and the actual error message, making it easier to diagnose issues later. Following this setup, we define a global exception handler for any unhandled exceptions that may arise within our application. This handler asynchronously receives the request and the exception that was raised. Inside the handler, we log the error using the error method, which captures the message detailing the unhandled exception. To provide feedback to the client, we can also return a generic HTTP 500 error message, informing them that an unexpected issue has occurred. This structured approach not only aids in error tracking, but also enhances the overall stability and reliability of your FastAPI application. The figure titled Importance of Best Practices for Error Handling in FastAPI presents a horizontal bar chart ranking 5 error handling strategies on a 1-10 importance scale. The bars correspond to built-in error handling 9, validation with Pydantic 8, custom exception handler 7, logging and monitoring 8, and background tasks for notifications 6. Key patterns visible are 1. Built-in error handling is rated highest 9, indicating it should be the primary focus when designing APIs. 2. Validation with Pydantic and logging and monitoring are tied at an importance level of 8, highlighting that input validation and observability are both essential and closely ranked in priority. 3. Custom exception handlers occupy a middle position, 7, showing they are valuable for consistency and additional context but come after core validation and built-in mechanisms. And 4. Background tasks for notifications score lowest, 6, suggesting asynchronous notification workflows are useful but less critical than direct error detection, validation, and logging. Each bar includes a numeric label at its end, the importance value, clarifying the exact ranking and reinforcing the conclusion that priorities should focus first on solid built-in handling, then robust validation and monitoring, with custom handlers and background notifications complementing those foundations. Now let's implement a way to handle errors gracefully by notifying users without blocking the initial request. In this example, we start by defining an asynchronous function called sendErrorNotification, which simulates sending an email notification when an error occurs. This function takes the user's email and the details of the error as parameters, and for now, it simply prints the notification details to the console. Next, within our user creation endpoint, we utilize FastAPI's background tasks to manage error notifications efficiently. If an error arises during the user creation process, instead of returning an error immediately, we add a task to the background that calls our sendErrorNotification function, passing in the user's email and the error message. This approach allows the original request to complete without stalling, even while we inform the user about the error in the background. By employing this technique, we uphold the user experience by ensuring that users receive timely feedback without causing delays in the request process. This implementation demonstrates one of the best practices for error handling, maximizing responsiveness in our FastAPI application. Now let's implement a test to ensure that our API correctly handles requests for non-existent users. We begin by importing the test client from FastAPI, which allows us to simulate requests to our application as though they were coming from a real client. Next, we create an instance of test client, passing in our FastAPI app as an argument. This sets up the environment for our tests. Now, we will write a test function named testReadUserNotFound. This function will execute a GET request to the endpoint that retrieves users, specifically aiming to access a user ID that does not exist, 999 in this case. Upon making the request, we then check the response returned by the client. The first assertion verifies that the status code of the response is 404, which indicates that the requested resource could not be found. Additionally, we assert that the response body contains the expected error message, confirming that our API properly communicates the absence of the user. This kind of testing is crucial to maintain robust error handling across the application, ensuring reliability in real-world scenarios when clients make requests that yield no results. To conclude, we've covered a comprehensive range of best practices for error handling in FastAPI. We discussed built-in features for returning proper HTTP responses, how to handle validation errors using Pydantic, and implementing customized handlers for both known and unexpected exceptions. We also highlighted the importance of effective logging, asynchronous tasks for user notifications, and ensuring proper testing of error responses. As we continue this journey, you'll find that well-implemented error handling not only enhances the user experience, but also provides the robustness needed in modern API development. Now that you have these tools and techniques under your belt, let's look forward to integrating FastAPI with React for full-stack development, showcasing how to balance backend efficiency with a delightful front-end experience. FastAPI has rapidly emerged as one of the most efficient frameworks for building APIs in Python. With its emphasis on speed and simplicity, combined with asynchronous capabilities, FastAPI provides an excellent starting point for full-stack development. In this lesson, we will explore best practices in FastAPI applications, emphasizing how to design your APIs using open standards like OpenAPI and JSON schema while maintaining readability and performance. So far, we learned about error handling best practices in FastAPI, including built-in features for managing errors, validation with Pydantic, and creating custom exception handlers for better API communication. We also explored logging, asynchronous background tasks for user notifications, and the importance of rigorous testing to ensure robust error response mechanisms. This foundation will enhance user experience and application reliability as we move toward integrating FastAPI with React for full-stack development. Now, we will cover best practices in structuring FastAPI applications, optimizing performance, and ensuring that our APIs are easy to use and maintain. The displayed pie chart titled FastAPI Best Practices Overview quantitatively distributes attention across 6 core areas: error handling 25%, performance 20%, architecture 15%, testing 20%, security 10%, and dependency management 10%. Key patterns visible on the chart show that error handling occupies the largest single portion, indicating it should be a primary focus when designing APIs. Performance and testing each take substantial identical shares, 20% each, together with error handling accounting for 65% of the chart. This highlights a combined emphasis on maintaining responsive endpoints and verifying their behavior through tests. Architecture, while smaller at 15%, remains a meaningful slice, reflecting the need for a clear project structure to support growth and maintainability. Security and dependency management are depicted as equal smaller slices, 10% each, signaling that while they may require proportionally fewer immediate resources, they are foundational responsibilities that must not be neglected. From these proportions, we conclude a practical prioritization. Invest first in robust error handling, concurrently optimize performance and build comprehensive tests, refine architecture to support these efforts, and ensure security and dependency practices are in place as essential safeguards. Now let's take a look at how to structure our FastAPI application. A typical structure involves creating separate directories for different functional components, which helps maintain a clean architecture as the application grows. Within the main application file, we initialize the FastAPI instance and include various routes by importing them from their respective modules. This modular approach keeps the code organized, allowing each file to focus on its specific responsibility. Next, we will implement the user-related endpoints in a dedicated file. We begin by creating an instance of API router, which allows us to define our routes related to user management. For example, we can create a route that responds to GET requests at the user's path. The asynchronous function associated with this route retrieves user data, returning a list of usernames, thus adhering to FastAPI's asynchronous capabilities. This setup ensures that our main application remains uncluttered, while each component of our app is clearly defined and manageable. By following this structure, we can further enhance the scalability and maintainability of our FastAPI application. Now let's take a look at how to set up a SQL Alchemy model for user management in our FastAPI application. The user class we define here inherits from base, which is provided by SQL Alchemy to work with ORM models. This class represents the users table in our database, where each user will have 3 columns: id, which is an integer and serves as the primary key; username, a unique string that ensures no 2 users can have the same name; and email, which also must be unique. This structure not only maintains the integrity of our user data, but also allows for efficient querying through indexing. Next, we will define the database connection setup that enables asynchronous interaction with our PostgreSQL database. Here, we utilize Create Async engine from SQL Alchemy along with a sync session, establishing a connection string tailored for asynchronous operations. The async session local creates a session factory to facilitate seamless database operations without blocking, a key feature for enhancing the performance of our FastAPI application. Finally, to effectively manage the database session within our routes, we implement a dependency function, getDB. This function utilizes an asynchronous context manager to yield a session object, providing an efficient way to interact with the database asynchronously as part of our request lifecycle. This approach helps maximize FastAPI's async capabilities while ensuring clean and maintainable code. Now let's implement a Pydantic model for user registration, which will help us validate the incoming data effectively. We start by importing the base model class from Pydantic, along with emailstr, to ensure the email field is properly formatted. By creating a user create class that inherits from base model, we define the structure for the user data we expect during registration. This class includes the properties username, typed as a string, and email, which is validated as an email address using emailstr. Next, we will utilize this model in our route for user creation. By declaring our route function, createUser, we specify that it accepts a user create object in a database session as parameters. The depends getDB syntax integrates our database dependency, allowing for seamless database interactions. Within this function, we will typically call our user service to handle the actual logic for storing the user in the database. For now, we are returning the username and email directly as a response, demonstrating how to process validated input efficiently. This structured approach enhances code maintainability and clarity as the application scales. Now let's implement a simple token-based authentication system using FastAPI's security utilities. We begin by importing necessary modules, including FastAPI's security components to facilitate user logins. The OAuth to password bearer instance defines where the application will expect to receive the token, which in this case is through a specific token URL. Next, we create a post endpoint at token that accepts user credentials in the form of an OAuth to password request form. By using FastAPI's dependency injection with depends, we can automatically handle the incoming form data. In this endpoint, you'll need to implement the logic to authenticate the user's credentials, and upon successful validation, return an access token formatted as a JSON response. Following this, we implement another endpoint, usersMe, which retrieves the current user's details based on the provided token. By utilizing the security function in the root handler, we ensure that only authenticated users can access this information. This design effectively protects sensitive data and highlights FastAPI's seamless ability to generate automatic security documentation, enhancing both functionality and user experience. Now let's see how we can implement caching to enhance performance in our FastAPI application using Redis. First, we import the Redis library, which allows us to interact with a Redis instance asynchronously. Next, we establish a connection to Redis with the specified URL. In our cache implementation, we create an asynchronous function to retrieve user data from the cache. This function checks if the requested data is already stored in Redis before querying the database, significantly reducing unnecessary database operations and improving response times. If the user data exists in the cache, it decodes and returns the data. Otherwise, it returns none. Additionally, we define another function to cache user data. This function takes a username and user data as arguments and asynchronously sets the data in RDIs under the corresponding username key. By utilizing these caching functions, we ensure that frequently accessed user data can be served quickly, optimizing our API's overall performance and responsiveness. Caching is a crucial practice when designing efficient APIs, especially when working with high traffic or large datasets. Now let's see how we can test the user registration functionality in our FastAPI application. To facilitate this, we use FastAPI's built-in test client, which allows us to simulate requests to our application. Initially, we import the necessary classes including test client and the app instance from our application's main module. Next, we instantiate the test client with our FastAPI app, which enables us to invoke endpoint requests directly. The code then defines a test function called test_create_user, where we simulate a post request to the user registration endpoint at users. We supply a JSON payload containing the username and email of a new user. Once the request is made, we capture the response and proceed with assertions to verify whether the response's status code is 200, indicating success. Additionally, we check if the returned JSON object matches the input data, confirming that the registration process works correctly. By implementing such tests, we can easily validate that our API behaves as expected, thus ensuring quality and reliability in our application's functionality. In conclusion, the best practices we've explored today for building FastAPI applications serve as a solid foundation for creating robust, efficient, and maintainable APIs. By focusing on proper structuring, database integration, dependency management, security measures, caching, and rigorous testing, you can ensure that your applications are not only functional, but also ready for the challenges of real-world usage. We have covered a lot in this lesson, giving you tools and techniques to enhance your FastAPI implementation. As you move forward, remember that these practices will significantly contribute to the overall quality, performance, and security of your applications. Stay curious, keep experimenting, and happy coding. Welcome to today's lesson on common pitfalls in FastAPI development. FastAPI is a powerful framework that can help you create efficient APIs quickly, but it's not without its challenges. Understanding these pitfalls from the outset can save you time and frustration down the line. So far, we learned about best practices for building FastAPI applications, focusing on structuring your project for maintainability and scalability. We explored efficient database integration, the significance of dependency injection, security measures like OAuth 2, performance optimization techniques, and the necessity of rigorous testing to ensure reliability. Now, we'll cover common pitfalls that developers face when working with FastAPI and how to avoid them. Let's dive in. Now let's take a look at how to effectively structure your FastAPI application to promote maintainability and scalability. In our example directory structure, we begin with main, Py, the core of the application that initializes the FastAPI instance. Following this, we have a models directory containing user, Py, where we define our data models. This separation ensures that our Pydantic models are organized, keeping business logic distinct from data representation. Next, the routes folder features user routes, Py, housing the endpoints related to user management. By isolating routes related to specific functionalities, we enhance clarity and streamline navigation. Moving to the services directory, we include user service, Py, for implementing business logic such as database interactions and data processing. This separation of concerns is crucial for easier testing and modification. Lastly, the utils directory with helpers, Py, serves as a place for utility functions that can be shared across the application. This thoughtful organization not only minimizes clutter in main, Py, but also fosters a more manageable and scalable codebase, making it easier for developers to collaborate and troubleshoot efficiently. The displayed chart titled Common Pitfalls in FastAPI Development is a horizontal bar chart that maps 6 specific pitfalls to their reported impact levels in % on a 0-30% scale. The data shown assigns the highest single impact to blocking code at 25%, indicating that synchronous or long-running operations are the most significant single source of problems in FastAPI applications. Monolithic code base and lack of data validation are tied at 20% each, forming a second tier of major concerns that reflect structural and input safety issues. Improper error handling is shown at 15%, while neglected testing and security oversights are both at 10%, representing lower but still meaningful risk areas. The values sum to 100%, so the chart conveys a distribution of relative impact across these categories rather than absolute counts. From this distribution, we can conclude that addressing blocking operations should be the top priority, followed closely by modularizing the code base and enforcing validation. Error handling, testing, and security, though assigned smaller percentages, remain essential because their combined impact is substantial. The horizontal layout and labeled impact axis make it straightforward to compare the magnitude of each pitfall, reinforcing the lesson's emphasis on prioritizing asynchronous design, clear structure, and robust validation as immediate mitigation steps. Now let's implement custom exception handling in FastAPI to provide meaningful feedback to users when errors occur. We start by creating a custom exception class named itemNotFound, which will be triggered when a specific item is not found in our API. Next, we define an exception handler for this custom exception using the @appExceptionHandler decorator. In this handler, we ensure that when an itemNotFound exception is raised, the API responds with a clear JSON message and a 404 status code, indicating that the requested item could not be found. Now let's take a look at the route defined with the @appGetDecorator for fetching items by their ID. Here, we simulate a scenario where only item ID 3 exists. If a user requests any item ID other than 3, the itemNotFound exception will be raised with a descriptive message. This implementation allows the API to provide users with specific feedback instead of a generic error, ultimately enhancing user experience and making it easier to debug issues when they arise. By handling exceptions in this way, your FastAPI applications become more robust and user-friendly. Next, we will examine a common pitfall in FastAPI development related to blocking code when fetching user data. Initially, we have a synchronous function that retrieves all users from the database using SQL Alchemy. The getUsers function makes a blocking call to the database, which means that while it's waiting for the data to come back, it can't handle other requests. This can lead to performance issues, especially in an asynchronous framework like FastAPI that aims to handle numerous requests simultaneously. Now let's see how we can implement an asynchronous approach to improve performance. By utilizing async session from SQL Alchemy's asynchronous support, we can rewrite the getUsers endpoint as an async function. This allows FastAPI to utilize Python's async capabilities effectively. Within this function, we use the await keyword to execute the query without blocking the main execution thread, enabling the API to process other incoming requests while waiting for the database response. This shift not only optimizes performance but also maintains the responsiveness of the API, allowing it to serve users more efficiently. Next, we will implement a Pydantic model for user registration, which plays a crucial role in validating user input data. We start by importing the necessary classes from the Pydantic library. The user create class is then defined, inheriting from base model. This class specifies two attributes: username, which is a string, and email, which is validated to be a proper email format using the predefined emailstr type. By utilizing this model in our API endpoint, we ensure that any incoming data for creating users adheres to the specified structure. Now let's take a look at the createUser function, which is defined as an asynchronous post endpoint at users. When a request is made to this endpoint, FastAPI automatically parses the incoming JSON into a user create instance. If the data fails validation, FastAPI promptly returns an error response, preventing invalid or unexpected data from being processed. This approach not only simplifies your code, but also enhances error handling and improves the overall quality of your application by catching data issues early in the workflow. Now let's implement a testing strategy using PyDist and FastAPI's test client to ensure our user creation functionality works as expected. First, we import the necessary components: test client from FastAPI, test client, and the app from our main application file. The test client allows us to simulate requests to our FastAPI app as if they were coming from actual users. Next, we create an instance of the test client, passing in our FastAPI app. This setup provides the context for our tests, allowing us to send HTTP requests to the endpoints we want to test. Now let's write a unit test for the user creation endpoint we previously set up. In this test, we will send a post request to the user's endpoint with a JSON body containing valid user data, including a username and an email address. We then assert that the response status code is 200, which indicates that the request was successful. Furthermore, we check that the response body matches the expected output, confirming that the user was created correctly. By incorporating this testing strategy into your development process, you can ensure ongoing reliability and catch potential bugs early in your FastAPI applications. Now let's implement a simple token-based authentication system using FastAPI's built-in security features. We start by importing the necessary classes, OAuth to password bearer and OAuth to password request form, from the FastAPI security module. The OAuth to password bearer function helps define a security scheme for our application, specifying that tokens will be obtained from a designated token URL, which we set as token. Next, we create a post endpoint at the token root where users can log in. Here, we define an asynchronous function named login that accepts form data containing the user's credentials. Within this function, you will need to implement your authentication logic, such as validating the username and password against your user database. Upon successful validation, we return an access token along with a token type indicating it's a bearer token. This access token must be included in requests to protected routes, allowing FastAPI to determine if the user is authorized to access specific resources. Implementing such security measures is crucial for safeguarding user data and ensuring your application maintains its integrity against unauthorized access. Now let's implement a simple user creation function using motor, an asynchronous driver for MongoDB. The code begins by importing the necessary module to connect to a MongoDB instance. We establish a connection to the database through the async.io motor client, which allows us to perform asynchronous operations. Next, we define a database variable to specify the database we want to use, in this case, my database. This sets the foundation for our subsequent database interactions. Then, we create an asynchronous function named createUser, which will handle the insertion of user data into the database. Within this function, we utilize the insert1 method to add a new user record. This method takes the user data as input and returns a result object that contains information about the operation. By accessing result_inserted, we can retrieve the unique identifier of the newly created user. This approach not only showcases the effectiveness of asynchronous programming, but also emphasizes proper schema definition, which is crucial for maintaining structured and efficient data storage in MongoDB. Now let's take a look at how we can create a route to retrieve a list of users in our FastAPI application. We define an endpoint using the @appget decorator, specifying the path as users and indicating that the expected response model is a list of user objects. This means that our API will automatically expect and return data formatted as a list of users based on the defined user model. Within the function getUsers, we include a docstring that clearly describes the purpose of this endpoint. It retrieves a list of users and returns it, or an empty list if no users are found. This documentation is not just for our own understanding, but is also conveyed in the automatically generated OpenAPI documentation, making the API self-explanatory for anyone who interacts with it. Finally, we would typically include the logic for fetching the users from our data source within this function. This design promotes clear and structured code, ensuring that our API is maintainer-friendly and accessible for future developers or for ourselves later on. Proper descriptions and structured implementations like this are crucial for creating effective and user-friendly APIs. In summary, we've covered several common pitfalls in FastAPI development that can hinder the robustness of your applications. From ensuring a well-structured codebase to implementing effective error handling, performance optimizations, proper data validation, committed testing, and enhanced security, every aspect plays a pivotal role in constructing solid APIs. Additionally, it's vital to appreciate the nuances of working with MongoDB and the importance of maintaining comprehensive documentation. By being aware of these pitfalls and following best practices, you can significantly elevate the quality of your FastAPI applications and prepare them for the complexities of real-world usage. As developers, continuous learning and improvement should be our constant goals. With that, keep experimenting, stay curious, and happy coding. In this final section, we will do a project challenge to apply what we have learned so far. Your task is to build a full-stack web application using the Farm Stack, specifically a used car sales platform where you can display, create, and manage car advertisements. You will create a backend with FastAPI to support CRUD operations, implement user authentication, and manage your data with MongoDB. On the front end, you will use React to create a dynamic interface that interacts with your API and utilizes React Router for navigation. Security is vital, so you'll integrate JSON Web Tokens, JWT, for user authentication, ensuring only authorized users can access certain features. Once your application is fully developed, you'll deploy both front-end and back-end to hosting services like Netlify and RenderCom. Remember, this is your chance to showcase your skills and creativity by bringing your ideas to life. For more details on the project, refer to the final project documentation in the GitHub repository linked in the description. Good luck and enjoy the process of building your application.